distribution is much lower. This is an analysis, a similar analysis that we made in comparison with the whole Europe. We have some numbers. I'm not basically our idea is we make these products. These all are independent validation data sets. We did with the GPCP, with GPCC, with many others, with the reanalysis. And basically all of the times we found that at least the product is better than the parent product that we've used to integrate them. And also most of the time, for instance, if you look EMO, for Europe, EMO is median correlation 0.72, and for this product, it's 0.8. So it's really much better. And the same happens for instance, root mean square error, and also for the bias. And for instance, if you look again at this hyper-P is the red one, in comparison with triple collocation by using two independent products, GPCC and MERA2. Of course, we are fully aware that GPCC, for instance, in Africa, in the center part of Africa, there is no gauge at all. Center part means 1,000 and 1,000 square kilometers. But basically, our product seems to be, the world looks quite red. It means that basically the product is outperforming the other two products. We have several papers running and using these products published. Basically, the product is available since 2024. We have already several papers trying to use these products. We are using also in the project that we have European Space Agency and European Commission, also with EUMETSAT. Let's see what happens, and because actually it's quite new. And also making the modeling community working with this product is super difficult. We had a project with European Space Agency, 2-year project. We told them, okay, come on, we have new precipitation, try to use this new precipitation instead of EMO. For hydrological modeling, it's super easy because actually you have just to change the input file. You don't have to make a simulation, something difficult. But we were able to do this kind of stuff only the last 2-3 months of the project, and at the end of the project, we didn't have the final results. So basically still, making the people working with this data is difficult, but we are trying to make this. But now go back to this Sentinel-1. As I mentioned, basically by using Sentinel-1, we should be able to have really dynamic 1 kilometer high resolution. We have a good example done in the Po Valley, because actually in the Po Valley there is also a kind of overlap of the overpasses, and so we have temporal resolution even of every 1 day and a half, 2 days. And for instance, we have developed this 1 kilometer, 1 hour precipitation product, including Sentinel-1, that is basically, and on the box plot, here is a hydrological validation. It means that we have used the product into the modeling, and we made a comparison for different gauge, stream gauge in the basin with an hydrological model. And here are different precipitations. So POBS, for instance, is observed precipitation, more than 1,000 gauge. That, for instance, the median KGE is a number 1, means perfect, 0.79. And basically, with the integrated satellite data, we get the TTE hydrology is the one on the right. We get even the best performance possible. And this is the first time that we found these results. So we say, come on, we are there. We can go ahead, and we can use Sentinel-1. We have made several attempts. For instance, we have tried also to use AI for ingesting Sentinel-1. But for instance, in this plot, it's not super visible, but the observed data is the magenta line. When we use AI, typically root mean square error is quite good, but we are struggling a lot to have zero, non-zero precipitation. So basically, we have to implement 2 different AI for zero and non-zero events. We have to basically make, but actually, it's it's quite difficult to get reliable results. One of my previous students, basically, he studied a lot AI techniques. I don't understand anything about that, but basically, he was able to develop a framework, an architecture, they call it architecture, to integrate also Sentinel-1 for getting 1 kilometer precipitation. And we did for the whole Italy. And actually, for instance, in this is the map that you can see on the left, the zoom. It's 1 kilometer. It's quite noisy, but it looks more reliable than at least less smooth than the 10 kilometer products. But still, this is the only example that we were able to basically provide. We are still working on it. We tried several times, but basically we didn't find a solution so far. Hoping that, for instance, by using also NISAR, integrating the different products, we can have a better temporal resolution, and also we can be able to have high resolution products. What else? Yeah, final uncertainty. Yeah, uncertainty is, I agree that it's a kind of topic to be discussed in the bar. And also basically different people look at uncertainty with a different perspective. What we have done in this paper together with some Greek colleagues, basically we were able to provide an estimated of precipitation plus uncertainty that looks quite reasonable. Because, for instance, we made several other attempts in which basically we published something that looks not really reasonable. The target here is basically we use observation to develop these confidence intervals, and then when you look at the precipitation and the uncertainty bar, that looks quite reasonable. This is done both for the Mediterranean region. Now we want, because for instance, in this digital twin project, ESA is pushing a lot every product developer to develop a product plus uncertainty, because then we have to track uncertainty to the modeling, and then we see what is the uncertainty of the final decision. This is super difficult, and the EO developer basically they don't care too much about uncertainty so far, and so basically it's another challenge that we have to address. Two last slide. This is a new journal that we just launched for the European Geoscience Union, Earth observation. If you have paper, it's open access, and it's going to be quite nice. And also this is, if you are interested in the topic of digital twin, we have a special issue on this topic. That's it. No, there is also a paper, a presentation tomorrow, in which basically we are trying to use gravimetry instead of SOLMOS2 for getting precipitation back in view of the next generation gravity mission and the MAGIC mission, that is basically the coupling of NGGM and GRACE in the collaboration between ESA and NASA, that is going to be flying probably in 2032, 33. Thank you very much. This one?
Sí, okay.
It just looks to me like, I mean, the CNN, you probably did some tiling, right? I think I can see the tiles in the results, right? You see the rectangular artifacts in your results in the bottom left?
Probably yes.
I mean, those are the CNN tiles probably, right?
We have to ask to Hamid, to Mosafa.
I mean, it just seems unlikely that this has a 1 kilometer resolution if there's like artifacts.
No, I fully agree with you. The problem of 1 kilometer, I am in between, people asking for 1 kilometer, and we are trying to make 1 kilometer without trusting really that is 1 kilometer. But it's a kind of, I don't know, way to go, or let's try first attempts. But I agree with you. It's when you go high resolution, it also looks very noisy to me. But at least it's an attempt.
So they just want the variability. Like I mean, they could interpolate the results themselves, right? I mean, I just. Yeah, but what is the benefit of having like noise instead of a smooth result?
That's good question. And my answer is always the same. Try to make this. Try to use the products on the right and the product on the left in your simulation. Let's see what happens. I fully agree that it can be not reliable, but just looking at the image with my eye is not enough. I want to have some other confidence about that.
Yeah, but do you? Like, where do you get, I mean, I think 1 kilometer is like almost, right, where do you get even like a ground truth from?
For instance, as I shown in the Po Valley, for instance, we have 1 kilometer precipitation by integrating the radar plus gauge. There we have the ground truth.
Exactly.
And for instance, here is, this is the best products that we were able to get around 1 kilometer. And if you look at the patterns, it looks quite reasonable. But this is just for the Po Valley we were able to find these quite good results. When we just go over Italy, it starts to be an issue.
Okay, yeah. Yeah, I'm just thinking like 1 kilometer seems really, I don't know if we ever get there.
No, indeed, I feel like with you. I'm not saying that we have developed a 1 kilometer product. I'm saying that we are. But if, as I have shown you in the third or fourth slide, for the Solmosto community, now we have plenty of 1 kilometer products, and the people are really saying, okay, we are there. We are not there. In all of my talk, presentation, and everything, I'm saying, we want to target this, okay, that's fine. Looks at the results. I'm not hiding the bad results that we get. I'm not saying that we are there. I'm saying that if you want to go there, still, it's a challenge. But if you live in Europe and you look at the Destination Earth initiative, they are saying, now we are going to provide you 1 kilometer, 1 hour simulation of everything, not only precipitation, but also snow, carbon, whatever. Come on, we are not there. But why not? This is science, basically. Trying. It's a lot of noise, yes.
Any other questions? Okay, well, thank you so much for the great presentation. And we'll start with our next panel soon. So I'd like to ask the speakers from the panel to join us up here. So this panel, the first panel of IPC15, will look into how the private sector can contribute to a greater impact on precipitation science and applications. I'm happy to be joined by Viviana Maggioni to co-moderate the session, and of course our speakers, Michael Marks, Ethan Nelson, and Olaf Bierman. So from WeatherStream, Tomorrow.io, and Development Seed. Viviana, please. So I think we can start with a brief introduction. I would like to ask you to just introduce yourselves, a little bit about your work, your organizations, and how your organizations are using precipitation, climate data for impacts.
Hello. All right. Yeah, so I'm Michael Marquez. I'm VP of Engineering at WeatherStream. Primarily at WeatherStream, we're working on developing sounders at this point, so we're not as deep into the precipitation as probably some of these other people here. As far as utilizing the precipitation data, we do have some soil moisture. We make an L-band soil moisture drone, so we do measure soil moisture. We don't actually integrate the precipitation too much. We do have an ML model that lets us estimate soil moisture from precipitation. And I think it's kind of the extent of our work on the precipitation side of things. We do obviously do some retrievals of precipitation from the microwave sounder data, but our satellite did just launch, so we haven't had too much time to actually validate that yet.
Hello, everybody. My name is Olaf Veerman. I work for a company called Development Seed. So we're also not super into the precipitation. We work a lot more with EO, within the Earth observation sector. We're technologists. We work with organizations like NASA and ESA and the World Bank on figuring out how to efficiently store and publish, distribute data so that people can use it for impact. Our mission is to shorten the distance from data to impact, so I think it's pretty appropriate for this panel. We have a little bit of precipitation experience, but I'll get into that, I think, in a little bit. Yeah.
Hey, good morning, everyone. My name's Ethan Nelson. I'm with Tomorrow.io. I've been there for about 5 years. Prior to going to space, we had just an enterprise offering, so trying to produce global precipitation analyses, short-term nowcasting. But now, for a few years now, we've been launching satellites, first K-band radars, and now microwave sounders. So we're really focused on trying to get the data and really increase revisit rates. And I wouldn't say we're trying to do the most cutting-edge precipitation research. We're more interested in kind of operational products and generating some of those lower-level, level 1 data that can then be used by researchers or other folks to really apply kind of the cutting-edge machine learning or other research techniques.
By the way, we were just joined by Pedro Rezende from Owl Places, so welcome.
Hello everyone, my name is Pedro Rezende. Sorry for the delay, I had car problems. Normally the people that live nearby are the ones that get late. This is the proof. So I'm the founder of Owl Places, and we work with several data sets, among them precipitation also data, a lot of Earth observation to analyze risks in real estate properties. In terms of precipitation, we use also atmospheric observation. Among them, we are using Destination Earth from the European Space Agency and the European Union, which allows us to understand thresholds in terms of volume of precipitation, extreme levels of precipitation. And with that information, we can warn the clients and be more precise in the locations which can have extreme events. And we are very focused in transferring this data, this knowledge, to actionable insights at the location level. Thank you.
Thank you. So the way we're going to do this, we're going to ask a few questions just to get the conversation going, and then we'll open to the audience for questions as well. And also, if you want to ask questions to each other, please feel free to do so. So to start, and to all of you, how do you see the private sector's role in climate science, precipitation science? Do you see it as a competing role? I think we talked a little bit about that yesterday. Competing role with traditional organizations like agencies and universities, or more complementary?
Should I start? No, definitely complementary. So we are using standards that come from the industry experts We are more focused in the later stage TRL, so close to market, close to adding value to the users. So we need validated evidence. We need all the lower TRLs that come from academia, that come from private also and public institutions that are researching, and we need this in order to have a defensible approach to value that we bring to our customers. So I would always say that it's complementary, and one should work together with the academia and the institutions making research.
Yeah, I would agree on that. Complementary as well, and really, kind of our focus is at least like moving fast and launching things. So, we can commercialize or standardize like a small instrument and get 30 up in 4 years. So, the quality is not going to be necessarily as good as these billion-dollar gold standard missions that are launched by governments, but the point there is to be complementary. So you have really those super high resolution, very well calibrated satellites that are providing kind of anchor observations, and then we're coming in and trying to fill those gaps. And so I think there's a lot of room for kind of partnership and sort of a hybrid relationship there.
Yeah, and I think that's I think that's especially evident in the weather for weather sector. If we're not really operating in that sector, but we look with a lot of envy to it, because I think it's a very dynamic part. Where if you look at all these short-term weather forecasting companies like Jua and Brightband and more, they provide a real complementary role to organizations like ECMWF, right? I think the ability of these companies to produce a product that really ties in with, they have, I think, very deep expertise of a particular domain, right? They know how to reach the data consumer. They know how to provide the data in a way that they can really use it. I think that's a very exciting place right now, but very complementary, right? Because I think all these private sector companies wouldn't exist without some of the models that an ECMWF is putting up, right? So.
Yeah, no, I'd have to agree, complementary. I mean, I think there's a little bit of competition, you can't deny that. But, in general, sort of the direction we're going in with these sensors, it's not just, so we are, pretty much engaged in that same activity of trying to launch a lot of satellites for revisit, but we're also looking into some larger programs, right? It's pretty clear that the direction NOAA is going in is more commercial, so they're not putting another sounder into the 1730 orbit. So to put something there that's, going to be Simba class with all those bands is going to require, either ESA to do it or the commercial sector to pick up the slack there. So we're working, to improve calibration, trying to work with NIST. In that sense, it's complementary. We want to, collaborate, make sure we have consistent calibration, all of these things.
Sorry, can I add one note? I agree with you on the competition. I think in a certain sense it's healthy, right? I think if Google a couple of years didn't, make it clear that their ambition was to go into the weather space, ECMWF would never have moved as quickly on adopting AI in their modeling, right? So I think this was sort of an external existential threat for ECMWF, and it's amazing how how an agency like that was able to move so quickly and is now producing the type of models that they do, and if really, I think are really leading the way there.
Beautiful. Thank you so much. So the theme of this conference is harnessing the data revolution, and the title of this panel itself is From Data to Impact. So the question is, in your experience, what does it really take to turn our precipitation and climate data into decisions that really matter to our communities? And feel free to answer in random order and skip the answer if you don't have anything to add.
Yeah, so from our perspective, I think we're still more focused on getting more of our own proprietary data. But in terms of trying to do impact, you know, we are working with other companies mostly in terms of trying to sort of apply this to like the energy sector, sort of line load ratings, the insurance sector, trying to make sure they have the data they need to do parametric insurance, to do all these things. I think from our perspective, we're trying to more be a data provider and then work with other partner companies on these things.
Yeah, from a data producer perspective, I think standards and interoperability really matter. So publishing your data in a way that organizations downstream can use it well, right? I think there's hardly any decision that relies on data from only one data product, right? I think, sure, if you want a simple decision like, do I go to the supermarket, buy a bike or car, right? You look at roof on rain, yes or no, but most of the other, right? If you're looking at flood risk, it takes so many different data products, soil moisture, and you want maybe physical infrastructure and terrain maps, right? And being able to pull this requires data to be readily available, but also easily accessible, interoperable and formats. I think what's very interesting, what's happening right now, if you look at the different sort of climate data, EO data, weather data, I think they used to be available in very different sort of formats. And I do think that we're seeing some convergence right now, which I think is very interesting. I think ZAR, for example, is I think one of the data formats that's really up and coming. We're right now working with NASA to turn the GPM image into make that available in ZAR format. I think those are very interesting. Interesting things that are going on, right? Sort of this convergence to these interoperable formats.
Yeah, I think one thing early on in kind of our company history was realizing that it's hard to make sort of a one-size-fits-all solution. Like I'm just going to make a data set and then throw it out there and everyone can use it appropriately. I know there's a lot of discussion yesterday about like red, yellow, green versus thresholds versus whatever else. And so at least from the commercial side, we focus on specific customers. Like Chris said, people come to us with money and say, can you fix a problem? An airline comes in and says, I have these different icing or de-icing scenarios and they cost this dollar, this dollar, this dollar. Apply a probabilistic forecast to that. So at least for us, it's really nice where we can work directly with our end users, find out their story, or specialty pharmacy, hey, this last 20 hours on a truck, am I going to make it or is it going to spoil? So going in and really understanding the users and kind of building a contingency table of cost versus risk appetite, I guess. And then applying our data sets to that and really driving decisions for them. So it's very customized and I would say bespoke, but is at least one way that we can actually apply the data and solve direct operational solutions.
In this particular regard, I would like to bring Owl Place's impact underwriting. So we are working with insurance companies, and right now they are being pressured by regulatory bodies to promote climate resilience. And one of the ways is to prove that the client has climate resilience or has achieved a certain degree of climate resilience, and with that have a better premium in the insurance. So we are the entity that is validating the climate resilience, that is supporting the plans to achieve climate resilience. And we believe that this is the way that also the financial entities, insurance companies, banks can help promote within their portfolios the impact. And of course, one of our goals since the beginning is to democratize the access to this data. And we are finding out that the best way to do it is to really work with all agents in the value chain, especially the main distribution channels. So this is the point.
Thank you. Now, I think I'll take the cue from your answer and ask you all. So we talked about trust and validation, and that's very important for defensibility, even. Sorry. So we were talking about validation, calibration, trust, and all that. How do you see based on also the speed of launches, like the need to have a lot of data, and also in terms of platforms, and then for the more on the side of the end users, how can we make sure that we maintain the level, the quality, or even improve it, so we can go to court? And we have some experts here who can then talk a little bit about this as well. Go to court, defend those numbers, if a customer contests and tells us, well, you know, I saw the rain, why are you not paying me? So how can we solve that problem?
So it has also been mentioned, the parametric insurance, so assigned certain thresholds of values of moisture in the soil or precipitation levels, heat that can damage the crop. So, and this type of thresholds is very easy to prove with the Earth observation. And this is I believe that this is one of the trends that will have an impact, especially even in African countries and Asian countries. So definitely, I would mention parametric insurance in this regard.
Yeah, I think that, I mean, from our perspective, we want everyone to validate and you know, to check the dots on our I's, the crosses on our T's. I think, as Michael mentioned about, like, obviously a lot of public agencies are moving towards just commercial data buys, but I think there needs to be, you know, a prerogative or sort of just a priority to allocate funding still. Excuse me. Validate funding for scientists, people in academia to validate the data, because, you know, a lot of us have a history in, you know, academia, working at universities, working at agencies, but we work for that company now, so there's obviously a conflict of interest. So we are really interested in partnering with researchers, with institutions, with these agencies to assess and validate our data. One, because it potentially gives, you know, other end users or other agencies kind of an independent assessment and validation and check of that data. But two, it also helps us because then we can see where we do have deficiencies, you know, next generations of instruments, how can we improve those? So, you know, I think sunlight is really the best kind of, maybe not disinfectant, but it at least, you know, opens the window and allows us to truly understand what we're dealing with.
I'll pass on this one probably.
Yeah, no, I think I'm mostly going to agree with Ethan here. It's great to have the community evaluate our data. Like you said, there is that conflict of interest. I think our goal is to have our data available as much as possible, open for, you know, scientific use, even if we are selling it commercially otherwise. But yeah, we want people to look at our data, show that it's useful, show that it's improving the models, you know, aside from ourselves.
Okay, thank you. So going back to the very first question, you all said that what you do, what we do is extremely complementary, right? So can you give us some examples of possible partnerships, possible initiatives that we could look at between academia, between the private sector, institutions, research labs, whatever comes to mind?
I know currently, for example, we're still working with NASA on a number of science programs There's the upcoming NASA Falcon, for example. It's basically a project to help develop higher frequency microwave radiometers for studying liquid water path and other similar things. So that's the main example that comes to mind, is still continued with that hardware partnership development. But also on the science, the data products, we saw so many great talks about how to use the existing data. I think that's a really important thing to continue, is that this research, the very creative ways to use the data to improve the products continues.
Yeah, I think two very big programs where this public-private partnership works very well. I think one is NASA has the CSDA program, so the commercials, satellites, data acquisition program, and ESA has the TPM, third-party mission, which is sort of equivalent. I think that's a great example of, a good public-private partnership, right? Yeah.
Yeah, I think echoing validation, data product generation, using our data for novel R&D as well. I mean, the reality is the scientists on our at our company, we very much want to do cutting edge, and we want to really explore with that, but the reality is we just don't have the time for that. So often it's about us kind of making connections and trying to enable researchers to use that data for innovative products, for validation, and so on. So, we're very open to collaborations in general.
So definitely, the time issue is a big thing, because in the market we need speed, and we have speed. So we have speed for validating with the end users. And on the other way around, we also need time in the research part. So definitely it will always be a necessity to collaborate. And then, of course, all these programs between NASA, the European Space Agency as well. So it allows to create new businesses, but also to understand new data sets that are being launched. And it enables the public-private partnerships to test the data, and then to understand how that data can be used in the market, and also to project what is expected to be the most needed approach for that data.
Thank you. And so we have two companies here that use data, two companies that generate data. I would be interested in understanding a little bit better how, for instance, Development Seed or OWL places could use the data from Tomorrow.io or WeatherStream, because from my understanding, a lot of the companies developing platforms or having direct contact with users rely a lot on open data from NASA, ESA. So how could we see in the future this integration of private data into your platforms?
So definitely, in some cases, the revisit time, the resolution, if the user has budget and has specific needs, we need to rely on private data suppliers. And so definitely we integrate with several private suppliers for using APIs for several data sets. And I would say that this will continue, especially where we see the sector going in terms of real time. So the users are creating an appetite for more data, real-time data, which is very hard, as you know, to really have real time. And also we see that it will start from the upstream, from the acquisition, from the satellites, and all this connection, not only the companies that launch the satellites, but also the companies that have the sensors and are responsible for the sensors that are mounted on the satellites, and how they connect the data to downstream to Earth. This will be very important, and of course we are very downstream, so we are creating platforms. We need this to also be very competitive in terms of costs, basically. So we need more offer on the private side, definitely, so that we are able to supply what the clients are in many cases demanding.
Yeah, I don't think it's so much for us an open versus closed data. I mean, I think there's space for everything, right? And I think private companies also need, you know, I understand why companies would want to not open up everything. Again, going back, I think it's about standards and interoperability, right? So I think that's what really unlocks value ultimately. I think, right, it's also in the benefit of WeatherStream to be publishing their data in ways that people can really easily pull it in, even if it's closed, even if it's paid, right? Even if it's paid. So yeah, first it goes back to sort of interoperability.
I mean, I'll just make a quick comment, which is, you know, the goal, I think, with a lot of the commercial data buy program is to sort of offload some of the cost off of the government onto other commercial users. I think the main value we see from our data is the low latency, right? That's where the real selling point is. So, you know, it's one of the ways we're very happy to provide the data is, you know, at a delayed latency to more academic users.
Thank you. So open science, but also access and equity. That's very important when it comes to climate services and climate science in general. So the question is, how can public and private partnerships really ensure that our data, that our science can be reachable to low-income institutions, vulnerable regions, and communities that may really need the kind of things, the kind of science that we do?
Yeah, so I think from our perspective, well, obviously for doing the science, we're hoping to keep as much of that open academically as possible. The low latency obviously has a pretty big impact in terms of disasters and extreme events. So I think as far as getting that data out, you know, to sort of lower income areas, we want to make that as accessible as possible. So we're going to be looking into how we can, you know, price the data appropriately for that. Obviously, some of that will be taken up by the NOAA data buys, providing enough data to sort of make up for some of those other areas.
Yeah, I think, of course, there's making data more accessible and open, I think, is very useful, but I think that doesn't necessarily guarantee adoption. I think there's a potentially a capacity building component. So we've been doing some work with a nonprofit called OpenAQ. They're trying to harmonize and make air quality data from across the world openly available. But they also have an ambassador, AQ ambassador program. I think they're now in their 4th edition. They've trained 40 people from low-income countries, provide them with some real resources, a stipend and travel budget and sensors. And yeah, I think that's a really nice way to enable people to work more with the data and yeah, create real impact on the ground.
That's a very good point. Sorry for interrupting, but I think maybe that's something that we're missing here at the table, you know, no-profit organizations, and that may really help us bridge that gap.
Yeah, I think, at least from our perspective, I think it's two-pronged. One, so kind of on our development side, we're actually, I don't know too much about the program, but we have like scientists and other folks at the company that are going to med agencies around the world, actually. One of my colleagues was in Trinidad last month, for example, and really partnering with those med agencies on the ground to be like, here's our platform, here's how you can use it, kind of getting that on the ground perspective of, you know, how do you connect a forecaster in some country to an API, and how can they utilize that effectively? And then I think the other prong of that is we actually have a nonprofit organization called Tomorrow Now. And so through that, we can directly partner with institutions like the Gates Foundation, for example. So we're tied directly to farmers in East Africa. So they get text messages like when to plant. It's gonna, or it's gonna rain or be windy the next week. And so really, again, it's about finding institutions and pathways to connect us with people on the ground so we can learn and understand their user story and then appropriately apply the data for their use case. Who the end user is and where they are really shapes what the form of that is, whether it's more of an API, whether it's low data rates, or even just simple text messages. We're really just interested in trying to do as much of that as we can as well through that nonprofit.
This is a very important issue. I think in the past events here we had in Portugal, February, all of us got SMS messages warning to protect ourselves. But I think this is not enough. We need precise insights even in these messages, and even considering other economies, we need to have specific benefits for these people to use the data. Otherwise, they will not use the data. If they don't see in the bottom line that by using the data they will be able to sell at a higher price the product that they are farming, or even not speaking about carbon credits, but all the diverse recipe sources that we can create using data, I think this should be also of public interest, because in the end we need also these people to contribute and to have a way of creating wealth. And I feel that here in Portugal and in Brazil, not giving tools or with precision enough for the people to use the data, the value.
Yeah, I think one more thing, that this question kind of ties in a lot of answers from the others too, is that I think for when these agencies are looking at commercial data buys and trying to invest in that space, it's imperative that they are choosing companies that are being open, that are publishing methods and basically how they're generating data, how it's calibrated, and not black boxes, because those like very invisible, we went from this to this really nice data set, that doesn't help kind of equity and access to data, because if people don't know what they're using, then they're not going to adopt it either.
Thank you so much. I think we can now open to questions from the audience. Who wants to start?
We're going to go back to uncertainties and metrics. So in listening to you, I think, let me first back up. So in data buys, it's fairly straightforward. The government can specify exactly what it needs, and if you don't meet it, it doesn't buy it. Right? In products, in services, right, where you have customers, and I think at least 3 of you have that. Can you talk a little bit about, what I hear is that don't try to make an uncertainty until you have a customer. Once you have a customer, they sort of make it pretty clear and you have to provide that. But can you give us a little bit of a sense for how important that is in your field, or whether largely the customer simply wants an answer from you? And your job is to provide that, and you don't give a flood warning that's 70%. You say either get out of your house or don't. So can you give us a little bit of a sense of how important uncertainties are versus just coming up with answers for the customers?
Yeah, that's a good question. I guess I'll answer first. I have the mic. I think I've noticed, like, just in the 5 years I've been at Tomorrow, we have shifted from kind of at the beginning super deterministic, like do this or don't do this. Now we're really focused on ensembles, on probabilistic output for everything. So all of our nowcasting, for example, that we use is probabilistic output. So that allows users to say, not just, is it going to hit 2 millimeters an hour? I need to stop my car race. It's what's the actual probability of exceeding this threshold? and then based on that, trying to, assess risk, which is such a buzzword. But so we really try to lean into that with both our kind of, I guess, enterprise offerings, but then also our data buys. So, the satellite data that we produce, like the level 2 stuff I was showing yesterday, those are all like quantile regressions. So we can actually like spit out a posterior distribution and not just a deterministic answer. So I guess it's a very mathematical answer to your question.
Yeah, for us, I think in terms of our sort of higher level products, so one of the things we're working on is sort of line load rating. It's basically very temperature dependent. And, we're based in Colorado. We've had some major fires due to power infrastructure. California also has that issue. It's something where if you're going to reduce, or I guess increase the line load rating, you want to make sure you get it right, because the impact of getting that wrong is very, very bad. So, these kinds of uncertainties are very important in the reporting of the data, I would say.
Just to add, so in our case, our clients demand. They demand transparency in terms of data sources, but also the probabilistic models to the degree of certainty versus uncertainty. I think this is not the case for every type of clients, but insurance companies, they have their own data scientists, they have their own very capable teams, so they demand that we show what is the degree of confidence that we have in the results.
Hi, my name's Andrea Portier. I'm the applications lead for GPM, and I'm curious, I kind of want to talk about the communications side of, you all talked about the need of, or stressing that, researchers are a very important part of the equation for the development going forward for all companies. I'm curious to know how the companies actually engage across agencies to make sure they stress that need, not just that, about the data buying, but also the need for researchers, so almost at the policy higher level, if you guys have a communications component. I'm just curious if that's something that is an integral part of making sure you're advocating for researchers, again, just out of curiosity.
Yeah, that's a good question. And it gets into kind of like the making of a sausage in politics. And so, I mean, I know we have, kind of government relations folks. I talk to them about a lot of things. So they're trying to talk to agency heads, and then they also engage in lobbying firms as well. And again, that's like very opaque to me. But I think, at least from the leadership perspective, the company is interested in trying to push that narrative. So I don't have a good kind of answer for that. But I think the other part is, kind of the scientists in our company, at least, we're always trying to be very supportive of researchers, people who are asking for specific data sets so they can write a grant proposal, or, are trying to present on something. We're really, again, trying to embrace that kind of openness. So even if it's not from the top down, maybe it's from the bottom up of like, look what we can actually do with this, help fund both sides of that, the people that are doing the science and the people that are providing the data.
Yeah, I would say from the top level, I maybe don't have a good insight, but I think from the bottom level, we do collaborate a lot with NASA, the military, researchers on the hardware. And that's the main way I see it sort of getting transferred. As far as discussing with leadership, I guess I haven't seen it personally.
Yeah, I think it's very nice discussions we are hearing. I just want to get summarized a little bit, like a few things that I'm, get everything I'm hearing. Number one is like, if you can tell a little bit about like your first question, that introductory wise, this is the company, how many people works, when it has been established, has been growing or about to study in terms of your applications. Number one, I think seems like I am the data producer, and my maybe objective is mostly government sector who purchase the data is one end of the story, and the other end of the story seems like you are providing some maybe product and output to the end of users. I heard 4 of them so far. I'm just trying to summarize everything. One, I heard about airline industry. Second, I heard about insurance industry. Third, I heard about maybe energy sector, like a power outages. Fourth, I heard about the agricultural, the thing. So if we get through, like, if you have a pie chart in your mind of your company, how much you put in the effort to the data providing to the, say, sectors like government or NASA, how much you are really, if you look at your annual income and based on that maybe is the private sector and which are the 4 categories. Try to summarize everything in a more, cohesive way that I'm looking for rather than, a lot of things going on individually. Thank you.
Yeah, I can go first. So WeatherStream, we were founded in 2015 out of Center for Environmental Technology at CU Boulder to build the GEMS 1 mission. So this is the first commercial microwave sounder that was really launched. And yes, so our mission from the beginning has really been to increase revisit rates. It's been, I'll say, a bumpy road. Right now, I think our focus is like 80% the government customer, 20% the enterprise. It's just more traction on the government side. It's in the past, right, with the DoD funding and whatnot. Company size, I think we're up to around 25 employees here at WeatherStream. I think I got all the points there.
We've been around for 24 years. We're around 65 large, which is a nice and comfortable size for us. So we do professional services, right? So we don't have a product. So we built the technology, and we're usually one layer removed from the end user, right? So we work with other organizations that, that are operating within a particular domain. Or we work with large data providers, and we build sort of the technology layer, the connective tissue, and it allows data to go from we usually start with level 2 products, right? But then all the way down to the user, so no domains. How we tend to divvy up our organization, it's a little bit more in technology area. I would say 60%, we're really thinking about data storage and distribution, so cloud-native geospatial data. I would say around 20–30% it's ML, AI, and then, I don't know what's left. What did I say, 60–20? So another 20% product development, which, by the way, these days is a lot in sort of building agentic and LLM-type interfaces, which we didn't get into it, but I think if we talk about data to impact, we do think that there's a lot of potential there. So yeah, I hope that covered most of your questions.
Yeah, this is a good quiz. So Tomorrow.io was founded about a decade ago, as Climacell was the previous name. The employee count, I would say, is about 150. We've actually been growing a bit as of late. I think, so until about 5 years ago, space wasn't like even an idea. I think some of the early ideas were using like basically cell phone attenuation to try and have like ground precipitation estimates, and that didn't work out very well. But up until that 5 year ago mark, it was 100% enterprise. So I don't know how the industry, like sector versus sector, was laid out, but it was all kind of that enterprise offering platform, insights and such. And then 5 years ago, when we decided to start launching satellites, that shifted slowly. I honestly don't know the breakdown of enterprise versus government. I would say enterprise still is the majority. Whether that's like 50 or 80 or 90%, I don't know. But really, that's our bread and butter funding that sustains and helps us kind of invest in this space program.
I started my first business in Africa in 2014, in Luanda, Angola. And so I saw in firsthand the impacts that flash floods had in the city and its buildings. And this was what made me start Owl Places, to bring this knowledge to the construction sector. And in 2020 we created the company, and we have been working with support, of course, from the European Space Agency and among other entities. We are very small, we are 3 full-time, but we are also very proud, so we achieved net profit in 2024, 2025, again this year probably. So we have very good numbers and we are lean. And more than that, so our projects, we involve and we pay, for example, we received from Eurostars funding, and we are paying with Owl Places AI. It's called the co-funded project, it has our name, so we are consortium leaders, and we are paying for more than 10 people. So I think this is a very interesting message to convey that more than leanness or more than profitable businesses is how you transfer the value to the society. And of course, the markets are very distinct. So the Portuguese market is very different from for example, the United States market. And we have to adjust to what we have. That being said, I think this is very important also in the terms of the collaboration that we spoke before, so the academia, the public and private institutions. We would not be possible to exist and to have profit without public funding, point. On the other way around, we never work with governmental agencies, so the client is always private. So this is a sign that the market needs the data, and also a sign that companies need the support to at least to fund the early stages.
So I think I have a question. So in the next 2 years, what technology are you more excited about in your own organizations? But not just excitement, what do you think that new technology or solution will unlock in terms of either a new market or different types of users that you're currently not being able to serve?
In our case, I would definitely say real time. So in our case, we see that the upstream business is experimenting a lot with real time, even network between satellites. And we see this with very good eyes. Of course, this will not reach us because, as everyone knows, it's very hard to implement at scale at this moment right now. But it's very good that we are seeing some very positive experiments in this sense. And from our side, also real time with AI. So we are working with the real-time planners, the agents as real-time planners, and we see very confident results that we can achieve a good degree of action plans. Of course, we will not substitute architects, engineers, but in the sense that we are achieving 10 times faster a very good briefing or a very good plan to start the work, and this will ease again the climate resilience, because in many cases what is necessary is to join a bunch of professionals to look at a portfolio that can have, for example, 8,000 assets. It's impossible to have a plan, an action plan to achieve climate resilience for 8,000 assets. So I think the technology, especially AI agents in this case, is a great starting point.
Yeah, I think real-time use as well is kind of my thing I'm looking forward to most in the next 2 years. NOAA has been doing a couple of evaluations of our data, but hasn't yet, I guess, sealed the deal on, operational ingest that has basically unlimited distribution to end users. So I think being able to see that in real time, see our data going into the models, being assimilated, seeing our data go into publicly available hurricane intensity estimates or tropical storm intensity estimates, that to me is probably one of the most exciting things, because right now there's just a couple of us at the company that see this in real time and make kind of our own internal plots, but actually like being able to see that publicly released and have that impact, I think is really exciting. And then I think the evolution of AI is, sorry to steal your answers. The evolution of AI just, you know, I had a slide in my talk yesterday I just completely skipped over, but it's kind of amazing what we can do and what it unlocks, not to replace us, but really to enable us and increase what we can do as scientists. So, you know, I've been excited of turning 4-day kind of coding, they're almost typing exercises into like an hour, and then being able to get back to doing science. That for me is super exciting.
Yeah, just hinted to it. So I think on the LLM agentic side, I think obviously there's a lot of hype, but I think we're also doing a lot of work to get some real value out of it. And especially I think on that last mile on making complex data more accessible to people, I think there's some real potential. So at Development Seed, we've been building you know, interfaces that put data into the hands of, you know, a policymaker or the decision maker for you know, well over a decade. And that process starts with, okay, what's the user intent? What does the user want, right? And we have a little bit of a process for that with user interviews, etc. But then at some point, in the design process, in designing this interface, we're making a lot of choices and design choices that constrain how the user are going to be able to interact with this data, right? So we make a lot of, and I think the LLM agentic systems which are systems that are really good at understanding user intent, allow us to really approach this quite differently, right? So I think with the newer systems that we're building for organizations like the World Resource Institute or for ECMWF, you know, yeah, the user interaction really changes, right? So for ECMWF, we've been working on an assistant on destiny data, right? Where right now somebody could say, okay, I have a piece of land in the north of Portugal. I'm thinking of growing grapes, right? I want to do a vineyard, but you know, what data sets should I be looking at, right? To understanding future growth conditions, right? This agent is able to understand, okay, automatically, okay, well, you must be in climate zone X, right? So you must care about, and you want to grow grapes, okay, you care about mildew, right? So, oh, if you care about mildew, you really should be looking at these data sets. And it's not trying to generate anything, right? It's not trying to come up with results. So the generative portion of this, with these type of partners, we don't really, you know, try to make up data. It's really about pointing people to the right place and understand what data products to use. And I think that already is very, very valuable, right? In a place that has so many different data sets and so many different things available. Being able to point people in the right direction, I think, is already very useful. And I think another anecdote of when we were building Global Nature Watch for the World Resource Institute. I think so. When we built this, the very first version, we built this, and Global Nature Watch sent, or WRI sent this out to sort of partners on the ground, and they sent it to a couple of partners in Peru. And we had not tested this thing. We had not even thought about, you know, testing this in any other language than English, because it was sort of an early prototype. But they sent it out to a partner in Peru who started talking to this thing in Spanish, and it gave, you know, gave answers. And I think that's really powerful, right? If you want to lower the barrier of access to sort of complex data, I think, yeah, there's some real value with it's not just hype, right? I think there's some real value in these type of tooling.
Cool. I think one of the things that really has me excited is just the evolution of the space sector. So like when we started, you know, we were launching these tiny 3U CubeSat, which, you know, it had some performance issues because of, you know, the limits of the technology. But things have just been evolving so much in the space sector. You know, we have these real-time optical crosslinks. We have these ride-share opportunities, right? So these things are bringing down the latency to basically instantaneous levels if you're on one of these platforms with the optical crosslink. And then the cost to launch has just come down so much, you know, it's actually getting feasible to launch some of these larger, closer to, you know, ATMS-like sensors for much lower cost. So I think that's sort of the aspect we're the most excited about.
Thank you. Other questions?
Thank you, and thank you for talking to us. I love discussions. So what I'm hearing, and this is obviously just from a few of the people that are providing data and providing products and doing this kind of interface. I work in academia and with more government side, but it seems like to me there's a lot of information, a lot of data that's being put out there. And it seems like, I guess I should say, is that a lot of it is being put out there without being evaluated. And it's being put out there and saying, you should trust this, but it hasn't been evaluated. And so it seems like companies are not putting it on themselves. They're waiting for academia, waiting for government to evaluate their products, but their products is already made available. Is that true to your extent in your practice and your companies? Or is it something that just seems like that's something from our point of view? Because it seems like a lot of stuff is not properly evaluated before it's released out. I don't know if that makes sense.
I'll just comment. So obviously we're going through CalVal right now, right? So hopefully by the time the data comes out, the data product description and all these important documents will be out, and you can all tell us how well we did in validating our data.
Good time to air a grievance. Like our sounder calibration paper has been in peer review over a year. And so part of it is it's hard for science to keep up with some of these legacy processes. So we've started leaning towards like just preprint servers. So, you know, we do a very rigorous calibration validation of our data. We just post it on archive or whatever science appropriate site it is. Then we can go through the peer review process and, you know, get our check marks and our reviewer comments that are always going to be good and bad. But yeah, that's just been something we've struggled with is trying to communicate that. So we definitely do it, and I did give a bit of an impression that we're not doing that or we're trying to lean on people. But you know, we have reports, we have ATBDs that we generate internally. We give those to agencies. They evaluate that. I know with our NASA evaluation, we got good marks on documentation. But so we're very happy to release that data. It's just that we're sometimes, hesitant's not the right word, but sometimes we don't like to just put that forward because it might seem like a used car salesman saying, you know, this is the greatest car in the world when that might not be the case.
Thank you. So you just mentioned peer review, and I am very curious to hear your thoughts about the conflict of interest with submitting a manuscript that shows that the data set that you produced is much better than IMER, GSMAP, and all the publicly available data set. Many of us serve as reviewers, editors of scientific journals, and there has been a lot of talks about many manuscripts coming to us, and many more coming to us in the near future. And we are not quite sure how to handle those. One idea that came up at one of the publication commissions meeting I was at just a few weeks ago was to invite someone representing the private sector in our publication commission so that we could hear, you know, that end of the story. But I'm just curious to know what you think about publishing, again, papers that would show a specific data set that even possibly not open access, showing, again, extremely good metrics and very low uncertainty compared to what we're used to.
I would also like to add that as a very small company, we do not have a lot of time to publish. We do have some publications, but there is also a lot of support here in Portugal, and I believe in other European countries. Also, they demand us to really communicate what we have accomplished during a certain project that is co-funded. Of course, this we do not only because we want to have our names published and revised by peers, but also because it's necessary. This is one thing. But I also think it is very important that the public organizations also have a specific budget for this, because the private entities should not be the ones that validate between themselves. I would say there is a big conflict of interest there. At this moment we are actually involved in a project with the European Space Agency, and part of our ongoing work is actually, in the end, our climate risk reporting is based in several data sources, and we want to validate that with ESA. So I think this is important for every company that wants to have defensible models.
Yeah, it's a good question, and I think, well, from the editorial side, I think as a peer reviewer or as an editor, it's holding the feet to the fire of the people at that company if they're submitting a paper, making sure it is objective, that you have quantitative facts and analysis, you have data that's released as part of the paper to back that up, as opposed to just like forged figures or whatever else that could happen. And I'm not saying that does. And then I think from our perspective, you know, sometimes it's just, like we want to publish, we have to publish. So we can't avoid the conflict of interest, but again, if we're kind of you know, kept in line, make sure that we're doing everything correctly and that we're not just bloviating, then I think, you know, that's how you do it. And then I guess the other aspect is we are always looking for academic partners who are, you know, doing validation, like the one yesterday about the Pathfinder precip products. That was great. That was great. Sorry, I'm pointing in the correct direction now. You know, that was great. And, you know, I don't know that gentleman, and I've never seen that work before. But it was an independent assessment. And I know there's another group at like Texas A&M Corpus Christi doing that. So sometimes we try to stay hands off, just so there's no even, I guess, like consideration of maybe there was some sort of whatever backroom dealing. So it's kind of a mixed bag, and I think just holding people accountable and making sure things just stick to the truth and stick to the data, that's the most important.
Yes, I know in the past we published some work on GIMS-1. The GIMS-1 sensor design was actually a PhD thesis. So the entire GIMS-1 sensor design, if you wanted to read it, there's a 150-page PhD thesis that goes into absurd detail about the antenna, simulations, etc. But similarly, I think as the CalVal starts to get into full swing here, we'll probably have people at our company going to conferences, IGARS, etc., publishing results from that, looking at double difference, etc. Obviously that, you know, as we just said, there's, you know, some potential for that to be maybe a little bit cleaned up. So obviously we want, you know, other groups, you know, I think we heard about how NASA is funding, you know, independent validations. We'd love that kind of thing on our data.
Coffee? Well, let's thank the panelists once again. It's time for coffee, right? Okay, thank you all.
Ah, yeah. Yeah. No. Just check it. Yeah, thank you.
Sorry?
This is going to be a long session.
Yeah, this one has to be a little bit more.
And perfect. Can you see my screen?
All right, welcome back. After, I hope, a lot of coffee. We are now at part 2 of the bridging models and observations session. And we start with an online presentation by Eric Peino, Trustworthiness of Satellite and Reanalysis Precipitation Products in Extreme Rainfall, Insights from Historical Data and the 2024 Valencia flood event. Go ahead, Eric.
Perfect. Good morning, everyone. I have to love to be with you in Coimbra, but instead I'm speaking to you at 6 a.m. from Miami. A bit of time of difference, but I'm very happy to be here. I'm Eric. I'm research associated at NOAA Atlantic Oceanographic and Meteorological Laboratory. And this work is a collaboration with Joan Beck from University of Barcelona. Basically, I will discuss the performance and insight of satellite and reanalysis precipitation products during the October 2024 Valencia flood event. On October 29, 2024, specifically the eastern Spanish region of Valencia experienced one of the most devastating flash flood events in Spain's recent history. The consequences were catastrophic. Extensive flooding affected the southern Valencia metropolitan area, and the event caused at least 230 fatalities and billions of euros in damage. The event was driven by an exceptional convective system that produced record-breaking rainfall rates. Specifically near Turis, an automatic weather station recorded 185 millimeters in just 1 hour, and more than 600 millimeters in 6 hours, with some locations exceeding the typical annual rainfall in less than a day. Events of this magnitude raise an important scientific question. How well do our current precipitation products capture such extreme rainfall events? Therefore, in this study, we pursued two main objectives. First, to evaluate the performance of IMER, GSMAP, and MARPI line during this event. And second, to place the Valencia 2024 flood in a historical context using the satellite record from 1998 to 2024. Moving on, the data and meteorology, our study domain covers the Iberian Peninsula with a particular focus on Spain. In the first part, we evaluate pre-gridded precipitation products, IMER version 7, GSMAP version 8, and ERA5 LAN. While they share the same spatial framework, they differ in the latency and precipitation retrieval approach. As reference observation, we combine nearly 1,000 rain gauge from 3 independent networks at hourly and daily resolution. After applying quality control, the gauge data were interpolated onto regular feed. Finally, to ensure a fair comparison, GSMAP and ERA5 LAN were resampled onto the IMER 0.1 grid, resulting in 4 datasets with the same spatial framework analysis up to daily and daily time scale. Well, let's now look at the spatial distribution of rainfall during the event. This figure shows the 24 hours accumulated precipitation on October 29th from the 4 datasets. Starting with observation in panel A, the maximum reaches 605 millimeters. However, it's important to remember that this value is already smoothed by the interpolation. And looking at the satellite product, I would like to mention that IMER correctly captured the location of the main convective core, but it strongly underestimated its magnitude with a maximum of only 188 millimeters. GSMAP show the opposite behavior, and it provides the best estimate of the peak intensity, reaching 611 millimeters, but it substantially overestimates the spatial extent of the extreme rainfall, with more than 2.5 times the observed number of extreme pixels, defined as pixels exceeding 100 millimeters in 24 hours. Finally, UFI land that show the purest performance. The maximum precipitation is below 100 millimeters with not extreme pixel detect. This indicates a complete failure to resolve the convective core due to the strong smoothing inherent to the reanalysis. The previous map shows us where the products succeed or fail. This analysis goes one step further and evaluate how well they capture the intensity of the event across time scale ranging from 1 to 24 hours. We found a parallel relationship between maximum precipitation and duration. And the slope of these curves tell us how rapidly rainfall intensity increases as the accumulation period becomes longer. For example, the observation, shown in red, represents the benchmark. Maximum precipitation increase from around 160 millimeters at 1 hour and to nearly 800 millimeters at 24 hours, showing the steepest growth among of all data sets. GSMAP shows the closest agreement but slightly underestimates. IMER shows systematic underestimation at all time scale from only 60 millimeters at 1 hour to around 160 millimeters at 24 hours. Finally, UFI land showed the weakest performance. The almost flat relationship highlights a structural inability to resolve the convective intensification that characterize event latest. Moving from spatial pattern to quantitative metrics, this figure summarizes product performance in terms of precipitation magnitude and detection skill. The scatter plots show that performance improved at the daily scale of respect to daily. GSMAP provides the best agreement with observation with a correlation of 0.72 or nearly perfect regression slope, while IMER still show a clear underestimation bias, and UFI land remain at the weakest product. The detection scores on the bottom level reveal a similar picture using Hansen's prepared score, where darker blue colors indicate better performance and the red color indicate worse performance at different thresholds. At all time scale, the skill of all products decreased rapidly as precipitation intensity increased. Again, GSMAP is the only product maintain meaningful skill for the most intense rainfall, while IMER quickly lose detection capability and UFI land almost completely fails to identify in early events. We now move to our second objective, placing the Valencia event within the historical record from 1998 to 2024. Using the same intensity duration framework, we compare the maximum precipitation extreme recorded by each dataset over the entire 26 years period. The most important result is shown by the observation in red. The October 29 event set new records between 3 and 18 hours. This confirms that the Valencia Dana was an exceptional long duration precipitation event within the observational record. Looking at the products, GSMAP consistently showed the highest historical extreme, reaching over 850 millimeters at 24 hours and suggesting an inflated upper limit of precipitation intensity. IMER systematically underestimated the historical ceiling with a maximum around 430 millimeters at 24 hours, but it exceeds the observational values at 1 hour, which is interesting. UFI land remained well below all other data sets, reaching only about 166 millimeters of 24 hours, highlighting the structural inability to capture the most extreme convecting event. We now address the key question to our second objective within the historical catalog of extreme precipitation events. How was the October 2024 Valencia donor rank? And this figure shows historical events in terms of their peak 24 hours accumulation, special concentration of extreme rainfall, and total precipitation volume, with the data highlighted in red. And UFR land completely fails to recognize the event as exceptional. The data is buried within the historical background, ranking only 24 in 26 years. GSMAP tells a very different story. The data appeared as a clear outlier, combined extreme intensity with a large volumetric footprint. It ran as the second most extreme event in the entire record, surpassed only by event in September 1999. Others provide an intermediate but still underestimated perspective with a maximum of only 188 millimeters. The data is absorbed into the clouds of historical events and runs only 47. Let me begin with three key messages. First one, the same event can have a completely different historical significance depending on the data set. Yes, not capture the intensity, but overestimate the extent. I may capture the location, but strongly dilute the peak. And UFR1 large misses the convecting extreme. And second one, well, as a extreme Mediterranean convection or extreme event in general, as many of us now remain as a major challenge for current precipitation products. The most intense short duration rainfall is precisely where this product struggles the most. Thank you very much for your attention.
Thank you, Eric. We have time for one quick question. Yeah, Daniel.
Thank you for your talk, Eric. That was really good. I just have a quick question on the IMA GSMAP side of things. So in particular, what I was really interested by is essentially they've got the same kind of satellite inputs in terms of the passive microwave and the IR. So it looks like when it comes down to differences between iMerge and GSMAP, it must be coming down to some algorithm differences. Were you able to highlight maybe why GSMAP was doing better with the extremes?
Well, sorry, I can hear very well, but I think if I understand the question, well, thanks for the comment. I would like to say that, well, the results are still quite preliminary. We are still working on understanding and interpreting this difference. But of course, yes, this is a just single case study, so we have to be cautious with the conclusion. This was a question because I don't hear good.
Okay, thank you, Eric.
All right, thanks again, Eric.
Hello?
We'll move on to the next speaker, Livia Leganes Fernandez. About a physically consistent model for precipitation particle size distributions, evaluation with hydrometer observations from the K-pop MS.
Okay, sorry.
Okay, better? Yes, okay, sorry. I'm Livia, and I work in Spain at the University of Castilla-La Mancha, and today I wanted to talk a little bit about microphysical properties modelization, because it's one of the great unknowns about precipitation science. So let's start with the definition of the drop size distribution and its relevance, right? The drop size distribution just tells us where how the sizes of the drops are distributed. Normally, there is a lot of small drops and a long tail for the larger ones, right? The important thing about this is that if we are able to actually model or measure in some sense this distribution, we are able to better understand what is happening. For example, in this figure, okay, you do not see, the dotted line would be the after, and the solid line the before. For accretion, when you have bigger drops absorbing smaller ones, you will have a change in this distribution, and it will be a clear change. So if you understand how the drop size distribution is changing, then you understand what the microphysical process you are having, or what is the motive for this change, right? So this will obviously lead us to a better parameterization of clouds in models, because the drop size distribution is widely used in models. And we will have a better link between macroscopic measurements and microphysical process, because the thing, right, is that we cannot measure really the microphysical aspect as good as we want. So all the thing is to match the macrophysicals with the macro observation with the microphysical process, right? So there is one thing that is subtle but important in the modeling of the drop size distribution, is that not any function is suitable for the job. You have to use a probability density function, because if not, you cannot assess or use probability theory or apply it well, and mathematical constructs appear. What do I mean with this? For a function to be a probability density function, you need to follow the Kolmogorov axioms, which are fairly easy, like non-negativity, the normalization of the probabilities, and that the probability of finding a drop with diameter 1 and 2 is the same, like of finding the two of them separated and just summing up, right? And when you do not follow this axiom, then you end up with models that introduce mathematical constructs that maybe thinks us that the mean diameters is below 0, which is not great when you want to put it inside a model, right? Because the models are drained by the elemental equations, and you do not want to implement physical characteristics into it, right? The reason why this happened is not because people do not care about this, obviously, it's because the difficulty of measurements, this kind of thing, right? So historically, there has been a lot of attempt of matching the radar observations, the reflectivity, water content, etc., with this distribution. So with the history of it, we have made some assumptions or whatever that are not precise, but it was what we had in that moment, of course. So there is a lot of ways of modeling the drop size distribution. Right here is a functional form of the gamma distribution, which is fairly accepted as the most accurate one, because Ulbricht in the 80s, if I'm not wrong, demonstrated that it actually represents really well the natural variability, right? So this is one of the many functional forms that you can use, and that is widely used, right? So here we have two parameters that are the the real problem to find, right? That is the scale and shape of the distribution. Here, as you see, we have a first equation that is just the distribution, and then we have the same equation but multiplied by NT, which is the total drop number or particle number, depending of what we're seeing, right? And this is subtle but important because a lot of the modeling that has been done actually embedded the total number of drops inside the shape of the distribution. And this actually results in not following the mathematical constraints, and then we have the artifacts that I was talking about. There are a lot of ways of actually retrieving these parameters. Most popular is, for example, maximum likelihood, which is just tell you the parameters that better represent the data points that you are using. But I think the most used one is the methods of moments. When you use the moments of the distribution, such as the mean, the kurtosis, the skewness, or whatever, to the measurements that you have. Why do we do this? Because the higher moments of the distribution are related to the observables, like reflectivity or the water content. So here we have the double moment normalized drop size distribution, which is an inheritance of test-tooth error. But here what we have is, instead of one gamma distribution, is a combination of two of them, and we use two moments, M1 and MJ, like whichever moments you want. And in this modelization, we use N0, which will be an intercept parameter, and the M, which is like the mean diameter, right? And in this kind of modelization, the thing I told you about mixing the scale of the distribution with the shape is done, right? So in this work, what we did is compare three models of the drop size distribution. The first one was the reference, that is the Bringy model moment, which is the formulas that I showed you earlier, but with the moment 3 and 6. Then we did a model 1 that was a variation in which we took the total number of drop explicitly in the model, and then a model 2 that was completely new, and we follow strictly the axioms that I was telling you about, and the total number of drops is completely separated by mathematical construct. So, of course, the theory is well, but we have to actually compare it to something. So we use the K-pop MS campaign with 10 years of 1 season, 1 minute DSD measured by disdrometers in South Korea. This is the sites and the paper where you can learn more about this campaign, which was really cool and have a lot of really useful data for this kind of science, so I really recommend to check it. And then the evaluation was done using the standard statistical methods that we always talk about, like correlation or whatever. And also, it's really used the Kolmorogov-Smirnov matrix, which compares the cumulative drop size distribution and kind of measure the maximum distance between them. The bad thing about this standard matrix is that when you have a small but significant difference, because you are seeing a cumulative kind of distribution, then you do not see this kind of differences, right? So we actually use the Weserton distance. That is just the cost to transform one distribution to the other, right? So in this first figure, we have the scatter plots of the reflectivity by the disdrometer and by each of the models that we are comparing. all three of them are pretty good, obviously. The Bringy model, or the reference model that we use, is more scattered because it has problems with the smaller drops. And when you see the representation of a single drop size distribution, you see that in some cases you will have a mean distribution diameter that is below 0, which is not ideal, as I say before. So that's why this scatter plot is more silent, if you want, but it's still really good. Like, there is a reason why it's the reference, right? It has been the standard for a long time, and it does work for operational applications. Then here we just have time series of the Weisserton distance and the Kolmorov-Smirnov statistics. And as we see, the three models works pretty well, right?
1 minute.
Oh, sorry. Then I will skip to the important part. Because of the difference of the construction of the model, the important thing is that when you construct the scale and the shape together, and you see the correlation between the parameters, there is a correlation that should not be there because it is not physical, it's just by mathematical construct. And when you do not do that, any relationship that may appear are due to these physical constraints. So what I really want to take is that while there is some relationship, of course, between the mean diameter and the width of the DSD, there is no universal DSD distribution, of course. But we should not relate the scale of the distribution with these first moments, because the same distribution shapes can have wildly different number of drops. And when we actually take this into account, the models perform better. And it's true that measuring the total number of drops is difficult by radar, and it's an ongoing work that we are doing, but when we do take this into account, it actually makes an impact. So it's such a subtle or little adjustment that has so many benefits that I think is worth making it. So that's all for me.
Thank you. Unfortunately, there's no time for questions. I encourage everyone to reach out to Livia during lunchtime.
Be happy to in the coffee break.
Yeah.
Okay.
Next speaker is Kyo-Soon Lim. He's going to talk about development and evaluation of cloud microphysics schemes using field campaign observations.
Okay, I'm Kyo-Soon Lim from Seoul National University. Today, I want to talk about development and evaluation of cloud microphysics scheme using field campaign observation. So, ICE-POP 2018 field campaign was held during the period 2017 November to 2018 March, during the which is the period of the Pyeongchang Winter Olympic Games in South Korea. So the purpose of this field campaign is to enhance the snowfall prediction of the complex terrain. During this field campaign period, there's many microphysical observations that we can use for the model development and evaluation. So we are trying to use this kind of microphysical observation to develop and evaluate our microphysical scheme. These three schemes. So first one, WDM6 scheme, is the revised version from the original one, which is included in the WRF model. In this scheme, we added the cloud ice number concentration as a prognostic variable. And this one, KDM61, which was published in GMD. In this scheme, we added the graph density as a predicted variable. So by comparing these two schemes, we can find out the effect of the predicted graph density. And this one, WDM7 scheme, we added the Hale mixing ratio as a prognostic variable based on the WDM6 scheme. So by comparing these two schemes, we can figure out the effect of the predicted Hale category in the cloud structure or precipitation. As we can see here, WDM6 scheme is superior than the WDM6 in terms of the simulation of surface precipitation. KDM6 all reduced the RMSE, but the ETS score is quite similar, but the bias is also reduced a lot in the WDM6 compared to the KDM6 compared to the WDM6. The one important thing that I would like to note here is the evaluation of the graph density and graph forward velocity relationship using these two schemes. As we can see here, the observation from the 2DBD and mask shows the high frequency of the graph density at around 300 kilogram per cubic meter, and then the forward velocity is about between 1 and 2 meters per second. But the WDM6 scheme, this one does not predict the graph density, so it does not show any variation with respect to the graph density, because it just put the fixed graph density as 500 kilogram per cubic meter. But the KDM6 scheme, which predicts the graph density, shows the quite a variable feature of the forward velocity and graph density relationship, as we can notice from the observation. But this one still has some problem, which is it just predicts the light graph density compared to the observation, but we are gonna just dig into this problem as well. But certainly, we can see in the previous slide that the KDM6 shows a much better feature of the graph density and graph forward velocity relationship compared to the observation. So here, we just compare the several cloud microphysics scheme to figure out the predicting the graph density is really helps the helps the simulate the rhyming signal. So here, this one shows the match to the around this timing. So it shows quite aggregation-like a feature. And then this one, 11 UTC matched to this one. So here, just black line shows a mask observation. So it shows the higher rhyming index, meaning the more graupel or hair-like particle. And then if it shows the less rhyming index, that means the particle is like a aggregation one. So this 14 UTC, we can see the rhyming index is getting lower again, and then the 18 UTC, the rhyming index increase again in the observation. That means just black line. So we just compare the microphysics scheme, that does not predict graph density in the upper figure, and then lower figure shows the rhyming index with a microphysics scheme that predicts graph density. So all the schemes in the upper panel does not capture this two distinct increase of the rhyming index. But if we see here, then the P3 scheme also for the DESCAM beam scheme, which also predicts the graphite density, pretty well capture the rhyming index as seen in the mask observation. So we just keep testing these three schemes. By comparing these two, we can figure out the effect of the predicting graphite density, and also if we compare these two, WDM6 and KDM7, WDM7, then we can figure out the effect of adding hay categories. So we tested several cases during summer and winter, and also for the hay cases. And then I'm going to show some representative cases, such as W1 case, WL2, and H2 case. So by adding hay category, WDM7 presents too strong reflectivity, as we can see here. And also, these two schemes, WDM6 and WDM7, it just produce too steep slope. That means grows, small ice crystal grows too fast in the upper level. But the KDM6 shows quite more slower growth of the ice crystal to precipitating particle that is more closer to the observation. Also, KDM6, by predicting the graphite density, it shows more closer observed bright band signature, as we can see here for W1 case and WL2 case. So the CFED, as I can show you previously, the KDM6 is much superior than the other two schemes, WDM6 and WDM7. But if we look at more detail for the surface precipitation skill scores, then the KDM6 shows quite similar skill scores for the surface precipitation. So maybe some artifact parameter inside of the cloud microphysics can affect this kind of result, I think. So this one, KDM6, that I show you today, it performs better than the previous one, and this one predicts graphite density. This one was adopted as operational uses in Korea Meteorological Administration and Korea Air Force. So we just appreciate a lot for the field campaign observation, which was provided by Professor Gyuwon Lee's group. So I'm going to leave my summary here. So that's all for my presentation. Thank you.
Thank you very much. Are there questions? All right. Seeing none, we'll move on to the next speaker, who is remote, and provided a recorded presentation about NOAA's Precipitation Prediction Grand Challenge initiative in support of GPACs, progress, contributions, and future opportunities.
Thank the organizer to give me the opportunity to present a pre-recorded presentation. So my talk is about NOAA's Precipitation Prediction Grand Challenge, PPGC. I'm one of the co-leads of NOAA PPGC initiative. First, I'd like to give you an overview about this PPGC initiative. Then I will talk about ongoing and planned activities. I will focus on the activities relevant to this session regarding bridging models and observations for the improvement. So this slide shows the urgent need to accelerate improvement in precipitation forecast. As you can see from those two graphics, those show the U.S. official forecast field scores. On the top left is the weather times forecast, about 1 to 3 days. On the right is the seasonal forecast field for the last 20-some years. So you can see the improvement rate has been very slow. So with that motivation, NOAA several years ago developed this PBGC initiative. The idea is to leverage, align all the capabilities and the resources across NOAA and also across observations, research, model development, and to improve the precipitation forecast from weather time scale to seasonal forecast scale. So with the base funding from NOAA labs and the centers, and also from the grants funding from my office, and also we also got some supplemental funding from Congress. We have supported a lot of activity, PBGC activities. Today for this session, I will focus on some examples on the research side, and also how we analyze observations, and also model improvement, including data simulation. So first of all, NOAA the UFS system provides numerical guidance for official weather and the seasonal forecast. So NOAA UFS has benefited substantial updates from various research outcomes, including model physics update, coupling to dynamic ocean ice, and increased resolution. So shown in this slide, you can see the improvement in MGL simulation and also reduced precipitation bias with all those model improvement and the resolution. And also this slide shows how those observation data collected in field campaign has been used for model improvement. So our office, in collaboration with other U.S. agencies, supported one field campaign called Atomic in 2020 in the tropic Atlantic. These are the coordinated ASC observations of trade wind shallow convection. After we collected the observations, NOAA scientists have used those atomic observation to drive UFS single column model experiment and try to diagnose the model biases in UFS, and also to improve UFS physics to evaluate the simulation. So this is just one example how process level field can, like intensive observation field campaign can enable model evaluation and improvement. So currently, my office, the specific program is called CDP, Climate Variability and Predictability Program, has planned to have conduct another field campaign called TPAX, which stands for TPOS, Equatorial Pacific Experiment. We feel this is a major contribution to GPAX. This session, I think, is more about like is the GPEX is the global precipitation experiment. It's a WCRP lighthouse activity. So this TPEX field campaign builds on NOAA's long history of tropical research. So as I mentioned earlier, we supported Atomic and many other field campaigns. So this field campaign has two components. One is in the Pacific Central area, another is in the Pacific East. Because we believe, and the science would indicate that what happened in the tropics will impact the precipitation extremes in U.S. and globally. So the field campaigns try to understand the ocean atmosphere processes in the tropic Pacific and try to address the model errors in global model, the systematic error in global model. And also, several years before we plan to support this TPEX field campaign, we also support TPEX pre-field modeling studies. The purpose is to try to inform and optimize TPEX field campaign design strategy, where to put the experiments to maximize the benefit by diagnose model biases and testing different options. And okay, so this is about model improvement and the collecting intensive observations. The PBGC initiative also supports studies to best utilize existing observations and the long-term observations. For example, we try to extend the long-term precipitation record and reconstruct and fill the gaps and quantify uncertainty, and also try to integrate satellite data, gauge data, and also other in-situ data. We also support activity to synthesize and analyze the past field campaign data. So those are the ongoing effort. And last year we got another set of another funding from Congress, the $21 million. We have used this money to support research area in different kind of research area, from research to modeling to product development and user engagement. And this funding will be for the fiscal year 2025 and 26. So those are just funded. We are going to be busy doing those research, and we're happy to share those results in the 1 or 2 years with you. Yeah, that's just a very quick show of the NOAA PBGC effort, and we feel with all the coordinated effort and additional funding, I think the PBGC is a historic research to operation transition opportunity to accelerate improvement of precipitation prediction skills. And PBGC, by aligning all the capabilities and the resources across NOAA, is NOAA's contribution to WCRP GPEX effort. And so I just present some activities, and if you are relevant to this session, if you have questions, please send me an email listed here. Yeah, thank you, and hope you have a successful conference.
All right, as you might have gathered, she's not available for questions at the moment, but hopefully you saw her email on the bottom of the slide. And we'll move on to the next speaker. Here it is, Yu-Won Lee, speaking about a long-term high-resolution precipitation data set over South Korea based on dynamically updated bias correction and adaptive residual radar gauge merging.
Thank you. So today I will talk about how we can combine the radar data with the rain gauge information to get the high resolution precipitation data set. In here, the high resolution means in terms of space, 100 meter or less than 1 kilometer resolution, and in time it's a few minute resolution. Okay, so as you know, when you talk about the multi-scale high-resolution precipitation product, we can use rain gauge as well as radar and satellite precipitation product. Rain gauge is the most accurate, but it suffers with low temporal and spatial resolution. And on the other hand, radar and satellite has a pretty good high resolution in space and time, but they are less accurate. In particular, so the satellite has the least accuracy in terms of precipitation product. Our ultimate goal is how we can combine all this information to get very accurate precipitation information. So in this talk, I will more focus on these two products, rain gauge and the radar product, combining two products to get the high resolution information. So these are our analysis domain, the Korean Peninsula. So the gray color here shown the radar coverage with 11 radar, dual parametric. And the right-hand side, you see the rain gauge from the AWS and ASOS observation. So we try to get the rainfall information at 500 meter resolution, but like in the Seoul metropolitan area, we can get the data at 100 meter resolution. And temporal resolution, we will generate data at the 10-minute resolution, but these are limited with gauge accuracy. So most of like 70 and 80% of rain gauge are tipping buckets there. But if we have the rain gauge, we can actually improve this temporal resolution since rain gauge has much better accuracy compared with the tipping bucket. And then we use radar data. So that has generated with the radar composite we call the hybrid surface rainfall map. And we use the gauge from the ASOS and AWS. The period is 9 years from the 2016. So methodology, we do the pre-processing for the gauge data for the basic data quality control. And that generates a 10-minute average rainfall intensity from the 1-minute data set. And then the radar, we do the dual parametric quality control algorithm, and then we generate the HSR image every 5 minutes. HSR is the so-called, we get the data, 2D radar data at the lowest observable height. And then we have two methods. One is bias correction in the radar data. So we use the exponentially weighted moving average suggested by the Hunter in 1986. And that the bias actually defined with the ratio between gauge and radar. And then for the spatial average, spatial interpolation, we use the radial basis function for the residue of precipitation between gauge and bias adjusted radar product. And then in the interpolation, we use the radial basis function. So with the exponential structure function, and then the W is the weighting function that derived every real time, so every 10 minutes. And then finally, we add this interpolated residual product with the bias-corrected radar product. So I will show an example. So the right-hand side is a gauge observation at each site. You see the heavy precipitation over the Seoul metropolitan area. If you apply the radial basis function to do the interpolation, you see the smoothed feature. So one of the biggest issues is gauge interpolation is you smooth out the entire field and then you cannot get any extreme value. So I will show the cross-validation later. And then these are radar data. It has a very good spatial structure, but the problem is underestimation. So the accuracy is pretty low. So what we did, we applied the bias correction for the radar product. So now the precipitation for the entire area actually improved, so or less the underestimated. And then finally, we generated the merged product of radar and gauges with we call the RRBF. So if you look at this area, so precipitation is much higher than the radar itself, and also it has a very detailed spatial structure. In particular, if you look at the radar product, bias-corrected radar product here around this area and around this area, it doesn't see the extreme value. But if you look at the final product, you have extreme, the yellowish color here and here too. So there is an advantage actually having a special structure as well as extreme value in terms of precipitation. So the next slide is a quantitative evaluation in terms of independent cross-validation. So for the gauge product, so you see the underestimation. So it's a leave one out cross-validation and the gauge true value. So in general, the gauge interpolated product always underestimate. And also you see some quantization issue. This is a validation for the 10-minute average rainfall intensity. And then if you look at the radar product, so still even more underestimation. This is linked with the radar rainfall estimation algorithm as well as radar under-calibration. So there is some issue with the radar, the calibration issue there too. But if you do the bias correction, so those bias actually reduced to almost 9%. Before it was about 45%. So by doing just the bias correction, you have pretty good precipitation product with the radar its own. But finally, if you do the merged product, so bias actually improved. So bias become less than about 6%, and then also random error is around 38%. So this is for the statistic for the 10-minute average rainfall intensity. And how about the hourly accumulation? Now all those quantization issues with the gauge disappear. You don't see the quantization in the x-axis. But still, you see the underestimation for the gauge product, for the radar product. So this is what you are actually used to use for the precipitation validation. But if you look to the bias correction for the radar, so bias actually improved. Bias become about 3% in this case, and the random error becomes 32%. But for the final product, so bias actually much better now. So bias is almost negligible. It's about 0%. And then the random error is about 26%. So this is sort of statistics we can do by combining radar and gauge. So in particular, also look at the extreme value. So there is no significant underestimation with the merged product. And then we try to compare with existing geostatistical techniques like residual curricking and curricking with the external drift shown in this color. And the gray color is original product from gauges and radar. And our final product is dark blue here. So in terms of correlation and bias and absolute error, so the radar and gauge has lowest correlation for the 10-minute and hourly, so same. But our final product is much better than any gauge or existing geostatistical techniques. In terms of biases, so the radar and the gauge has a significant underestimation. Radar is lower than the 40% biases. And then if you look at the mean absolute error, so the new method actually has much better accuracy. And hourly accumulation, it has about 20 to 30% the random error. And then the next issue is how these error statistics actually occur for the different rainfall intensity in x-axis. So the gauge and radar product has significant underestimation as rainfall intensity increases. So it's a bad news. So rainfall increases, you have more biases in terms of percentage. That's a significant amount. For particular, gauge has about around 50% biases for the over 100%, over 100 millimeter per hour, the 10-minute average rainfall intensity. But the new product doesn't have such a dependency. Bias is around less than between 10 to 20%. And it doesn't have such a significant improvement, the increase of bias as a function of rainfall intensity. And then the random error, so radar and the gauge product has increased random error with rainfall intensity, but our final product doesn't show much the random error increase. So in particular, actually the random error decrease with the rainfall intensity increases. And then the next step is how about the error statistics in space? So this is error statistics of mean bias in gauge and radar and the different rainfall product. So gauge has underestimation. So this is 0 biases. So the gauge has slightly lower than this color. And the radar has a bluish color, means a significant underestimation. If you do the bias correction, this product actually improved close to the 0, but still it has some underestimation in this area and this southeastern area. In particular, if you look at the mountainous area here in the Jeju Island, you don't see much, the precipitation. That's due to the orographic enhancement, but that is not produced by the weather radar due to the beam blocking. But if you look at the range and gauge product, so those areas improved. For entire area, the bias is close to the 0. So this is, again, we have improved the entire statistics for the entire area. But still, you see a few points around here and there. These are linked with the radar, its own data processing problem. It has some beam blocking issue too. These are mean absolute error, random error. So you see in the gauges, so in general, it's lower, but if you look at this area and this area, it has a significantly larger gauge uncertainty. In particular, gauge has interpolated data, so in the edged area or the low density area, you don't have a good information in gauge. But radar information, you have significantly see some issue with this area and this area too. So that's coming from the radar. But the problem is in this area, we have very dense radar network in around Seoul area, but still it does not have good information due to some beam blocking due to the mountainous terrain.
1 minute. If we can get it back.
Okay. And then the bias corrected. So you see the general improvement in the random error, and final product, it has in the small least error uncertainty. So we published this one into the ESSD discussion. You can download data. So the entire data set is in Genodo, so you can use it for the training your satellite data set too. Thank you.
We have time for a very quick question. Ali?
Go on, this very nice study, excellent in the sense. Just the analogy to what in the US, that we have MRMS and the stage 4, you're kind of creating the similar type of products in over the Korean Peninsula. One of the main differences I see that in terms of the interpolation scheme. Yeah. So both MRMS and stage 4 are using inverse distance weight. Yeah. And with the, as far as I know, I asked the stage 4 guys, they are using 16-kilometer radius of influence versus MRMS using 60 to 80 kilometer radius of influence. So what will be differences you might expect with in your, bias going this algorithm versus inverse distance weight? I mean, what's your recommendation? Thank you.
So first, we optimize the exponential structure function for the Korean data set. And the second step is we actually derive a weighting in real time, every 10 minutes. So when the system structure change or error structure changes, actually W will be modified, weighting function modified in space too, all the time. So that's the difference between the IDW and our techniques.
All right, thank you. We need to move on to the next speaker, which is who is again Eric Peino, online, talking about quantifying thermodynamic and dynamical drivers of tropical cyclone rainfall and landfall. At landfall, sorry. Okay, good to go.
This talk is not related to my current work. I will focus on tropical cyclone rainfall. So, from an observational perspective, and we'll address a simple question. How does tropical cyclone rainfall change as a storm approach landfall? I'd like to start mention that tropical cyclone rainfall is one of the leading causes of cyclone-related fatalities, yet it remains one of the most difficult hazards to forecast. This is especially true near the coast, where a storm transition from ocean to land environments. And we know rainfall change around landfall, but the special pattern of those change and the process behind them are still not fully understood. To address this, we asked three simple questions. What does the special structure of tropical cyclone rainfall look like? How does it change as a storm approach and cross the coastline? And what environmental factor drive those changes? To answer this question, we analyzed 492 long-falling tropical cyclones worldwide, covering 6 ocean basins between 2001 and 2021, as shown in the figure. Each storm is classified into one of the 4 coastal phases: open ocean within 500 kilometers of land approximately, offshore, pre-landfall, and landfall. I would like to mention too that this classification is based on the storm distance from the coast, but also taking account its size and the timing relative to landfall. Let me briefly illustrate the methodology using a random time step from Hurricane Gustav in 2008. For each tropical cyclone position, we combine 4 complementary data sets: IMERGE, a rainfall observation; OISST for sea surface temperature fields and variables; IB tracks for track and intensity information; and finally, we use chips for environmental predictor. From this dataset, we characterize both the rainfall structure and the surrounding environment, including humidity, vertical wind shear, storm intensity, motion speed, ocean condition, and rainfall asymmetry. All analyses are performed in storm relative framework using pre-early records, and results are stratified by coastal and storm intensity. And this is our baseline, is the open ocean composite shown in shear relative framework. The red arrow indicates the direction of environmental vertical wind shear. And the 3 panels correspond to tropical storm, minor hurricanes, and major hurricanes. And the distances are normalized by radius. I wanted to highlight this point basically. First one, rainfall is clear asymmetry. In all intensity groups, the precipitation maximum is located in the down shear left quadrant. Second, the inner core rainfall becomes much more intense and concentrated as storm intensity increase, as we expect. Third, the outer range field becomes relatively less prominent in a stronger storm, suggesting that the precipitation organization shifts inward during the intensification. This is the central result, I think, that of the study. This panel shows the percentage change in rainfall relative to open ocean baseline, using tropical storm as an example, with a very similar pattern observed for minor hurricanes. Green indicates rainfall enhancement and brown indicates suppression, while black contours show the baseline rainfall structure and cross mark a statistical significant change. We find a clear progressive drying as storm approach land. Both the inner core and outer rain bands weaken from offshore to landfall, showing about 30% reduction in rainfall at landfall in both regions. In contrast, major hurricanes behave differently. The inner core weakens, but the outer rain bands become progressively wetter as landfall approach. In other words, rainfall is not simply reduced near the coast, it's redistributed outward. These changes are clearly not uniform across the storm. The inner core and outer rain bands respond differently, and that response depends strongly on storm intensity. So the next question is, what drives this contrasting behavior? To understand what drives this rainfall change, we create regression models for each coastal phase and apply a dominant analysis to quantify the relative importance of each predictor. On the left, I show the model includes storm intensity as a predictor, and on the right, the model without it. The height of each bar represents the total variance plane, while the color segment shows the contribution of each individual predictor. From this result, we see that SST dominates rainfall variability in general, explaining around 30 or 45% of the variance in both models. However, this dominant weaken near landfall, where vertical wind shear and asymmetry become the main controls, indicating a clear regime shift as a whole. The another thing that I wanted to mention is when intensity is removed, rainfall asymmetry emerges as a dominant predictor of variability. This is particularly interesting as it suggests that asymmetry captures information independent of a storm strength. To understand the relationship between the vertical wind shear, rainfall asymmetry, and precipitation, the rain rate, we perform a mediation analysis for each coastal phase. This allows us to test whether shear has a direct effect on rainfall or whether part of its influence is mediated through another mechanism. We find that a significant fraction of the shear, in fact, is mediated by rainfall asymmetry, particularly during pre-landfall and landfall phase, where shear effects are strongest. In other words, shear does not only affect rainfall directly, but also reshapes its special structure, which in turn contributes to the reduction of inner core precipitation. This mechanism is relatively weak over the open ocean and offshore, but this is substantially as a storm approach land, where asymmetry accounts for probably 40–50% of the total shear effects. Overall, the picture that emerged is that near the coast, increasing shear both suppress convection directly and recognize rainfall in a way that further reduces inner core precipitation. While vertical wind shear suppress rainfall as a storm approach land, SST shows the opposite behavior during the kind of phases. The effect is substantial, comparing the coldest and warmest SST environment. Tropical storm and minor hurricanes can experience rainfall increase of more than 140% during pre-landfall phase, with a strong positive correlation. Using quantum regression, as I showed you here, we further see that SST influence trends toward the upper scale of the rainfall distribution. Sensitivity is most higher at 90 percentile than at the median, particularly during pre-landfall conditions. In other words, warming oceans do not just increase mean rainfall, they preferentially amplify the most extreme events. And importantly, this amplification is largely independent of storm intensity, as the result remain almost intense when intensity is included or excluded from the model. I want to mention two main conclusions. First one is that coastal approach suppress rainfall in weaker systems, while major hurricanes mainly reorganize it, drying the inner core and enhancing outer bands. The second one is higher shear near landfall amplifies rainfall asymmetry and reduce rain rates with about half of the effect mediated through structural change. And third one is that the SST is the dominant thermodynamic control, preferentially amplifying extreme independently of storm intensity. Looking ahead, the next question is which combination of shear, SST, and intensity produce the most extreme rainfall change on landfall, and this has direct implication for flood forecasting and operational prediction. This is all. Thank you so much for your attention.
We have time for questions. Any questions? Okay. Thank you, Eric. We'll move on to the next speaker, Miguel Lima.
Sorry, I can hear very well. Okay. Sorry, I'm going to stop sharing.
Miguel is going to talk about low latitude blocking drives southern hemisphere precipitation redistribution.
Good morning, everyone. My name is Miguel Lima. I know it's getting near lunchtime, so I'll try to be fast. The presentation I'm going to do here today will be a bit different from what you are seeing. So I'm more worried about the drivers leading to precipitation that affects the distribution of climatological precipitation or the extremes. And in this case, I will be talking about how low latitude blocking drives redistribution of rain in the southern hemisphere. I know most of you have a meteorological background, but just to summarize here, these low latitude blockings are obstructions to the westerly flow in the atmosphere. For example, right here, we have an example of an omega block and its impacts on the summer months in Europe. So for example, in the middle, we have a heat dome, and in the flanks, we may have extreme precipitation, thunderstorms, sometimes even hail or tornadoes. The first step of my PhD was to identify these structures in a systematic way, and that's exactly what we've done. In the University of Lisbon, we've had a tradition of studying atmospheric blocking since the 60s, so very early on. And now it was my turn. I developed this software, which is available on GitHub as an open source software that identifies these structures in climate data. And this is based on a conceptual model that we have. So we start the meander of the jet stream, and we call it subtropical ridges. And as it evolves, we have omega blocks and rect blocks, and so on. As you saw, my interest is in the southern hemisphere, not on the northern hemisphere. These structures are mainly studied in the northern hemisphere due to their presence. Most days, we have an atmospheric blocking somewhere around the northern hemisphere, but in the southern hemisphere, the picture is slightly different. Right here, you can see the distribution of atmospheric blockings in the southern hemisphere, and as you can see, we have two main types of blockings. We have the low latitude ones, which are composed of the ridges, omegas, and hybrids, and then we have the high latitude ones. I'm not going to go into depth on those high latitude ones because they are very complicated, and it's honestly a bit of a mess. For the low latitude blocks, however, I'm very interested in those. As you can see, their frequency tops at around 15% of days. Much, much different from the northern hemisphere side of things. And for example, near South Africa, we have regions where we have about 3% of days with these structures. This is very little, and you may wonder, why is this guy interested in this? Because these little amount of days are very strong impacts on precipitation and can create very strong extremes. One of these cases, which is what actually motivated me for this work, was in 2024. And as you can see in these pictures, this was one of the greatest disasters in Brazil's history. It was the Rio Grande do Sul floods in May of 2024, so right at the end of the spring months. And as you can see, on the right, you have the precipitation distribution. Right here is the coast of Brazil. You can see the mouse. But yeah, it's the coast of Brazil. We have a southern state, so Rio Grande do Sul. And then you also have Uruguay. And over that entire region, which is more or less the size of Portugal and Spain, so a big region, you can see that we have a region where we have an exceedance of 4 standard deviations of anomalous precipitation. So we are talking here about the extremes of the extreme, so very rare events. And in the figure below, something we noticed when we were looking at the weather maps for those days, we noticed that there was a very persistent structure that was occurring in the Pacific. And you may wonder, well, this is very far away. What is the connection here? Well, in fact, there is a connection. When we looked at this weather map, and we looked at many more variables, for the sake of time, I'm not showing them. But we have a much stronger South American low-level jet, which is carrying vapor from the Amazon towards the coast. We also have some structures that come from the Atlantic that cause that water vapor to precipitate. And what we have is, if this advances, okay. What we have is a map like we have here. So this is the composite image when we have Pacific ridges. This is the map of South America. So I don't know if you can see it very well, but we have like dashed lines which indicate significance. And for the drier regions in southern Chile, we have dots for significance. And as you can see, there are 2 major spots, one in southern Brazil and one in southern Chile, one creating a wetting pattern and one creating a drying pattern. And this was very consistent across these days, so we have these significant regions. And we've done this by sector. Okay. We have done this by sector, so we analyzed many sectors. And we see, well, obviously, we noticed that as we get closer to land, we have more impacts on precipitation. This is the case for South America. For South Africa and the Oceania, the case was not as clean as this one. As you can see, the presence of landmass over these regions is very little. So we have more teleconnection-like patterns. Also, it is worth saying that atmospheric blockings are a wave train. So while one is present near the Pacific, there's also another structure maybe in the Atlantic. So also worth taking into consideration. Again, for the sake of time, I'm not showing the analysis for the other regions, but we've selected some sectors in specific, if this advances. Okay. And right here, you can see these figures for the 3 main land masses, and you can see the evolution for South America, for example. Let's focus on that. We see the same pattern below, so on the left below, the same wetting and drying pattern, and as the blocking evolves into the Atlantic, because these are slowly moving structures, the pattern slightly changes. And we compared these with some case studies, and it was consistent with, for example, in Chile, check figure D, so on the top, we have a wetting pattern. This is consistent with atmospheric rivers reaching Chile. And what we saw was that, for example, atmospheric blocking was one of the responsible drivers for the mega drought kind of stalling 2 years ago. Another example, and let's zoom in on South Africa right here. This is the case when we have blockings in the middle of the Indian Ocean. And like I said, that this is a wave train kind of thing. And there is a very small blob of extreme precipitation that is noted in the Western Cape region. And again, this might seem like a very small thing, but we identified more than 20 case studies where a block in the Indian Ocean was causing floods in the Western Cape region, which is home for 4 million people. So it is not something we can ignore. And to better understand these patterns, we've done some composite analysis on, in this case, I'm just showing you 3 variables to keep things simple. From left to the right, we have geopotential, which, well, just indicates as the shape of the main ridge. So these are pseudo coordinates. This is centered on the average ridge. And we can notice that ridge kind of pattern. And what this implies to the other variables. So for outgoing long wave radiation, which is not as obvious, we have an increment of convection in the equator side of the ridges. And this actually I found this out by accident. Then I was looking at papers and I found out that this has been studied since the 70s by Hoskins. What wasn't studied was the connection with precipitation. And we found out that a part of this precipitation is caused by an increase in convection by the existence of blockings. Whether it's convection creating the blockings or the blockings creating convection, that's the part we don't know. For large scale, and it's the part that's much more studied, we looked at integrated vapor transport, IVT, and we saw that the poleward side of the ridge actually has an increment of this water vapor transport, which was a bit obvious for us. But when we looked at the quality of these composites, what wasn't so obvious was that geopotential was very good, OLR was very good, and right here we attested the quality with just the coefficient of determination. But IVT was kind of bad. So we needed to look into these things case by case, and we did this analysis. Again, you can talk to me later. I can show you some figures on that. But yeah, so just to summarize, we mapped these entire impacts for these specific sectors, for the 3 land masses. These hadn't been done before for either hemisphere, actually. And we began to make this tropical mid-latitude connection, which we hope to continue in the next months. Finally, this figure from Jimeno et al. Just shows the main drivers that affect water vapor transport in the southern, actually for the whole world. I'm just focused on the southern hemisphere. And my main aim for my PhD is to include ridges and blockings as one of those drivers, because these are the least the worst represented in the models. So it is where we have to improve. And that's it. Thank you.
All right, I see already a question.
Thank you, Miguel, for your presentation. I strongly recommend you look in the subtropical easterly jet for the case of South America. Mm-hmm. You actually found something in the equator side of the upper level jet, actually. You have something called transverse agiostrophic circulation that increase convection at particular site, and you have the mesoscale convective complex create this kind of pattern there. This is we know this since the 80s, okay? So it's something you should look at. I don't know if you actually...
It is something we hope to do in the next months, because we want to do this quantitative analysis. We also want to include some MJO analysis into this. Actually, we have done it. But we also need to include some metrics on what you just said, and also on the South American low-level jet.
Yeah, so do you have the upper-level jet and low-level jet interaction, actually?
Yeah, and it's actually that complex interaction that lowers the significance of the connection between convection and blocking, specifically in South America.
Okay.
For South Africa and in the maritime continent, this relationship is much more clear.
Okay.
Yeah.
Thank you.
Thank you, Anna.
All right. I guess we can move to the last speaker.
Thank you.
Kuo Sen Kuo, talking about precipitation's role in the 2017 Oroville Dam crisis.
It's the same deal.
Yeah. Now you really stand between us and lunch. No pressure.
Precipitation, particularly its phase, in the 2017 Oroville Dam crisis. This will be presented by Kuo Sen Kuo. Oroville Dam is an earth-fill embankment dam on the Feather River, east of the city of Oroville, California, in the Sierra Nevada foothills east of the Sacramento Valley. At 235 meters high, It is the tallest dam in the US and serves primarily as a water supply. We will show an animation that provides a background to the Oroville Dam crisis. Next, we will show an animation of the large-scale context of winter 2017 in the Eastern Pacific, west of California. It includes extratropical cyclones, potential atmospheric rivers, and precipitation. We follow it with an animation that focuses on the Sierra Nevada and the 2017 California floods. We then dive into a more detailed analysis, showing daily watershed averages of snow depth, snowmelt runoff, snowpack temperature, and snow water equivalent. Finally, we accentuate the role of the precipitation phase by contrasting snowmelt runoff and snowpack temperature between the Feather River and Tuolumne River watersheds. We then make some conclusions.
In February 2017, the world watched as the main spillway on one of the largest dams in the world suffered a catastrophic failure, prompting a series of events that led to the evacuation of nearly 200,000 people downstream and hundreds of millions of dollars of damage to critical water infrastructure.
The following is a one-minute history of the crisis. In early to mid-January of 2017, a series of storms causes 70 feet rise in Oroville Dam. On February 7th, as flows increased, major spillway damage was discovered. Spillway flows halted between February 7th and 10th, but resumed as runoff filled the lake. On February 11th and 12th, the emergency spillway overflowed, and the earthen base eroded. Mass evacuations were carried out on February 12th for Oroville and downriver towns. Flows increased on the main spillway. Lake level dropped. On February 13th, crews filled the eroded hillside with concrete and rocks. 2 weeks later, on February 27th, flows were halted down the main spillway to access and clean. On March 17th, 2017, the water level of Oroville Lake was lowered. Hyatt Power Plant reopened. Both spillways needed to be rebuilt. The first video will show the broader context, including extratropical cyclones, atmospheric rivers, and precipitation originating mostly in the Pacific. We will then show a second video focusing on the Sierra Domain. The Feather River watershed, where the Oroville Dam is located, is outlined in magenta. We also use the Tuolumne River watershed, outlined in gold, to contrast the Feather River watershed in our analysis. The Sierra Nevada Conservancy region, which contains the watersheds, is outlined in black. Gray shaded areas denote extratropical cyclones' spatial extents. The letter L marks the low pressure center. Triangles mark areas of enhanced integrated water vapor transport, or IVT, a characteristic of atmospheric rivers. Purple triangles indicate where IVT is greater than 500 kilograms per meter per second, whereas red triangles indicate IVT greater than 750 kilograms per meter per second. The triangles have different sizes because they are based on our innovative spatiotemporal adaptive resolution encoding, or STARE. In fact, extratropical cyclone and precipitation areal extents are also represented using STARE indices. We will talk about STARE again later. Circular dots indicate precipitation, green for rain, and white for snow.
In the interest of time, I will skip this one.
Large-scale context for now. This is an animation for the Sierra-focused domain spanning the period of the 2017 California floods from January 7th to February 22nd, 2017. In addition to extratropical cyclones, atmospheric rivers, and precipitation, we added a blue to white background to indicate snow depth. Shallower snow depth is bluer, while deeper snow depth is whiter. The source of the snow depth information is the Snow Data Assimilation System, SNODAS data product, available at daily frequency from the NOAA National Weather Service's National Operational Hydrologic Remote Sensing Center. It is noticeable, although not very obvious, that the white area of snow depth over the Feather River watershed shrank when the Oroville Dam crisis began on February 7th, coinciding with liquid rainfall brought by an atmospheric river from the warmer southwest direction. The analysis presented in the following slides requires the co-location of multiple, diverse data sets at different resolutions, for example, by subsetting MERA2 and SNODIS data for watersheds with irregular shapes. Our STAIR indices enable such co-location with native data without first reprojecting the data onto a common grid, significantly improving analysis performance. Moreover, STAIR handles swath data with the same proficiency. However, describing STAIR will require another presentation. This slide presents the analysis of 4 snow variables for the Feather River watershed. Clockwise from top left, they are snow depth in millimeter, snowmelt runoff in millimeter, snowpack temperature in degree Kelvin, snow water equivalent in millimeter. The color-shaded areas are based on 10-year statistics derived from the SNODIS data. The 10-year minimum to the 10th percentile and the 90th percentile to the 10-year maximum are shaded in peach color, whereas the 10th to 20th percentiles and the 80th to 90th percentiles are yellow. The middle 20th to 80th percentiles are shaded in green. Daily values of the snow variables will be marked by black dots and traced with red lines from day 1, December 1st, 2016, to day 90, February 28th, 2017. The green vertical hatched bars indicate the presence of atmospheric rivers over the Feather River watershed, whereas the purplish ones indicate that of extratropical cyclones. Note the drop in snow depth right before the Oroville Dam crisis. Snow depth mostly increases during the passage of atmospheric rivers or extratropical cyclones. It even broke the 10-year maximum after the start of the 2017 California floods. This slide presents the analysis of 4 snow variables for the Feather River watershed. Clockwise.
Somehow it's not running correctly because it's not running the animation. It doesn't start
This
the
slide
animation.
presents the analysis of 4 snow variables for the Feather River watershed. Clockwise from top left, they are snow depth in millimeter, snowmelt runoff in millimeter, snowpack temperature in degree Kelvin, snow water equivalent in millimeter. The color-shaded areas are based on 10-year statistics derived from the SNODIS data. The 10-year minimum to the 10th percentile and the 90th percentile to the 10-year maximum are shaded in peach color, whereas the 10th to 20th percentiles and the 80th to 90th percentiles are yellow. The middle 20th to 80th percentiles are shaded in green. Daily values of the snow variables will be marked by black dots and traced with red lines from day 1, December 1st, 2016, to day 90, February 28th, 2017. The green vertical hatched bars indicate the presence of atmospheric rivers over the Feather River watershed, whereas the purplish ones indicate that of extratropical cyclones. Note the drop in snow depth right before the Oroville Dam crisis. Snow depth mostly increases during the passage of atmospheric rivers or extratropical cyclones. It even broke the 10-year maximum after the start
I'm sorry, but the slide is running as I expected it to, and I think I have the video, and can be shared with the attendance. Somehow this is not running like it runs on my computer, so I need to quit this. And perhaps I can skip to the, and just show this one.
The temperature of a precipitation system determines its phase. Together, they played a crucial role in the Oroville Dam crisis. In the accumulation period, snowfall precipitation formed a deep snowpack in the Feather River Basin. Then, just as the snowpack temperature reached the melting point, heavy rainfall added more runoff to the system. The crisis may not have been preventable because it was difficult to predict the extremely high inflows to the reservoir, which caused record water levels and catastrophic damage to the spillway. Better prediction and monitoring may have led to earlier reservoir discharge and mitigated spillway damage. However, California had been in a 5+ year drought at the time. Fresh water must have seemed very precious. Precipitation often accompanies large-scale systems, such as extratropical cyclones and atmospheric rivers, which are generally more predictable. However, its value at the watershed level and on short time scales remains limited.
Okay, so that's my presentation, and I'm sorry for the glitch. I couldn't have anticipated that.
So I believe this morning was an email was sent to everyone with the link to the SharePoint. I'm sure we can upload the presentation there, right?
This is an animation of the large-scale context
So I will show the
from
animation that I
2017
skipped.
at half-hourly frequency, starting from December 1st, 2016. The date and time are shown in the upper left corner. Data source is NASA's MERA-2 reanalysis. Extratropical cyclones are identified based on sea level pressure. Enhanced integrated water vapor transport indicates the presence of an atmospheric river. We use connected component labeling to track the events in the 3D spatiotemporal domain, 1D in time plus 2D in space, rather than 3D, because we are dealing with surface
If you have
phenomena
questions, you
or
can ask
vertically
now.
integrated
And
quantities.
I will just
Each
let
event
the
thus
animation run.
occupies an event volume in the
All right,
3D
any
space-time.
quick question?
Only precipitations whose event volumes have an overlap with that of an atmospheric river are shown. The Oroville Dam crisis happened during
I
the
guess they can reach out
2017
during
California
lunchtime in
floods,
case.
which lasted
And
from January
yeah,
7th
feel free
to
to
February
check the
22nd,
full
2017.
presentation on the
We
SharePoint
noticed that precipitation and
after the
atmospheric
conference.
rivers occur mostly
Everything will
over
be
the edges
uploaded
of
there.
extratropical cyclones.
All right.
Please also pay attention
Thank
to the
you.
precipitation phase
We are
over the Feather
reconvening
River
at
watershed before the
1:45
start of the Oroville
with the
Dam
keynote
crisis
speaker
on February
again.
7th.
Have a good lunch.
You should have noticed that before February 7th, it was mostly snowfall in the Feather River watershed, but afterwards it was liquid rainfall.
vou ali experimentar o computador porque eu achei estranho. Aqui não sei. Aquele senhor, ele é um bocadinho complicado. É uma apresentação muito fácil. Só complica. Mas ele é assim em tudo, é curioso. É? Tudo. Já tirei até os colegas dele uma péssima apresentação. No meu entender, ignorante não, porque depois já fiz muitas apresentações nas minhas aulas. Exato, exato. Agora, aquela apresentação não era muito perceptível. Pensar na área, se calhar percebeu. Acho que não. Do ponto de vista visual, estético, da apresentação em si, eu vou-lhe fazer o teste só com uma coisa qualquer, porque eu achei estranho. Eu tinha aqui os canais abertos, estava tudo, e eu não percebia porquê.
Top of your game. Feel it, got everything you needed. Now bring it like you need it.
Hello. So we'll be starting in 1 minute. Okay, well, I hope you had a nice lunch, some time to recharge batteries. We'll be starting again with our fourth keynote speaker, Dr. Gabriel Moldovan from ECMWF. Thank you so much for presenting.
Thank you, Vasco, for inviting me and to give this keynote speech, and thanks to the organizing committee for organizing this very nice conference. So yeah, today I will be talking about data-driven weather forecasting at ECMWF and about the AIFS more specifically. So for those who don't know, the European Center for Medium-Range Weather Forecasts is an intergovernmental institution founded in the 1970s by several European countries, and its role is to basically join forces at the European scale and to tackle critical and difficult research questions, which is medium-range weather forecasting. The flagship product from IFS is our integrated forecasting system, which is a conventional physics-based model. It runs with this pipeline that we have here. We have data simulation that is used together with the observing system to get initial conditions for a model. Then these initial conditions are then fed into the actual numerical model, and then we have predictions. But traditional weather forecast codes are very expensive. They run on thousands of CPUs at the same time, so weather forecasting is actually a very expensive activity. And researchers have started to explore more and more the idea of actually, whether we can produce forecasts without an actual numerical model. And the whole idea behind it is basically, can we use analysis or reanalysis products to train an AI model to produce weather forecasts. And this is a very short history of data-driven explosion that we've seen in the past years. So in 2018, this concept of training on analysis data was explored by ECMWF and others. And at that time, it was deemed impossible. We thought that it would never happen in the next decade because the computational cost would be just too expensive. But in 2022, big tech companies just proved everyone wrong with the operation of GraphCast, FangWeather, etc. And what was really interesting was that these AI trained models demonstrated quite good skill, competitive against the IFS. Very rapidly, so the center, ECMWF realized that we cannot turn a blind eye to this. We cannot just ignore what happened, and decided to massively invest in exploring AI models, and in 2023 we already had a prototype that was basically inspired on GraphCast. And 3 years after the first apparition of GraphCast, etc., we had our first 2 operational models at the center. So in February 2025 we had the AFS single, which is a deterministic model trained on mean squared error. And then we have the second error, which is the AFS ensemble, second model, which is the AFS ensemble, which is trained on a probabilistic loss, and it produces ensemble forecasts. So this is a little bit the current pipeline of AI weather forecasting and machine learning at the CMWF. So machine learning is actually used in the entire segments of the chain. We have machine learning that is used actually in data simulation a little bit, etc. But with the AIFS, so the artificial intelligence forecasting system, is the first time that we actually completely swap, say, the physical model with the machine learning, machine learned one. So this is quite a paradigm change, I would say, because now instead of people that work on the IFS, instead of focusing on improving or modeling of the physical processes and the numerical equations that live in the model, we actually focus on getting the best data and having the best algorithms that capture or that use this data at its full potential to train better AI models. So it's quite a shift in the way we do things. So as I said before, the AFS still relies on the data simulation system of the AFS for its initial conditions. It is actually trained on ERA 5 and also on operational analysis, and currently we have 2 models that are running operationally. But let's have a look a little bit of what is going on behind the hood, so what's actually inside AFS model. So in terms of variables used in the current operational version of the AFS, the AFS v2, this is an exhaustive list of all the variables that are in there. So we have the atmospheric state that is represented at 14 pressure levels. We have different key variables that we have there. We also have external forcings such as orography, latitude, longitude, time of the sun, installation, etc. Time of the day, sorry. We have near-surface variables such as temperature, near-surface wind, and of course precipitation. The training task, to put it simply, we are trying to train a model that learns how to jump from reanalysis to reanalysis or from analysis to analysis. So this is equivalent to basically learning the data-driven approximation of the atmospheric time evolution operator, but from analysis to analysis. And then very importantly, to produce long lead time forecasts, we use the model autoregressively, so the forecast becomes the input to the model in the next time step. Currently, the time step is 6 hours, but towards the end of the year, we'll have hourly output in the operational model, or at least this is the plan. Another very important thing is the loss function. So loss function is really telling the model what you should care about. So here we have 2 options. As I said before, the deterministic version of the AFS uses regression loss, mean squared error in this case. So it's robust and easy to implement, but it produces smooth fields due to double penalty, and this is well known for everyone. We also can use probabilistic loss. In this case, the continuous rank probability score, which is harder to implement, so it's more expensive to train, but it evaluates the full predictive distribution, and this has some advantages. This is just a representation of both these losses. So while the mean squared error really focuses on minimizing forecast error, in the CRPS version of the model, here we are looking to have a community distribution function that matches the observation set. So the CRPS will be optimized when we have an ensemble that produces forecasts that are well calibrated, so we have appropriate spread and mean error. And of course, for all these losses, we need to decide on how to aggregate over variables and weights, so we need to empirically decide how much weight we put on geopotential and precipitation and to meter temperature. And this is mostly very empirical work. So this is an overlook of what I've said so far. So we have in the input, there are 5 variables or operational IFS analysis variables. We have around 30 kilometers of resolution. We're using actually more than 40 years of reanalysis data and 8 years of IFS analysis data. And we have atmospheric and surface variables plus forcings. We haven't said anything about the model so far. we have an output at t plus 6 hours, and then we have a target which is ERA 5 or IFS analysis, and we can use either mean squared error loss or CRPS loss for training our model. Maybe very rapidly, just to now have a look at what is actually inside the model and model architecture choices. We are using a graph neural network. In graph neural networks, data is represented at nodes and edges. In this implementation of the AFS, we can distinguish two representational spaces. So we have data space and we have a learned latent space. So basically the model functions in 3 steps. We have an encoding process where we encode data from the data space into the latent space. Then we have a processing phase where we actually compute, where we advance the state of the system in this latent learned space through the processor. And then we have the decoding back into the physical space. All this chain involves attention, the attention mechanism, and at the end of the prediction chain, of course, we'll compute or we'll compare against the target, which is either ERA 5 or operational IFS analysis. We'll compute a loss and we'll backpropagate, updating the model weights. So the training scheme of both AFS ensemble and AFS deterministic follows a similar training scheme. So we first have a pre-training phase where we only give ERA 5 data to the model, and we have the model to produce t plus 6 hourly data. And then we have a rollout phase, or fine-tuning rollout phase, where we use operational IFS analysis, and we ask the model to produce forecasts up to 72 hours. And in this rollout phase, we actually use the autoregressive nature of the model to produce longer lead time forecasts, up to 2 days. So that was true for the AFS deterministic and So that was true for the AFS deterministic and the probabilistic version of the AFS. I won't go into the detail, but there are 3 main changes. So for training a probabilistic model with the CRPS, we need to train an ensemble. So we have 4 model realizations. So this is the first big change. We also have noise that is actually injected into the latent space. And the third big change is, of course, the loss function. Instead of using a mean squared error, we actually use a continuous run for the score for the loss function. And if you want a little bit more details, I would recommend reading this paper. And here we see actually the real benefit of using a CRPS loss instead of a mean squared error loss for training. On the left-hand side, you have an IFS forecast, or a conventional traditional model forecast for precipitation over Europe. On the middle, you have one realization of the probabilistic model, and on the right-hand side, you have a realization of the deterministic model. So you really see that the deterministic model produces very smooth forecasting compared to the IFS-CRPS and IFS model. So the IFS and the IFS-CRPS produce much more closer forecasts. So right now, the operational configuration for both these models, which are operational since February 25 and July 2025, is the following. So we have 50 perturbed members that are started from the perturbed initial conditions of the IFS ensemble. We have one control member that is started from the unperturbed initial conditions. Well, this is technicalities about the data simulation, ensemble data simulation system. And we have 50-day forecast for each model at a resolution of around 30 kilometers, so a reduced Gaussian increase of 10 to 20, 6 hourly output, and the same for both AFS single and AFS ensemble. So now let's have a look at the skills of this model. So I don't know if any of you is familiar with this type of scorecards. So this type of scorecards is usually used to compare different model cycles, and it was used a lot in the past to compare like newer versions of the IFS, etc. So you have scores across different pressure levels. I don't think my mouth is finger, but whatever. You have scores across different pressure levels. We look at root mean square error and anomaly correlation for key variables such as geopotential, temperature, and winds in the atmosphere. You also have scores at the surface, so 2-meter temperature, 10-meter wind, and precipitation, which is really the last line. And basically, to really simplify it, here we are comparing the IFS single, so the deterministic version, against the IFS in its control forecast form. And whenever the scorecard is blue, it means that the AIFS is better than the IFS. So overall, we see that the IFS performs better than the IFS across all lead times and for really the headline scores. But again, the scores are really pointed towards larger structures, and this is actually a fair assessment. So the IFS is really better at predicting large CMT scales in comparison to the IFS. But for example, for precipitation, which is evaluated against CNOP stations, so point observations, we actually see that also the IFS manages to outperform the conventional model. So the scorecard is quite blue, and again, when it's blue, it means that it's better than the conventional model. You see some red there. It's mainly in the stratosphere, and it's quite significant. So we're still trying to understand why this happened, but it doesn't seem to impact scores, the lower levels of the atmosphere. And more or less the same story for the ensemble version of the AIFS. We see a very nice improvements over the tropics. We still have some issues with 10-meter winds, but so far the model is quite competitive against the IFS ensemble version. Now, are these models useful? Because the scorecards maybe only actually what the researchers that use them and forecasters maybe don't really care very much about them. So let's have a look at some cherry-picked examples. The IFS works very well. I really like these examples because with this really pushes back a little bit against the idea that if an AI model hasn't seen an event, it cannot really predict it. So this is, I'm sure a lot of you are familiar with this event. It's a rare snow along the Gulf Coast. That happened in 2025. January 21st. And here on the right-hand side, bottom panel, we have the reference, which will be the IFS short-range forecast or the analysis for the IFS. And we see this event that happened in the Gulf. And very interestingly, we see that the IFS, even though it did not see this event at all, because this is the first time that something like this happens in this area in more than 130 years. If my memory doesn't fail me. So we see that the model, even though he has never seen this at all, it still manages to predict this type of event, and it managed to predict it in 10 days of advance. Whereas the conventional model, well, we did see a signal 9 days in advance. So this is quite remarkable and really shows that the model not only learns to interpolate specific locations of the planet, but it really learns how to interpret the state of the atmosphere. And if the state of the atmosphere allows for an extreme event to happen, it will predict that event. Another case here is just an extreme precipitation event in Queensland. Again, I won't go into detail. Even though the AFS single model prediction is quite smooth, we still managed to produce very high precipitation totals for this region that was affected by this event. On the bottom line, you have iMerge. On the middle line, you have the IFS, and on the top lines, you have AFS forecast. And we do see the issues in smoothing, but we do see that it also captures extremes quite well. And a third case on 2-meter temperature. So it's really on 2-meter temperature that the AIFS and AI models in general seem to excel. This is an event that happened in France in 2025, 30th April. So climatologically speaking, this was actually quite an extreme. And well, as you can see here, the model managed to capture it many days in advance, while the conventional model did not really capture it 1 or 2 days before it happened. And again, AFS really excels in meter temperature forecast. But of course, well, everything seems to be only good words about the AFS. I cherry-picked some examples, and of course there's other examples where the AFS didn't perform so well, but of course we need forecasters to use it and to give feedback so that we can really have build trust on this type of model. And the good thing about AMOs is that in terms of cost, operational utility costs, I would say, they're much cheaper than physics-based models, like 1,000 times less in terms of energy requirements. But of course, the elephant in the room is ERA5, and to train ERA5 and to produce ERA5, to use enormous amounts of expenditure, euros, etc. So we have to always consider when we compare the operation costs of this model, we have to consider the operation costs that producing ERA5 compared. So now moving on a little bit more to more precipitation-related activities. One of the things we're exploring is fine-tuning the AFS with iMerge data. And well, so far we have trained the AFS with ERA5 reanalysis and also with IFS analysis data, and the results have been great so far. As I showed before, the model is even more skilled than the IFS for the conventional model. But of course, ERA5 has some shortcomings, and a lot of you will be familiar with that. So first of all, precipitation is not really simulated in ERA5 in the IFS analysis. It's actually a model forecast. So this is the first thing. And we know that in some regions, such as the tropics, it's not really accurate. And well, we wanted to explore different products for training the AFS. And of course, the first product we tried is the iMerge one. And I'm always stricken by the differences in just when you plot an iMerge output and compare it against an ERA5, the differences are just very striking, especially over the oceans, and in terms of precipitation totals and live precipitation, the difference is really significant. This actually started with a paper that we wrote on evaluating precipitation observations across Ecuador. So this was the work of Angela Ida Wong. She spent a year at WF, and she came with an observation data set from the Ecuadorian weather services, and this was quite nice to have because it's really an independent source for evaluation. And we just wanted to evaluate 3 different products for this region in South America. And very nicely here, so the most important product I would say is the top left one. We use a scoring metric. I'm not sure a lot of you are familiar with it, the SIPS score. This is basically trying to categorize rain output in 3 different categories. We have no rain, light rain, and heavy rain, instead of using like the Rudman squared error, which would penalize large errors quite heavily. So it's based on I won't go into detail, but it's based on these 3 categories and how well we forecast them, depending on station climatology. And the conclusion so far is that for this particular region, iMerge seems to be the best product, or the product that represents precipitation the best when compared, again, MSWEP and ERA5. So of course we wanted to fine-tune the AFS on iMerge, and this is some early results that we have. So basically what we're doing here is that in the fine-tuning phase, we just swap the total precipitation. We swap ERA5 total precipitation with the one that we have from iMerge. So physically speaking, this doesn't make any sense at all, because there's no break completely physical laws, because there's no correlation between the TP that we have in training and, for example, the other variables such as humidity, etc. So we break all possible physical law here, but you can still do this when you train an AMO. And very interestingly, what happens when we fine-tune the AFS on iMerge is that we do see an improvement in the tropics. So this is the top right plot that you have here. Again, it's the SIP score, so the higher the better. The green line is the AFS iMerge model, and you see that it's across all the times better than both the IFS, which is in red, and the AFS trained on ERA 5. But very interestingly, we see degradations in the southern hemisphere, especially, and the northern hemisphere. So here, I mean, I'd be really happy to discuss with anyone that works on iMerge why would this happen and what's going on. Is it maybe because, especially why we see this huge degradation in the southern hemisphere? Is it because, well, the northern hemisphere is more data rich, so it's expected that the iMerge product has less accuracy in the southern hemisphere? Is there something else that could be going on? I'd really be happy to discuss this with anyone in the room. I very rapidly go and present some other approaches that are also being explored at the center. We have a group of people that are exploring forcing the AFS with AFS forecast. So basically, it's just forcing the conventional model at the larger scales of the conventional model, some specific model levels, and these are shown to actually improve the forecast in the IFS model. This is actually something that is being done by the Canadian weather services, so this is actually already operational for them. Another stream of research is AI prediction directly from observations. So of course we use ERA 5 because it's very convenient, right? But data simulation is quite expensive, so there is people exploring whether we can produce forecasts directly from observations. And the results are quite scary, I mean, quite exciting, but it raises a lot of questions on, well, what will happen for weather forecasting in 10, 20 years. But it's really, really exciting work. And finally, more on the long-term horizon, there's also a group of people that are exploring foundational models. Foundational models combine multiple types of data sets, build type of single core units, that core models, foundation models, and then forecasting would be just a specific task that we fine-tune these models towards. We could also have like downscaling that is learned by these specific models. So it's really kind of the next generation of AI forecasting models. So where are we right now? Right now, for headline scores, data-driven models seem to be best, but again, this comes with caveats. These headline scores are really focused mostly on large structures. For extremes, it is true that the deterministic AI models, or AFS single, tends to underpredict extremes, but this does not mean that it can be useful. When it does predict extremes, it can actually be quite accurate. So I think it's still useful for forecasters, and we just need forecasters to use it and give us feedback or a better idea of how much we can trust for this type of models. And for the extreme events for the AFS, CRPS models, when we looked at the early scores, it's actually quite competitive against the IFS ensemble, so we still a little bit more evaluation on this part. And where is the field going? I would say, well, Earth system data-driven models. So right now we have mostly atmosphere-related variables in the models, but there's people working on integrating other components such as land, ocean, and other processes, etc. We're also working on extended range predictions beyond 2 weeks. We're working on higher temporal and spatial resolution. I think later this year, we have hourly output, and in the next year we'll have 9-kilometer resolution on the AMOs. And we see that training is slowly moving towards combining maybe ERA 5 with observations. I mean, this is a little bit my opinion, but there won't be a new model that is published that just completely outperforms all the other 6 existing models. I think what's really important now is data and how we leverage the data that we have. And I think ERA 5, we have mostly used 99% of the capacity. A very important question is what data simulation, what is the role of data simulation in the next 5 to 10 years if we see that these models that are initialized from observation actually perform quite well. And yeah, the European kind of scale, we have Eastern Bloc is really trying to collaborate with the member states to open and rationalize AI models of every member state water center. And, well, the kind of framework behind all of this is Anemoy. So Anemoy is an open source framework that provides complete toolkit to develop data-driven water models from data pipelines. So we use ZAR a lot. I heard that it was mentioned a lot during this conference. From data creation, dataset creation to training and model inference. So here's some papers if you want to read a little bit further on this, and I'm very happy to take questions this time. Thank you very much.
So I emerge in the southern hemisphere. The GPM algorithms in general have historically had a lot of trouble over the Southern Ocean because the radar doesn't see a lot of light precipitation there, and all of the other algorithms are calibrated to match the radar. I will say, though, that that is changing for version 8. We're making a lot better use of the passive observations, so it would be very interesting to see what your experiments look like with the new versions.
Yeah, thank you. I'm really excited about V8.
I was wondering about the strategies you guys use during the training process. Like, how do you curate the data set you use in terms of the years? How do you stratify your data at all? How do you try to prevent things like overfitting, that sort of stuff?
So what data we use? How many years?
Yeah, what years do you guys use? How do you evaluate? How do you do the training, testing, verification stuff?
So basically we use, I think this is what I tried to say here. I remove a lot of slides because, but, so we use 40 years of ERA 5 data. Then we use 8 years of IFS analysis for fine-tuning. And on the evaluation side, so we always evaluate, or if we train a model up to 2024, we usually evaluate on the next year. I don't know if this is the best thing ever because, of course, the atmosphere will be correlated from one year to another. But on an operational setup, it's really hard not to stop yourself from using that recent data because that really makes big impact on training a model. And then we also use synop stations, so observations to evaluate our model also, which is all integrated in like the evaluation pipeline of the IFS. So we use the same evaluation pipelines.
Do you think that some of the variables where you do better at has to deal with just the better quality measurements you use? Like 2-meter temperature? Oh, just like the better quality measurements. You know, you said you didn't do as well in the stratosphere. I mean, I would expect that maybe that's to be expected.
Yeah, on the stratosphere issue, it's really hard to know exactly what's going on. It could be that it's very hard for the model to learn the dynamics of the stratosphere. Maybe the observations are not very high quality, so the model interprets them as noise sometimes, or it doesn't really manage to compute the correlations properly there. But yeah, it's a good question. Yeah.
Since this is a pre-sub conference, what ERA 5 or ECMWF has always had too much evaporation, particularly in the tropics, and a bit too much precipitation. You could see that in your slide as well. So the question is, when you went over to train with the observed precipitation without changing the observed evaporation, does that screw up the physics? I mean, can you comment on that?
So the thing is, we don't have evaporation in training at all. So the model produces precipitation diagnostically. All the moisture-related variables we have is, so we have relative humidity, we have total cloud water, and I think that's it. So we don't have this physical relationship in the model.
Hello, thank you for this nice presentation.
On slide 14, you have mentioned that you have introduced the noise in the training of data. So what
40?
kind?
40?
14.
14, sorry. 14. Oh yeah, for the ensemble version.
Yeah. So what kind of noise and what is the criteria that you have introduced while training the model?
So actually what we do here is that we start from Gaussian noise in the latent space. And then we have a layer that is learned during training so that this noise is modulated and transformed such that it actually represents a little bit model uncertainty. So it's the component that adds the uncertainty in the forecast. So you could see it as just ourselves trying to modulate or to model this uncertainty in the forecast by adding some noise in the latent space. But this transformation and modulation of the noise is actually learned during training. So we just leave the model learn that by itself, and then the target is CRPS, right? We want to minimize CRPS, so do whatever you want with this noise, but minimize CRPS with it.
Yeah, very interesting. So if I understand correctly, you are kind of moving from ERA 5 to iMerge or products. That's what you are evaluating. I mean, as an alternative. It sounds like that. So in that regard, is it really important for you that the latency in the iMerge availability, like we have an early, late, and final, so are you gonna, do you really care about wait 6 months after the product happens? Is that a factor on your study, or use rather than maybe you might have to force the early or late product because of you cannot wait 6 months? That's my first thing. I think the second is although of course the iMerge is a great product, but also the so-called friendly competitor is the GS map from the Japanese agency. Have you ever looked at that as another alternative options, which is also they have with and without gauge adjustment. They have 2 versions available. Thank you.
So on the first question, this is an actual design choice. So if we choose to have iMerge as input for model, we will need available data. So we probably need the early runs. What is the latency on the early data on iMerge?
I think 4 hours.
4 hours. So it would be quite critical, but in the design choice here in the results that I showed, precipitation is diagnostic. So we don't really need an iMerge input for the model. We would just actually fine-tune the model with iMerge data. So the model understands what is the iMerge distribution and will try to forecast something that is similar to that distribution. And we don't necessarily need data input. So it depends how you want to tackle the problem. Do you want iMerge as an input to your model, or you only want iMerge as a target to train your AI model? And this is really a core, critical design choice that we need to make at some point. So yeah. And on the second question, no, but this is just a matter of, that's also why I attended this conference, is to really learn a little bit more about what are the available precipitation data sets and products. And for sure, now I really want to also test this other alternative for training the AFS. Yeah.
So this was really interesting. You had a bullet in closing slide. Do we need data simulation in future? Can you say something more about that? Pros, cons, what's your personal opinion?
Yeah, so this is a group of people that work at ECMWF, and they work on producing forecasts directly from observation. So what we do here is that we have these massive data sets from satellites, etc. We curate them. So this takes a lot of work. We put them in the ZAR format. We make them readily available for the codes that we have. And then we basically produce forecasts. We train a model to produce forecasts using only these observations as input. And the model actually can generalize pretty well. So even if your satellite data does not cover the whole Earth, since the model is global, it can actually learn to produce forecasts where data does not necessarily exist at all times. So it's a little bit more complicated than that, but the core idea is really, do we always need data assimilation? Do we always need analysis to train a model? And what I would say is, well, there's people exploring this. So far, the prototypes that we have are not beating the AFS that is trained on ERA 5. It even seems to be the case that gridded observations, so you take your satellite data and you put it on a grid, and you put nonce where you don't have data, it seems to work a little bit better than just using raw data and using like different encoders. So there is people exploring this possibility of like parsing forecasts without analysis. And I have no idea where it will go. Like if in 1-2 years we prove that it's actually quite competitive against the AFS, this will be, I would say, a massive discovery, and we need to be ready for that if it happens. But
okay. Thank you for your presentation. It was really nice. It was very interesting, really well said. I did have a question about some of the extreme events you were talking about. I do landslide stuff, and we're very interested in extreme precipitation. And so one of the things on your slide, it showed, I know you cherry-picked, but on this, if I'm not mistaken, you're comparing it as your truth value to a forecast, correct?
So
not ground reference?
Yeah, this is maybe not the best choice ever. I could have used a radar, but this is just as a reference. It's not truth, it's just in this test case I'm using analysis or short-range forecasts from the IFS operational forecast for that day, which is more or less accurate. I would say more accurate, much more accurate than all the.
Absolutely, yes, absolutely, it's more accurate. It would be interesting, though, to do the ground reference and see how it compares, because that's something that we also look at. So very cool. Thank you.
I have a question. Let me make sure that I understand it well. So at time 0, you only get information from ERA 5?
In operations or in
operation, yeah.
No, you use the IFS analysis, so the operational analysis.
So you have to run IFS anyways, right?
We have to run the data simulation system.
Okay, so you have IFS at time 0, then extract all the variables that you've shown, and then everything else is just prediction. So you get delta t, and then use that delta t for future step, and then use it again as an input, and then forecast next step, then use it again. Yes. So are you using only 2 successive time steps, or more than that?
So we're using T0 and T-6, and that's it.
Well, thank you. This is a great start to our afternoon. We're now moving on to our next session, moderated by Dr. Christian Kumaro and Dr. Effie Fofola Giorgio.
Next session is on data variability at all scales. It's my pleasure to introduce someone actually from my same institution, Freundschuh, who will speak about a data set that he's been developing for helping the AI community with algorithms. Simon?
Yeah, thank you so much. I'm going to talk about the community baseline and benchmark for machine learning satellite precipitation retrievals. And I'm giving this talk as the chair of the machine learning working group of the IPWG. So this is a screenshot from our most recent meeting. So there's contributions from all of the members of our working group. If any one of you is interested in joining that working group, you can please talk to me later. So at the beginning of this year, we finally released the first AI-ready benchmark data set for satellite-based precipitation retrievals. The principal features are that it basically includes satellite observations from the principal sensor types that we use for satellite precipitation retrievals collocated with high-quality reference data from ground-based radars over the US. And then I think what is particularly interesting is that it has a separate testing data set that includes independent reference data from 3 different regions so that you can actually evaluate the models also for generalization across different regions. So to complement this work, we kind of started trying to come up with a baseline retrieval so that we don't only have the benchmark data set, but that we actually have an open model that is publicly available and that kind of defines a state of the art of precipitation retrievals so that if anybody wants to propose algorithm improvements, they actually have a strong baseline to compare against. So what we did is that we looked at different machine learning techniques and evaluated them systematically on the benchmark data set. The techniques we looked at were the Bayesian-Monte Carlo integration, which is kind of a traditional retrieval technique that was used in the previous version of gprof. Random forest, XGBoost, and a fully connected neural network. So these are typically retrievals that operate on single pixels. And then, of course, convolutional neural networks, because they give us the capability to actually look at image structure. And because for convolutional neural networks, there is quite a big design space. We spent some time exploring this design space. So the first thing we looked at was kind of how do different ways of training the model impact the retrieval accuracy. So here you just see different error metrics as they progress, how they progress as we train the model. So on the x-axis, you have how long the training runs for how many epochs. And here you see the solid line is the stochastic gradient descent optimizer with a momentum, and then the dashed line is the ADAM-W optimizer, which has become more popular during recent years. And so just if you keep the learning rate constant, the learning rate is, of course, one of the defining parameters for the training. You see the metrics all improve as the training progresses. But now when you start kind of decreasing the learning rate, what you see is that the metrics actually stabilize. So if you don't decrease the learning rates, you see that especially the bias still remains fairly noisy until the end of the training. And so reducing the learning rate is required to stabilize these metrics. However, if you do, what we found when you do like when you reduce the learning rate whenever the validation loss plateaus, which is one common approach, you might end the training too quickly. And also we see that for these two approaches, actually the ADAM-W optimizer works less well than the stochastic gradient descent optimizer. Another way to handle the learning rate is to use like a Cozen annealing schedule that is more of a gradual reduction of the learning rate. And what this does, it actually gives better results at the end, and it also puts as stochastic gradient descent and ADAM-W on the same accuracy again. And then we also tested what happens when you add restarts to that. That just gives exactly the same accuracy. So there's a small impact from the kind of training strategy that you use to kind of represent this later on in the results. We take actually the weakest training approach, which was using ADAM-W with this reduced on plateau learning rate, and the stochastic gradient descent with the Cozen annealing learning rate with restarts. We also looked at different architectures. So this plot just shows across different panels the validation set accuracy of different metrics. And then basically each marker in this plot represents a different model configuration. And so for each model, we scaled the complexity. So we made the model deeper and wider. And this gives, those dots are basically connected by a line. So as we make the model more complex, the inference time on the x-axis goes up. And then you have the different configurations encoded by the color and the marker combination. So starting with the color, this is kind of the large-scale architecture of the underlying model. So for CNNs, the most familiar, the typical architecture is kind of the UNet architecture, but of course we can build other convolutional neural networks. We looked at what happens if we just leave out the downscaling. We have like an asymmetric encoder-decoder and also kind of an proposed improvement of the UNet architecture, which has more denser connections and where the computations between the different scales are kind of more interleaved. So if you compare the different colors, orange is the UNet. You see that for across all the metrics, this is already pretty optimal. The UNet ++, so this more denser variant, it gives the same accuracy. The other two approaches seem to work slightly worse. Then we also looked at kind of the principal building blocks, the convolution blocks. I will not go too much into details because this is what the different markers are. You see that they're fairly similar. One thing you see, though, is that actually as we increase the complexity, the accuracy tends to go down. That is because we have not increased the number of training steps. It's not an overfitting effect. So we check it is that the training loss is lower, so it seems that if you would just increase the training time, this would probably catch up with the less complex ones. But for our baseline model, we wanted to keep the compute kind of reasonable. So this is now moving to the testing data set. Those are the different accuracy on error metrics on the testing data set. On the x-axis of each plot, you have the different domains. So CONUS is the training domain, and then the gray bars are baselines, is gprof version 8 and gprof IR, so the two retrievers that go into iMerge in the next version of iMerge. And then the purple retrievers are the purple bars are the single pixel ones, and then the three orange bars are the UNet models. So there we have the lightest bar is the weakest training approach. The next darker one is the strong training, and then the darkest one is kind of the good training approach with the best model architecture. This is what we then kind of propose as a baseline, which we call the IPWGNet. Yeah, so you see actually one interesting thing. So generally, the convolutional neural networks, they work quite robustly better than the single pixel retrievers. But you seem to see that over CONUS, this advantage is actually best. So that seems to indicate that there is a certain overfitting. So the model seems to learn CONUS-specific or maybe MRMS-specific features that give the retriever an advantage over CONUS, but less so over the other domains. Just to give you a more specific example of how the retrievers look when we apply them to GMI. So top left corner, you see the reference from ground-based radar, and then top row, you have the single pixel-based retrievers, the more conventional machine learning techniques, and then bottom row, the convolutional neural network retrievers. I don't know if you can see it, they're hard to distinguish differences visually, but if you look at the error metrics, you see that the CNN retrievers give higher accuracy. This is, of course, GMI is our flagship precipitation sensor, so it is actually quite easy to do a good retrieval with it. You see much bigger differences when we move to observations that give us less information on precipitation, like single-channel IR. So if you look here, the top row, the single pixel-based retrievers, there's almost not any structure left. But if you move to the kind of convolutional retrievers, you see actually that it's able to capture basically the scattered convective cells that we see in the reference data. Just to look a bit beyond kind of these point-based error metrics, if we look at the precipitation distributions for the three different domains, orange is now the IPWGNet kind of baseline, and then you have the solid lines is the GMI retrieval, and the dashed lines is the GeoIR retrieval. And so you see actually for GMI, there's a small difference. The CNN retrieval does a bit better at the high-end precipitation, but there's a very big difference for the geostationary IR retrieval. Another metric, the effective resolution, so kind of the skill of the retriever to recreate the spatial structure. Here you also see that the CNN retrieval works quite a bit better. Actually, over CONUS, we go down to a resolution of effective resolution of 10 kilometers, and the single pixel-based retrievals are about a factor of 2 lower. And this is even stronger for the GeoIR retrievals. Yeah, just concluding. Yeah, unit-based retrievals are kind of state-of-the-art for precipitation retrievals. I think most people know that by now, and this just confirms these results. We've seen that almost no matter what they do, they give you robust results. So all the tuning did not help very much. And so the baseline that we're proposing is essentially a simple UNet with residual connections. And we've got all the implementations already publicly available on the GitHub of our IPWGML working group. It still needs some cleaning up, and we hope to get this paper, hopefully the preprint by IPWG in 3 weeks, so keep an eye out for that. And then, of course, interesting is that we see a certain sign for overfitting over the CONUS radars. So there's, of course, the question, how much tuning is it worth doing if what we learn is actually artifacts in our reference data? Yeah, thank you very much.
Thank you, Sam. Questions? Yeah.
Yeah, it was really, really fascinating talk. One thing that I didn't understand, you know, a lot of times when you use like PyTorch or scikit-learn, the default optimizer is Atom, not AtomW or stochastic gradient descent. So I was wondering, why did you choose those two? Did you try Atom? Is there a reason why you guys did those two?
I feel like most people nowadays are using AtomW, right? I mean, AtomW was kind of proposed as, I think, a fix for Atom. So that's just what I use by default.
Yeah.
And then I thought, as stochastic gradient descent is the simplest one.
Yeah.
And it has, I think it has a substantially better memory footprint. So yeah, that was kind of the idea. Yeah, you take the simplest one and you take the one that everybody else takes now. So.
All right, makes sense. Thanks.
Mike is coming.
So with respect to cost function, are you using what you're using, and then why are you using that?
Just MSE, because also again here, we plan to look, we didn't want to open the can of worms that is the loss function, so we just used MSE and kept that for future work.
But don't you think that might affect extremes or something?
Yeah, it does, but I think it's the, as I said, this is this is kind of the first step, right? We just want to find a robust starting point for future investigation, and so MSE seemed to us like the choice, the reasonable choice, or like, yeah, default choice, I guess.
All right. Okay, we're going to go now. Thank you, Simon. We're going to go to the next talk.
So the next talk is by Edwin Donovan, an artificial neural network QP scale correction model for the WSR-88 weather radar network.
All right, so radar-based QPE for rain those sort of algorithms have been in development for several decades now, and I think we're at a point where the algorithms themselves are really good when rain is close to the radar. So in this situation, it's a lack of beam broadening, you're well below the melting layer, and you're close to the ground, so there's less variability between what the radar senses and what people would experience on the ground. But there's a still challenge when rain is farther away from the radar. So in this situation, the radar beam will overshoot and hit the melting layer or snow layers. You have to deal with different scattering regimes. There's also the problem of beam broadening as well. And then probably the most important discrepancy here is this gate to ground distance. So all the processes that go on between the gates and the grounds, like advection or microphysical processes like evaporation, just aren't covered. And then finally, there's this issue of terrain-induced beam blockage, which in the US is a problem, particularly in the western portion, where you have the Rockies and Cascade and other mountain ranges that will frequently block the radar. So overall, these scale, environmental, and beam elements are not taken into account in our current operational QPE algorithms for rain. So to address this, our team came up with an artificial neural network correction algorithm. This algorithm has currently 11 features. So the first feature is just the gate retrieved rain or snow precipitation rates. So we use specific attenuation and KDP for rain, and then for snow, we use reflectivity and KDP. We also use 4 other features for radar. We include reflectivity, ZDR, KDP, ρHV, and we also include several environmental parameters as well. So one of these parameters we're calling evaporation potential, which you can think of as just the vertical integration of evaporation from the radar gates to the surface. We include melting layer height, gate interpolated wet bulb temperature, the difference in wet bulb temperature between the gates and the surface, the radar range, and the distance between the gates and the surface as well. So overall, we have 5 radar products. So we have the 4 sort of standard radar, dual polarization radar variables, including reflectivity, and then the radar-derived rain rates or snow rates. And then we have 4 environmental parameters, which we derive from the RAP model, and then we use 2 scale parameters or beam parameters. The model that we use is a fully connected feed-forward artificial neural network model. It has 3 hidden layers. We use Gaussian area linear units for the activation functions in these hidden layers. And then for the final layer, we use a shifted rectified linear unit activation function. So the idea here is that when the model is first initialized during training, the weights and biases are low. So the baseline essentially is what the model starts with, and then it makes a correction upon that. And then finally, for the loss function, we use a global relative square error. We do training a little bit differently than other QPE models. We use the 1-hour accumulation. And so what this means is that for all the radar volumes in the time where we have 1-hour gauge measurements, we take all the radar volumes and then we integrate them for a particular set of weights and biases during training. So the idea is that we come up with the rain rates or the snow rates for the particular radar volumes at each of the times, and then we numerically integrate to get the 1-hour accumulation. So these processes are just sort of algebraic operations, so doing the back propagation is not an issue at all. And one thing I should notice here is that the actual scaling factor we come up with is FNN. So the product that we get is the adjusted rain rates, but the model, the neural network model predicts this FNN parameter, which is a multiplier for the original rain rates or snow rates. Here's a map of our data set. We curated a particularly large data set of almost 500,000 gauges across almost 5,000 total events where we're considering continuous periods of 3 hours for each of these events. And then we did our best to stratify this data, including the geography, the rain intensity, and the terrain. So each of these 3-hour events we broke up into 1-hour periods. And then we used a greedy iterative event splitting algorithm in order to try to bin these histograms appropriately so we get approximately the same number of counts for each of these categories. So for example, in the terrain and the intensity and the height, we wanted the training tests and verification data sets to be about approximately 80-10-10. So here I'm just going to go into some results. The format for these plots is that the left panel shows the lowest tilt reflectivity at the evaluation time for the 1-hour accumulations. The black circles that you see there are heights above mean sea level in terms of 1 kilometer increments for the contours. The red contour indicates 200 kilometers away from the radar, which is the max distance that we considered here. And the scatter plot that you see on top of that plot is the difference in terms of the 1-hour accumulation between the original baseline retrievals and the gauges that we use for the verification. So on the right are the results. So the top scatter plot shows the original baseline retrievals, and on the bottom is the correction. So this particular example, you can see that the neural network model does really a great job decreasing the rain rates appropriately, particularly in the light rain, so in between like 1 and 4 millimeters. The neural network model does a great job actually dragging down some of the rain rates appropriately, but still maintaining the appropriate high rain rates that we see, where the 1-hour accumulation gets up to over 64 millimeters. Here's a typical light rain results. There's a stratiform rain from Seattle, Washington. Again, we have this sort of over-prediction of rain rates that you can see in this region as well, between about 1 and 4 millimeters. And the neural network model actually does a great job dragging down those overestimations and improving the results quite a bit. So we get, in this particular example, we get a decrease in the room mean squared error by over a factor of 4. So you can get really quite significant improvements using this neural network algorithm. Here's an example from State College, Pennsylvania. So this is interesting because you see all the sort of more convective elements to the south and in the Maryland area, and then more stratiform rain that's closer to the radar, maybe to the north. So for the close to the radar, the results are actually quite good and unbiased, but then we get these underestimations that you see in the Maryland area. So in this particular example, you can see that a lot of the improvements come from improving the Pearson correlation coefficient. So we improve it from about 0.6 to about 0.81. So the changes that we see are pretty substantial for some of these verification cases. And then finally, here's an example from a terrain case. So this particular radar from Flagstaff, Arizona, you can see the negative tilt here. So this is one of these cases where the WSR88D is actually utilizing negative tilts. So you know that the radar itself is quite high up. And originally the baseline, you can see we dramatically underestimate the 1-hour accumulation. But with the neural network correction, we can actually correct for that quite a bit, and so the results improve by a factor of almost 2 in terms of the root mean squared error. Okay, and then finally, here's just a cumulative result for all the verification gauges. So these are for this is for all the gauges that are in the verification set from all the events that we have. On the left is the original baseline, and then on the right is with the neural network correction. And you can see just across the board, we're getting much better statistics. You can see the root mean squared error decreases by over 1 millimeter. This negative bias, so there's a negative bias of about minus 0.4 millimeters that's in the baseline. We essentially cut that about in half, so we can really improve the bias that we observe, particularly in this crucial region between, say, 1 and 4 millimeters. And finally, you can see the correlation coefficient increases by quite a bit as well. So we're getting more correlated, less bias, and more accurate results. And then finally, we're interested to see how does our products for single radars compare to other products. So this is, for example, the MRMS third generation dual polarization 1 hour accumulation. So MRMS has various products for doing 1 hour accumulation, and this is one of them that uses dual pole variables. You can see, kind of surprisingly, we actually outperform MRMS for the single radars in all the statistical categories, at least they're very comparable. And this is surprising because MRMS it's a mosaic of a bunch of different radars and CONUS. So the model that we're using is kind of hampered in that way because it's not utilizing all these different radars, but we're actually able to get a lower root mean squared error and a lower bias as well with a similar correlation coefficient. Okay, so to conclude, we train, tested, and verified this artificial neural network correction model on almost 500,000 gauges. We saw over a 1 millimeter decrease in the root mean squared error when using this correction model, so it really seems to be important for getting accurate QPE. And then we saw lower bias and root mean squared error and relative error than the MRMS. So overall, this is looking really promising for us, and for the next steps, we're interested in testing out different hyperparameters, incorporating different variables, maybe including variables associated with advection or other processes as well. And our goal really is to try to deploy this operationally in the ORPG, which is what's used for the WSR88D network. So with that, I'll take any questions. So thank you.
Thank you. I'll take the opportunity to ask the first questions. When can we get that?
When can we get it? Well, if you email me, we can chat. So I am finishing up a draft manuscript, so it'll be submitted soon. So.
Because I'm thinking this explains all the last errors we had in the retrieval algorithm. It's not my fault.
Yeah, just a few clarifications. You said, did you use the RAP as an input rather than her? Is there any
Correct.
There any reason behind that?
So processing 500,000 gauges takes a while, and I have to do the interpolation. So the interpolation with the RAP, even though it's coarser resolution, is faster. That's why.
And one of your slides shows the number of gauges. Did you say you have 400,000 gauges?
Almost 500,000, yeah.
There are 500,000 different gauges that you have found out?
Well, some of the gauges are reused, right? I mean, for different, so it's over a 5-year period.
Oh, okay, so it's not like a 500 different gauges, 500,000.
No, 500,000 gauges across 5,000 events across all the U.S., so I can go back and show you.
So that's what confused me about, I guess, because I know that MRMS used 26,000 gauges, like separate. So your one is that many gauges, but actually could be reused, the same gauge.
Yeah, and I didn't mention this, but to save storage, I use a 2-kilometer median filter over each gauge, and that way I just have the mapping between the radar and the gauges directly.
And then maybe the one last question is, given the fact this is a European, we are in Europe, what do you think about your methodology can be applied to outside the United States?
So, it's everything I showed here is, nothing is really special, right? This is an artificial neural network model. It's not even a convolutional neural network. So it really just takes in input and spits out output. So anyone can do this. it's not particularly hard. I mean, we've seen presentations today that are much more complex.
Super quick question. I saw Peter's the DAS relationship at the beginning.
Yep.
What do you do for snow?
Snow, that's a great question. So for snow, currently, we cap KDP at 0.01 degrees per kilometer. We're probably going to change that to actually ensure that we have the negative values in order to debias the snow in the same way we do for rain. But yeah, we're just using Peter's, Z KDP relationship. Yep, just one. Yep.
Yeah. How do you handle zero precipitation? Like, do you have that in your data? Because I think I saw a paper last where they didn't have it, and that's where the neural network used it.
Yeah, we cap it at a very low value. So and I don't know if I show this here, but in any of my hidden slides, but each of the variables I cap at a minimum and maximum value, and some of the variables have transformations as well. I do a log transform on the rain rates because it scales better, but I just have a very low rain rate because if you have 0.01 millimeters per hour, it's basically zero. So.
Did you have time to look at like the accumulations over longer time, like the climatology essentially?
No, and the reason is because that just takes more time. 1 hour accumulation, I think, is stable enough that you can do a lot of work.
Yeah, but I mean your corrected data. Like
actually applying it over? No, we should do that at some point. We just haven't had time to do it.
I think that would be really great to see.
Yep, for sure.
So next speaker is Jim Smith from Princeton. He will give it remotely. The other authors are Vitek Krajewski, just for those that don't know, one old-timer that has been almost in all IPCs, and Rasu Maker. So we'll be on estimation and analysis of short duration, warm season rainfall extremes in the eastern U.S.
I'll discuss polarimetric.
Yeah, on polarimetric radar.
I'll discuss polarimetric radar estimates of extreme short duration rainfall in a specific context, and that is estimation of probable maximum precipitation. Probable maximum precipitation is a design and safety standard for high hazard dams in the United States. One goal of the talk is to advertise the recent National Academies report, which provides recommendations for modernizing probable maximum precipitation estimation. It's a long report, and I'll highlight the two most important recommendations. The first is to change the definition of PMP from an upper bound on rainfall to an extreme quantile, and the second is to estimate PMP using extreme value analyses applied to rainfall fields derived from long, high-resolution climate model simulations. Developing the necessary modeling tools is an ambitious goal that will lean heavily on good observations of rainfall extremes, and that's where the polarimetric rainfall estimates will be needed. There's a lot of work to do in developing accurate PMP estimates over the wide range of time and space scales required for dam safety applications. Today I want to focus on one of the biggest challenges for PMP, which centers on extreme short duration rainfall, especially in mountainous terrain. More than half of the high hazard dams in the U.S. Are in watersheds with drainage area less than 50 square kilometers, and there's a concentration of high hazard dams in and adjacent to mountainous terrain. To narrow things a bit more, I'll focus on the Smethport challenge, which is to accurately simulate the climatology of rainfall extremes from Smethport-like storms using high-resolution climate models. The July 1942 Smethport, Pennsylvania storm produced world record rainfall at timescales ranging from 10 minutes to 4.5 hours. I'll use the Smethport challenge as a vehicle for assessing modeling and scientific advances needed for estimating short duration PMP. Some key points about the Smethport challenge. The first is to note that it's meaningful to consider Smethport-like storms as a class of events suitable for climatological analysis. They control PMP for a 1,000-kilometer stretch along the western margin of the Appalachian in the eastern United States. The second point is that orographic precipitation mechanisms play an important role in rainfall extremes. And finally, it's difficult to accurately simulate extreme rainfall from Smethport-like storms from numerical weather prediction models. There are more than 400 bucket survey observations from the July 1942 Smethport storm, but of course there are no radar observations. We need accurate, high-resolution rainfall fields from polarimetric radar to develop and assess models used for PMP estimation. There are, however, no storms in and adjacent to the Appalachians during the polarimetric radar era for which rainfall maxima approach the largest bucket survey observations. Record bucket survey observations, shown here in blue, are about twice the largest polarimetric radar observations, shown in red. For the polarimetric era, we use KDP-based algorithm that incorporates available surface observations. For each of the polarimetric era storms, our rainfall analyses are larger than the operational rainfall products. Now, there are wildly different sampling properties for bucket surveys and for polarimetric rainfall data. Sampling differences and or errors in bucket surveys may contribute to the gap between bucket survey and radar analyses. It's also possible that there is a built-in tendency for underestimation of the most extreme rainfall from polarimetric analyses. If so, it's a significant problem for development of model-based tools for PMP estimation. We've carried out gauge radar intercomparisons for extreme rainfall events during the polarimetric era, including the ones that I showed in the previous figure. These analyses generally support the conclusion that polarimetric algorithms underestimate cores and peak rainfall. The results here are for a Smethport-like storm that occurred in July of 2023. It's important, but it's difficult to draw strong conclusions based solely on rain gauge radar intercomparisons. Radar rainfall algorithms typically assume that vertical motion is zero. Strong downdrafts provide a mechanism for systematic underestimation of rainfall extremes. Smethport-like storms, like the July 2023 storm, on the extreme high end of the convective intensity spectrum, with hail a common feature. World record rainfall accumulations for the Smethport storm were paired with nearby surface hail reports. Strong updrafts in polarimetric observations are indicated by ZDR columns, in which large values of ZDR extend above the 0 degree sea level. Strong downdrafts are linked to KDP columns and to descending KDP cores. Strong downdrafts provide a built-in mechanism for underestimation of peak rainfall. And I'll have more to say about vertical motion and radar rainfall estimation in the next session. In addition to our polarimetric rainfall analyses, we've examined the climatology of rainfall extremes from operational products. This figure shows 3-hour exceedances of 225 millimeters from the MRMS reanalysis, which mimics the operational polarimetric algorithm. The August 2021 Waverly, Tennessee storm is the only storm from our collection of extreme Appalachian storms that appears in the MRMS lists. And the magnitude of rainfall is smaller than the rainfall accumulations from our analysis. There's little evidence for Smethport-like storms in the MRMS reanalysis. Even more troubling, there's no evidence of Smethport-like storms in the CONUS 404 data set, which is developed from simulations using the Weather Research and Forecasting model. The CONUS 404 data set doesn't even include the August 2021 Waverly storm. There is, unfortunately, extensive evidence of extreme rainfall from Smith-Morton-like storms and flash flood fatalities. The CONUS 404 analyses point to the difficulty of accurately simulating rainfall extremes from Smith-Morton-like storms. Part of this challenge is tied to orographic precipitation mechanisms. The MRMS and CONUS 404 analyses were presented by Russ Schumacher at a workshop on extreme convective rainfall in mountainous terrain that was held last November. The workshop completed the work of the National Academy's PMP Study Committee and includes outstanding presentations that chart out scientific and modeling advances needed for modernizing PMP. I encourage you to have a look. The PMP study features a vision statement, thanks largely to Effie. Achieving the vision is a big job. The PMP study details why it's worthwhile to do so, not just for PMP applications, but for a wide array of high-profile societal problems dealing with hydroclimatological extremes. Thank you.
So yeah, I was part of the PMP consensus study, and we did a lot of work. So if you have not looked at the report, please have a look. It is basically presenting not only the vision, but the framework for updating extremes used for design of high hazard dams. So the next talk is by Sterios Emanuel at the University of Central Florida. Beta log normal canonical cascades and breakdown coefficients for temporal disaggregation. Application to high-resolution rainfall over Sardinia. Thank you, Sir.
Yeah, thank you, and thanks to the committee for having me and the hospitality Vasco. Actually, there is a small thing. The study is not over Sardinia, it's over Florida. Yeah, we changed a little bit the scope, but yeah. All right, so a lot of talks about AI and data. I'll take you back a little bit to good old traditional stochastic hydrology. About temporal disaggregation of rainfall, I'm pretty sure that whoever has worked long enough with rainfall data had at some point the issue of having a product that was desirable for the application, yet it didn't have the right temporal resolution for something specific that we want to do. For instance, creating ietograms, right, for stormwater drainage design. Now, when we're doing stochastic temporal disaggregation, the most frequently used tools are multiplicative cascades, which serve as generators of what we call multifractal measures. And rainfall is a process that is multifractal in nature. It exhibits multifractal scale invariance over a finite but very important range of scales. Now, the two types of models that are used in the literature are either what we call canonical cascades or microcanonical cascades. And essentially, they take the process from a coarser scale and they break it down to finer scales using either multipliers or breakdown coefficients. The two models are pretty much the same in terms of their nature, but they have a major theoretical difference, which is exactly the breakdown coefficients and multipliers. The multipliers in canonical cascades, which can be considered also the ground truth, let's say, of the entire process, they represent the process better, are essentially only lower side bounded, which means they can go to infinity, right? They range from 0 to infinity. While for microcanonical cascades, the breakdown coefficients, they are bounded on both sides. They are bounded to 0 and 2, okay? Which means that for canonical cascades, we can go only from one side of the process to the other, while microcanonical cascades are reversible also. canonical cascades, they maintain practically the amount of rainfall that we had at the different levels. So, the practical differences and what they look like, okay? So, although they are both multifractal, as we said, they have very different scaling properties, which you can see in this graph. Practically for moments above 1, the process tends to deviate a lot. And this is because microcanonical cascades, they tend to preserve coarser scale rainfall totals exactly at its level, which means that there is a dependence in the BDCs, the breakdown coefficients that we saw earlier, and this has been proven also theoretically in the first study of the series of studies that actually led to this presentation by Aguilar Flores and Castellano in 2024. Now, the real question is, given the gap that we have between canonical and microcanonical cascades, can we somehow estimate microcanonical parameters in order to reproduce practically the scaling that we get in canonical cascades? So there has to be some type of bridging between the two processes, and this has to be done through the breakdown coefficients, okay? The breakdown coefficients between two sequential levels can be defined by this relationship. I'm not going to get into the details of the relationship. You have to remember that it's bounded in 0 and 2 with a distribution that is independent of the level, the cascade level that you are. But the most important thing is that this actually can be proven, the relationship and the boundaries can, they have a second order analytical approximation, which was the second part of our efforts. Another study published in early 2026 by Langus et al. And leads practically to a matching strategy for the case of beta log normal cascades. When we are talking about beta log normal cascades, we're talking essentially about two distributions describing a process, a beta distribution describing practically the intermittency of the process, and a log normal distribution describing the variability within the wet days. There is a very rigorous mathematical way to do it. I'm just going to describe it, that we have to fix the beta parameter, the C beta of the microcanonical process to be equal to what we estimate from the canonical process, and this way we preserve the fraction of zeros, so the intermittency of the process. And then we have to estimate a log normal parameter in a way that the second initial moments of, so the variability of the canonical and microcanonical cascade variants match. And on the bottom right here, you can see actually what this matching looks like in terms of moment scaling functions. You can see that the two processes actually match when we do the matching process that I described, exactly up to a maximum admissible level of 1 minus the parameter of the beta distribution divided by 2, which is a very important theoretical result, and it's based on the second order approximation that I mentioned earlier. And for any C log normal larger than this maximum level, the second initial moment of the dressing factor diverges, and we cannot have this analytical approximation no more. And this gives the answer, actually, that if we have a combination of beta and log normal parameters from a canonical process, we can actually have another combination of beta and C log normal parameters in a microcanonical setting that reproduces the process up to a maximum level. So we apply this over Florida. We chose to do it over Gorges as a first approach, a first study. And we use rainfall observations from NWS. They are very high temporal resolution, 15 minutes, and they have very long records. We have 45 stations over Florida. And they cover a broad rainfall regime, right, with convective storms, frontal systems, hurricanes, you name it. So the methodology for the parameter estimation in order to do the temporal disaggregation. So first we have to aggregate the available time series to the daily scales in order to reproduce an experiment where we have a daily product and we want to disaggregate it into finer scales, okay? Then we split the rainy days in different rainfall intensity groups, which you can see in the scatter plots below, and conduct a scaling analysis for each of the group in order to estimate the C-beta and C-log normal parameters from the canonical process. Then we can use these pairs, these combinations, in order to create a statewide regression model practically, and you can see it's a simple regression model in the log space. And from that, we can estimate practically the C-beta and C-log normal parameters for any point in the state, okay? Now, after we finish with the parameter estimation, we have to do also the stochastic rainfall disaggregation, which means that for each wet day in record, we have to use the obtained regression that we had in the previous plots in order to estimate C-beta and C-log normal, given an observed daily rainfall intensity. Then, given this set of parameters, we estimate the C-log normal star, so the C-log normal of the macrocanonical process, using the approximation that we have from the BDCs. And finally, we can downscale the daily rainfall intensity by randomly shuffling essentially the respective distribution that we have to develop a cascade to the desired level. And I'll show you an example of how it looks like, and it's similar over the entire state practically. Here I'm going to take the daily scale, which is the upper scale, and I'm going to take it down to 45 minutes, which is sub-hourly. And here you can see how the distributions look to the 6th level practically, because the 0th level is the first one here. And what you can see is that across all practically resolutions that we saw, the microcanonical practically disaggregation reproduces the observations exactly in terms of the statistics, okay? And for risk applications, this is extremely important, obviously. So to conclude, we have a matching strategy between beta log normal canonical and microcanonical cascades, which is established actually in a paper that's going to be published soon in Fractals. It has been accepted, where we use all C-beta and C-log normal parameters to create a single regression over the entire state or states. We aim to expand this over the entire US and provide regression for all states, all US states. And given this pair of parameters, find an admissible C-log normal for the microcanonical process in order to conduct the stochastic disaggregation. Then the cascade-derived marginal distributions reproduce the empirical CDFs almost exactly across all studied sub-daily and sub-hourly scales. We can go down to a minute practically. The framework accurately converts low-resolution rainfall totals into finer scale realizations, and practically it supports stochastic disaggregation at GOTS and unGOTS locations. And finally, as future directions, what I mentioned practically, that we will have this intensity conditioned regression curves over all US states, and we will expand to all NWS COOP stations that we have, and potentially gridded products. Thank you.
I'm interested in the relationship between the multifractal behavior of rain and the microphysical processes. So what can your beta log normal matching strategy, how can that help us understand microphysics better?
The microphysics of the process?
Yeah.
The microphysics of the process, you cannot understand much essentially from statistics, right? Essentially, the statistics describe the inherent behavior of the process as a process, right? So it describes the intermittency, it describes the variability, but microphysics, not so much.
Okay. So what's the main sort of outcome then that's important for that people can use? Because your presentation was quite technical.
Yeah.
So I'm trying to, I'm interested in how can I use this in my own research?
It's a great question, actually. Yeah, okay. So imagine that you have a product, right, like the Daymet product, that it's in daily scales. So you have stations across the US that are only in daily scales. using the matching strategy, right, or the curves that I actually showed, okay, you can go down to sub-hourly scales in order to derive, for instance, a nietogram for...
So it's a way to extrapolate to smaller scales, or...
You are not extrapolating. You are practically estimating exactly the properties of the process at this case. Yeah.
Okay, great. Thank you so much.
Yeah, I think I was just bit my information about. You said the co-op gauge is 15 minutes resolution.
Yeah. Yeah, there are 2,500 COOP co-op gauges that go down to 15-minute resolution. Yeah.
Okay. Because most of them, we know them, they are daily gauges.
Most of them are daily, some are hourly, and there are 2,600 that are 15-minute resolution. Yeah.
Thank you.
Yeah. Thank you very much.
So the next talk is by Ho-Young Cha from Korea University, Beyond Sessionality, Uncertainty in Estimating Probable Maximum Precipitation Under Climate Change.
Hello everyone, I am Ho-Young Cha, I am at Korea University. So today I will present the study related to changes of probable maximum precipitation under climate change through statistical analysis. So this is the contents of this study. So let me talk about introduction of this study. So as climate change allows the atmosphere to hold more moisture, extreme rainfall events are becoming more frequent and intense around the world. So it is essential to analyze regional extreme rainfall characteristics and establish reliable design rainfall and proactive response measures. So as extreme rainfall becomes more frequent and intense, estimating PMP has become increasingly important for the design of hydraulic structures. So PMP refers to the theoretical maximum amount of rainfall that could occur over a specific area and time period. So it is commonly estimated using hydrometeorological or statistical methods based on regional rainfall characteristics. Based on this background, this study aims to estimate future PMP values using climate scenarios. Because climate change increases rainfall variability, we examine the plausible range of PMP estimates using the Horsfield method. We also estimate the return periods of future PMP values and compare them with the commonly suggested 20 million year level. So next I will show our study area. So our study area is South Korea. So South Korea has complex topographic with mountainous and coastal plains and many river basins, which strongly affect regional rainfall patterns. Each climate is influenced by the East Asian monsoon and typhoons. So PMP estimations should consider these geographic and climatic characteristics using rainfall stations. This study used the future rainfall projections from KMA based on shared socioeconomic pathways climate change scenario. So shared socioeconomic pathways describe different future pathways of socioeconomic development and greenhouse gas emissions. By using these scenarios, PMP values and their return periods were estimated for the period from 2022 to 2100. So next we talk about our methodology. Here this slide summarizes the overall methodology used in this study. First, annual maximum daily precipitation was derived for 6 future 30-year periods from 2002 to 2100. Then PMP was estimated using the Hirschfeld method based on the mean, standard deviation, and frequency factor of annual maximum precipitation. For the frequency factor, two approaches were applied. One calculated from the data and another fixed at 15. Finally, the return period of the estimated PMP was evaluated using the Conver distribution under different climate change scenarios. So to explain the Hirschfeld in more detail, statistical PMP is estimated by adding the mean annual maximum daily precipitation to the product of its standard deviation and frequency factor. So in case 1, the frequency factor is calculated by excluding the maximum value and using the adjusted mean and standard deviation. And in case 2, the frequency factor is fixed at 15, and the resulting PMP values are used to compare changes across future periods and climate change scenarios. Additionally, we estimated the return period of PMP using the Conver distribution. This allowed us to examine how the reality of PMP changes over time and across different SSP climate change scenarios. So then this is the result. The mean and standard deviation of annual maximum daily precipitation were calculated for each climate change scenario and future period. The results are presented as distributions to show the range and variability of annual maximum daily precipitation used for PMP estimation. So the mean annual maximum daily precipitation generally ranged from 30 to 180 millimeter under SP5, A5, it tended to increase over time. And the standard deviation ranged from 10 to 120 millimeter, and it was generally larger under climate change than under the climate change scenario. And then the figure on the slide shows the results of the frequency factor analysis. So it was calculated for each SSP scenario and the future period using the annual maximum daily precipitation data. So overall, the frequency factor remained below the upper limit of 15 proposed by Hirschfeld. However, under SSP 370, especially during 2071 and 2100, some stations showed a relatively large value close to 15. And then PMP calculated based on the previous estimated frequency factor and statistical values. The results were compared between case 1, which used the calculated frequency factor, and case 2, which used a fixed value of 15. Case 1 generally produced PMP estimates below 1000 millimeter, while case 2 showed much higher values, with some exceeding 100,000 millimeter, 1,500 millimeter. So overall, the PMP ranges were similar across scenarios and periods, but the highest estimates should be examined more carefully. To examine the highest PMP estimates more closely, this table summarized the top 5 PMP values with their corresponding years and stations. The results show that the selected regions and periods differ depending on the SSP scenario and the frequency factor calculation method. So these differences indicate uncertainty in statistical PMP estimation, especially related to the choice of frequency factor and climate scenario data. Next, the return period of PMP was calculated using the Conver distribution. In case 1, most return periods were generally within 100 years, while case 2 showed much longer values, often exceeding 10,000 years. This indicates that the estimated return period can vary greatly depending on the frequency factor calculation method. So to examine these return period results in more detail, this table summarizes the 5 longest return periods with their corresponding years and stations. The locations and periods differed across SSP scenario, and the longest return period did not always match the highest PMP values. So this suggests that a larger PMP does not necessarily lead to a longer return period, and then uncertainty remains in both PMP and return period estimation. So this is our conclusion. So this result indicates that the frequency factor calculation method is a major source of uncertainty in statistical PMP. So since PMP values and return periods vary by scenarios, period, and region, climate change may significantly affect the magnitude and reality of extreme precipitation events. So we propose the PMP is not value, it is the range through uncertainty. So for the future work, we aim to improve the current frequency factor approaches, since the proposed values and ranges still have limitations. So by considering both future climate change scenario, climate change and South Korea's regional topography and climate characteristics. So thank you for listening.
Now we have the last speaker of the day. I think the last speaker is bridging the gap why radar calibration is essential for rainfall, for reliable rainfall estimates from Joao Ferreira from here.
Good afternoon. My name is João Ferreira. I come from Portuguese Met Office, and I'm glad I was invited to this conference, and I hope to learn with you all, and I will give my contribute now. Well, I will start talking about the Portuguese Met Office, the meteorological radar network, general concepts. I wouldn't need to do this, but I will include this. The impact of wind farms on radar operation, the mitigation measures, what can we do, the results, and future improvements. Well, the Portuguese Met Office is an institute and state laboratory serving as a national reference for ocean and atmosphere. The mission is coordinate scientific research, technological development, innovation, and the provision of service in this field. We do 24/7 meteorological forecast and monitoring center for general and aeronautic purposes, forecasting, issuing weather warnings directed to the public and authorities, information available via the web page, subscription services, etc. Civil protection, we do daily briefing with civil protection entities. We have a dedicated website with updated critical information, focused on safeguarding lives and property. Well, we have a radar network. We contribute to the European network. It's through the OPERA program, the NetNet. This is an example for the 17 and 18 of October 2019. We started working with radars back to 1988, when we made a protocol with several universities in Portugal, and now we have complete, let's say, complete C-band Doppler radars in Aroca, which is in the north of Portugal, in Flores, which is in the Azores Island, in Porto Santo, which is in the Madeira archipelago, in Terceira, which is in the central group of Açores, in São Miguel, which is the eastern group of Açores, and other in near Lisbon, in Coruche, and in the south of Portugal, in Lolé. So these are the locations. The newest ones are in Flores, January 2025, and São Miguel in January 2025. Well, I will skip this because maybe I don't have time to do the whole presentation. I think you will know what this is about. So the radar emits electromagnetic radiation, a wave, a high frequency, at these frequencies. As it travels through the atmosphere, the radar pulse intercepts with the target along its path. The target reflects or scatters a portion of the incident energy in all directions, and that's the whole thing. There are some images missing. Sorry. Okay, it's here. So all our radars are now dual polarization, which means they emit in vertical and horizontal axis. So this is good to several things. So it can distinguish very well between snow, hail, and rain. Okay, so another point, a challenge to effective radar coverage is posed by strong echoes resulting from the effects and backscattering of radar radiation by terrain features, vegetation, water surface, or man-made structures, such buildings, bridges, and utility poles. The echoes are almost always present, even under normal propagation conditions. So this is known as clutter. This is an example of ground clutter for the reflectivity field. So there is no rain at this day, and you see lots of clutter. Yes, now the problem of the wind farms. Wind farms are very good because they are very ecologic and things like that. But they have some they put some problems in the radar meteorology. So they produce lots of clutter caused by the wind farms. For example, this is an example for a Roca radar. This is a day with no rain, so all the map should be clean, and it is not. These are the places where there are wind farms. So it's 21 to 25 of July. You see all those wind farms here. This is a summer situation. The same for a winter situation. There is no rain also in this period, and during the winter, it's still present. So for Kurush radar, the same thing. And the winter situation. And for Lolé in the south, we have wind farm cluster also. So this is a problem that must be tackled. Mitigation measures. What can we do? Well, in IPMA we use a relationship very used in all the world, which is the well-known Marshall-Palmer relation, which relates the reflectivity with the rain intensity. This is the Marshall-Palmer inverted, Marshall-Palmer. So we have the rain intensity related to the reflectivity. And this is the one that produced the clutter with the wind farms that we showed before. If we use another physical quantity called specific differential phase, KDP, that we heard about in previous presentations, we can mitigate a little bit the wind farm problem because KDP is much less sensitive to wind farm clutter than the reflectivity. So one thing that we could think is use KDP instead of Z. But that would be a mistake because at first glance replacing RZ with RK may seem straightforward. However, in practice it's not that simple because KDP is an inherently noisy radar variable, particularly in the regions of light precipitation. Normally, KDP is used only when the Z is the reflectivity is above 35 dBz. Well, what can we do then? What we tried, and this is the first step that we are doing, because normally we use the radar as a surveillance instrument, not as a tool to accumulate long periods of precipitation. We try to use both the rain coming from reflectivity and coming from the specific differential phase. So what we tried was use both. And how did we do that? We have 1 minute accumulated precipitation over a rain gauge, ground rain gauge. We try to use this 1 minute precipitation and see how it relates with both reflectivity and KDP. And we use these stations. So the circles are where the ground stations are. The radar is the pin. We use the stations which are 150 kilometers from the radar, and we put it all in one. We put it all in the study, and we regressed all this data, and we built this function, which is a 2-degree polynomial well, this is the part that most people would say that this is wrong, cannot be done. And but we were able to get this map, which seems okay. This is a period of heavy precipitation from 1 of January to 15 of February this year. It was a very severe rainfall event. The radar-derived field appears to be mostly consistent, showing credible quantitative precipitation estimates. However, some issues were identified during this study. A pronounced artificial ring cannot find, but it's in the south, though this circle here. So this was a problem that during 3 or 4 years was never spotted, because it's the only way to spot this is to integrate sufficient time. So this was spotted and it was solved. It was an hardware problem in the FARO radar. So this is good also to see eventual problems that the radar had. Well, but the field, the precipitation field seems nice. Future improvements. The most critical aspect of this work concerns the rainfall function derived through multiple regressions using data from 2024. It can be argued that radar estimation errors are not uniform across all stations included in the calibration data set, and that relevant factors such as station-to-radar distance and azimuth should have been explicitly accounted for. In the initial phase of this study, these factors were not considered. Nevertheless, the results obtained are considered satisfactory. The next step will be to explore machine learning approaches like XGBoost as an alternative to multiple regression. In this framework, the training inputs would be consist of Z, KDP, distance, and azimuth. I heard in the previous presentation I saw, I think it was 11, which was much more than this, and I would like to speak to you about this. It would be very, very good. While the target variable will be the observed precipitation, it is important to note that in this approach, the empirical transformation used to derive RZ and RKDP would be omitted. And so we don't use the power function relating KDP with R and Z with R, and we expect the machine learning to learn from the original data of KDP itself and reflectivity itself. Okay, thank you. Thank you.
All the way.
Hi, João. Obrigado for the presentation. I have a question regarding the availability of data for Portugal, because I can easily find radar data for Spain, for example, through IMET. But for Portugal, there's nothing available. Is there anything in the plans for the future to release the data to the public, either this or from the automatic stations, that we can use for research, for example? Yeah, but that's the issue. Having to ask, and the chain of emails and everything. Yeah. Yeah, for example. Okay. Okay, thank you.
Any other questions? Coming from behind you.
Hi, Zhao. Thank you for your talk. I just wanted to make you aware of an initiative that's being run through IPWG. So we're looking to create something called a surface baseline precipitation network. And the idea is to collect as much meteorological data as possible from ground-based radars. So I'd like to talk to you further about that if possible and look if Portuguese data could be something that could contribute to that. Thank you.
I think especially data from the Azores would be incredibly useful.
Really?
Yes.
And the new ones and all of them.
Okay, one last one, and then we're going to go for coffee break. Mike is coming.
Thank you, João, for your presentation. Just a quick question about the interference in the radar. You talked about the mountain and the topography, orography, you know. But I remember some of the colleagues from the Met Office telling stuff about the interference of WLAN networks, like sometimes the Wi-Fi networks. I think
there are lots of interference. I can talk about that only for 1 minute.
Yeah, the question was just if the methodology that you were talking about, does it mitigate this problem?
Could mitigate
or it could mitigate? Okay.
Hardly. It's going to be very difficult. You see blockage all over the place. You have in the south that blockage. It's a mountain over there. In the center of Portugal, there are trees just near the radar that must be cut off. So they also introduce blockage. And the worst scenario is in the north, where the beam is blocked by a mountain, and all the northeast part of Portugal is very...
It's like a blind zone.
Yeah.
Like it's blind, yeah. Okay.
It's blind. It's a blind zone. So it must be complete with another radar, possibly from our neighbors, Chinese neighbors. But, well, we have lots of problems. We have another annoying problem. It's not here in this map, but in the south, there are lots of boats passing by. And even the boats create fluttering. So it's very
And
difficult.
João, just for that you talked about the northeastern part, do you think that Salamanca radar can complete this? Okay. Yeah, thank you.
You know, I keep you from the coffee, but because the next section is on applications, I'd like to bring up one point for thought. So we've talked a lot about evaluation metrics. Of course, we measure what we care about. And also, as machine learning models advance, we talked about loss functions. And the ECMWF presentation and other made the point, root mean square error, of course, is not good. It's a double penalty, so it's going to smooth things out. And then we talked about the CRPS. So I will preserve the whole PDF. But the point I want to make is preserving the whole PDF at the pixel, whatever the pixel size is not good enough. For example, if I preserve the PDF at the pixel level, suppose the pixel is 10 by 10 kilometers, and I shuffle randomly all my pixels, I have preserved the PDF at the pixel level. I have done nothing to tell the pixel what the value at the neighborhood pixel is. So we have not preserved any covariance, any special organization. It's not difficult to see that Of course, I cannot preserve the PDFs at all scales, but if I preserve the spectrum, which is the variance at all wave numbers, at all scales, I basically, at least, I can preserve the PDF at the native resolution, and with the spectrum, I can present the second moment, the variance at all scales, which then preserves the covariance at all scales. You see what I mean? You can show this. So I think it is important to think about a loss function that does something about the spatial organization too. And we have shown in a paper 2 years ago in IEEE that this makes a big difference. I hope I made the point. It's not enough to look at the pixel, because I can shuffle the pixel and nothing happens to the PDF. Covariance and spatial organization is something we should explicitly train the model to preserve, and it's not difficult.
The name of the session? The name of the session in your folder.
The name of the session
In your folder. He said then the title of. So welcome back to this afternoon session. We just need this session plus a panel, so we are almost there. I'm convening this session with Hassan, who is going to make the first presentation, and it's about evaluation of health observation for radiological simulation at kilometer scale.
Thank you very much, and good afternoon, everyone. So I'm Ehsan Modiri. I'm a hydrologist who works at Helmholtz Center for Environmental Research in Leipzig, Germany. And today I would like to talk about the evaluation of the Earth observation constraint hydrological simulation at kilometer scale by the implication of the public health and vector-borne disease risk mapping. And first, I initially start with precipitation and hydrological simulation, then I will jump it to the part of the public health issue. So precipitation is the primary driver of the hydrological process, and since past decade, so we have access to really high resolution, high spatial temporal resolution of Earth observation products, especially for precipitation. So traditionally, when we run hydrological model using the coarse input data, so we face a huge amount of uncertainty. But with this high amount of the high resolution Earth observation, so it can tighter the uncertainty and increase the performance of the model. And so the new Earth observation products offers us a potential to improve hydrological simulation at kilometer scale. But a key question here is, can a high spatial temporal Earth observation products lead to a better performance hydrological simulation or not? And do simulation propagate these improvements in both ecological forecasting and public health or not? So I here designed a chain of activity that starts from precipitation, then goes to hydrology, and then ecology, and in the end, the public health. The scientific gap that we have is the most of the evaluation and research these days concentrate on a single model and on the single basin, and they mainly focus on the data simulation, the traditional data simulation. And the current research rarely assess the kilometer scale impact. And the Earth observation as a calibration constraint remains underexplored. And therefore, we decided to set a research to have multi-model, multi-basin, multi-region investigation and use EO as a calibration constraint to evaluate the performance of the hydrological model. So in this research, we have 3 case studies. So Rhine River Basin, limited in Germany, and the Po River Basin in Italy, and Tugela in South Africa. And so we ask all the partners to use the common harmonized precipitation forcing and temperature. And for European case study, we use IMO1, and for South Africa, we use CHIPS. And then so we replace the precipitation forcing with Hyper-V Lucas product. And then I'm gonna benchmark the performance of different models and evaluate the impact of high-resolution Earth observation programs. So a set of experiments is defined. So in generally, we have three different categories. The first one is the baseline, which is the forward line, no calibration. And in this baseline, we use the conventional meteorological forcing. Then we change it to the next category, so-called EO only, which we use the conventional precipitation and replace it with this Hyper-P product and calibrate the model against Earth observation, soil moisture, ET, snow cover area, and the combination of these components. And the last category is the merge Earth observation plus stream flow to somehow align the time series to see to somehow isolate the impact of precipitation itself and the other Earth observation variable. So before integrated of Earth observation, so we did and calculate the baseline scale to show that what's the performance of the model to benchmark the whole thing. The dashed line is the forward one and the solid line is the calibrated one. And from left to right of the figure, so the resolution goes to be coarser. It shows that for the majority of the models, so by going to the high resolution product, the performance of the model will go high. But the calibration performance, it's totally model dependent and basin dependent. So we cannot have any universal benefit from the Earth observation. And to move forward, so I have a showcase here for the Four River Basin. So to summarize the whole thing in the both figure, top and down, so I would say that the EO only calibration provide a mixed basin and model dependent results, so it's totally different. So from model to model, so we have different reaction. And EO plus Q calibration is most reliable gain, and the variability play a significant role here. So the metric that we use, that we discussed in the last session, is KGE. KGE is the metric that has three components: variability, bias, and correlation. And then, so these three components show us what's the best value. And the value is changed between -infinity to +1, and 1 is the best. So it shows that the same Earth observation precipitation it has different responses for different models. So again, so I will come back to the conclusion: there is no universal benefit from EO precipitation. And this one is somehow investigates only and isolate the impact of the Hyper-P products to show that by changing precipitation forcing, what would be the results. So if you have a look at the table, in the Po River Basin, it shows that one of the models have a higher performance in 59% of the whole discharge measurement gauge. And for Tugela in South Africa, which is a data scarce region, is the same. So the majority of the model shows the higher performance. But in the Rhine River, where we have the dense observation network for the discharge, so the new Earth observation precipitation does not have any improvement. So the beyond precipitation, if we wanted to move forward to other variables similar to soil moisture, ET, and snow cover area, so so the showcase that we have here in the lower panel, it shows that changing the conventional precipitation to Earth observation precipitation, how much has impact. And so the orange color is worse and the green color is better. Again, it shows that the second category, EO only calibration, improves for some models, and responses remain basin dependent. And again, the EO plus Q calibration deliver the most reliable results for us, even for all other experiments that we have. So here, so I come back to why should we care about having high spatial temporal resolution of precipitation, and what's the consequence of this thing. So to be honest, if hydrology is wrong, environmental predictor become unreliable. And unreliable data propagate through the entire causal effect. So precipitation incorrect cause and lead to the wrong runoff, wrong soil moisture, and consequently the environmental suitability and then vector or present absence of these sand flies or disease risk. To bridging the last part to that topic in public health, I would say that Leishmania is a disease transmitted by sand flies, which is a small insect that when they fly, they do not create any noise. So they are different from mosquito. As a hydrologist, so that was funny for me to understand and recognize this thing. And then so Leishmania is a disease that it's common between animals and human, and it's traditionally distributed all around the coastline in Mediterranean region. But after having, since 1990, climate change, it expanded to northward. So it, from time to time, we saw this thing in France and even south of the Germany. So we established to have a machine learning model based off the observation data that we collected all around Europe. So it's the CatBus XGBus method. And then so the method will produce some density distribution of sand flies on the daily and temporal resolution and 1 kilometer spatial resolution and over the whole Europe. And as you see in the figure left below, so we only have few gauges to measure the sand flies all around the Europe. And we use as a predictor or the feature importance of the thing, so we use every variable that we have access to. So all the methodological input, the hydrological simulation, morphological, land cover, land use, everything that we have in our hands. And then so we force the model MHM, the mesoscale hydrological model, to produce soil moisture in different layers up to 2 meters. And then so we did some sort of feature importance, selected the main one, and then run the model. And it shows that the predictions are controlled by a combination of the short-term climatic variables similar to temperature and soil moisture. We already lagged them for 1 day, 2 days, 7 days, 2 weeks, and so on, up to a year. And then long-term environmental suitability similar to morphological features. And in the end, it's produced a map. So as I said, so daily map for 20 years. So we have a sand flies density distribution all around Europe, but I zoomed in on the Iberian Peninsula when we have Spain and Portugal to show that what's the meaning of this thing. So we have 12 maps, so I just snapshot the mid of each month to show that the dynamics of the movement of the density for sand flies, which is the main factor of the Leishmania's disease. It shows that by changing to the year 2021 to 2022, only a single year, one of the species that we have moved 45 kilometers to the north, and so the occupied region that this sand flies distributed has an increasing of the 4.5%. So to answer the final question, can better precipitation information improve disease early warning? So my answer is yes. So the value of kilometer scale precipitation is not limited to hydrology. It propagates through the entire environmental prediction chain and supports public health early warning system for vector-borne disease as well. So as a sample, so I snapshot the system that we have for a project named CLIMUS. So for the whole European country, we have early warning system for this disease. So, and it's not only Leishmania, for mosquito we have the same thing, for dengue we have something, and malaria, so this sort of thing. So we were able to build for the first time a monitoring system, and after on a early warning system to show that how, and then people can see in the app in the next phase of the project that, okay, the warn, this region, so we go to the direction of the NOTS 3 region, so it means city and some municipality. So I think we achieved the thing that we have it in our mind, and that was the presentation that I wanted to share with you. Thank you very much.
We have time for one quick question.
Sorry. Quick question for the short and medium term forecast. So essentially, you're gonna give this to like public health. The goal is to be giving it and working directly with public health officials. I'm assuming. What's the forecast like when you say short and medium term? What's the goal to give that?
You mean how far is it?
Yeah. Sorry. Thank you.
So we use some of the ensemble members that we have. We use CIS5 scenarios. We have some climate project. So we already have 3 days, 7 days, 15 days, and some months. Yeah, but the point is, if you wanna rely on something, 3 to 7 days is the best thing that I already mapped up here. Next 7 days.
Oh, okay.
Yeah, but if you move forward, so because of having uncertainty in the precipitation, especially data, so we will face problems.
And just real quick, this might be a silly question, but sandflies to versus mosquitoes, do you have to change like the parameters depending on the ecological?
Yes. Yes.
Like how
but after doing feature importance, so they reacted differently because they have different ecological background behind. So sandflies mainly live in the layer of 5 to 15 centimeter. For egging, mosquito has to be near the floodplain. So they have two different nature, and from time to time they compete each other.
Thank you.
Yeah, and the last note is I had no clue in this topic, but I forced to learn something.
Thank you very much, Hassan. We can move to the next speaker, who is Simon, and talking about bridging the sensitivity gap in precipitation estimates from spaceball radars using passive microwave observation.
Yeah, good afternoon. Preparing the talk, I realized that gap might not have been the best word. Maybe it's more like two gaps. I guess every radar has its gap. What do I mean by this gap? Just to illustrate these are coincident observations from on top. You have radar reflectivities from the CloudSat CPR, which is a 94 gigahertz cloud radar, and at the bottom you have the reflectivities from the KU radar. And so comparing basically the reflectivities from the same precipitation event, you see that the KU radar misses kind of light and shallow precipitation, whereas the CloudSat radar kind of saturates and loses sensitivity very heavy precipitation. Now, as you probably know, these radars are very important for people like me who develop passive microwave retrievals because we use them as reference data. So we train our retrieval algorithms on them. And so the issue is that when we train, we primarily use for GPM, we use, of course, the GPM KU radar. We basically learn to miss precipitation. And so you see this when you look at kind of the zonal means over ocean. On the left panel, you see in orange, this is GPROF version 7. And then compared to ERA 5 and GPCP, you see at high latitudes, GPROF version 7 is deficient. And the reason for that is that the DPR, our training data, misses light and frozen precipitation. So for version 8, we wanted to do something about it. And so the solution that I came up with is basically use a convolutional network retrieval, just like GPROF NN, but train it with two outputs. One output trained to reproduce the CloudSat-based precipitation, and then the other output trained to predict the DPR-based precipitation. This is just an example of how that looks, of like a mid-latitude cyclone. On the leftmost panel, you see the results that the retriever produces for the DPR-based precipitation. At the center, the CPR-based precipitation. And then this white contour, I just added it to show what the extent of the precipitation of the DPR precipitation. You see the CPR precipitation adds quite a bit of that. But now, of course, we want one precipitation estimate. So we developed like a fusion technique, which basically just when the DPR retrieval doesn't say there's precipitation, then we look into CPR and take that precipitation, and then we smoothly interpolate into DPR as we see more in the DPR-based retrieval. So this is actually the coincident scene that I saw at the beginning. The gray dashed line is the CloudSat overpass. So if you look back at this precipitation system, the top panel now adds kind of the retrieved precipitation. So the blue line is the DPR-based precipitation estimates, and you see at kilometer 200, roughly, it just drops down where the DPR stops seeing any reflectivity. But by using kind of the CloudSat-based estimates, we're actually able to recover the missing precipitation using the GMI passive microwave observations. Now, of course, we wanted to somehow figure out, does this just add precipitation, or is this actually physically meaningful? So to do this, I just collected all the overpasses of GMI over measurements from the SAT-RAIN dataset. No, not SAT-RAIN, ocean rain dataset. Those are shipborne disdrometer measurements, so direct measurements of precipitation from ships. And this is basically all overpasses I could find between 2014 and 2018. So looking first at just the precipitation detection. So here you see precision recall curves. So these curves just quantify how well the algorithm detects precipitation. And then you have the blue curve, which is the DPR-based retrieval, the red curve, which is the CPR-based retrieval, and then the green is when you merge the two, and you see the green typically improves upon the single instrument-based retrievals. And then compared to gProf version 7, we see that we do a much better job at detecting precipitation, particularly at the mid and high latitudes, central panel, and then even stronger for mixed and frozen precipitation, where gProf was not doing very well. gProf version 7, that is. The precipitation estimation, the leftmost panel are the biases. So if you now again look at the colors, the green retrieval substantially reduces biases compared to the DPR-based retrieval and also gProf version 7. For snow, or frozen precipitation, we're still kind of low, but we basically more than half the bias that we saw on gProf version 7. Looking at mean absolute error, mean squared error, and correlation coefficient, the picture is a bit more muddled, I guess. So usually the fused precipitation estimates in green are roughly about the same accuracy as the DPI estimates, but the error seems to increase a bit. Anyhow, this is kind of the first part of the conclusions. So we developed this merged precipitation retrieval, and we use it actually in gProf version 8 to fill in missing precipitation in DPR. And so just to come back to the zonal means from the beginning, the green line is now added here, and it increases precipitation quite a bit at high latitudes and brings it closer in line with GPCP and error 5. Right. Another important point, this only works over ocean because we don't have precipitation, no liquid precipitation estimates from CloudSat, so we couldn't use it there. Right. This is the positive part. However, there was an issue that I kind of found when I looked into this. So I wanted to figure out why does this merging increase the error in the estimates against the ship-based measurements. And so I compared the DPR precipitation and the CPR precipitation. So basically collocated them, they look at the same spot, and now if you look at the left panel shows you the comparison between the CloudSat-based precipitation estimates and the DPR-based estimates. And this is, I guess, almost as bad as it gets, right? I mean, they essentially don't agree. For snow, we see that there's a region where they agree, where the kind of sensitivity regimes overlap. I also compared both radars to MRMS, so ground-based radar measurements, and so for CPR, you seem to see a similar pattern where CPR either heavily underestimates or heavily overestimates, but never seems to match it. And for DPR, we see this pattern where DPR has like this limited sensitivity, so it doesn't go below kind of 0.5 millimeters, and so you get this breakup, but it's more, at least we have a region where the two agree. This is a scene which kind of just seems to illustrate what I think is the pattern we see in these scatter plots. This is MRMS radar estimates compared with CloudSat radar estimates. On the left panel just shows you the horizontal precipitation field. It's fairly homogeneous in MRMS. But then if you look at the estimates along the swath, you see that actually CPR seems to jump from like being about 10 times as high as MRMS to being 10 times lower than MRMS and then jumping back up. And in the CloudSat reflectivities, it seems to coincide with a strengthening of the surface signal. So this is kind of the conclusion part 2. The CloudSat 2C rain profile product is inconsistent with what we get from DPR. I think this is a fairly, I think we should be worried about that because we use GPM, if I understand this correctly, we use GPM combined and CPR2C rain profile together as to constrain the high latitude precipitation in GPCP, and through this also an I-merge. So basically all the climatological information we have about high latitude oceanic precipitation comes from combining these two data sets, which are obviously not consistent. And yeah, I think as a community, we should probably put more focus on this kind of upstream validation. These data sets are more than 10 years old, and as far as I know, I'm the first one that kind of looked at them. And so I feel like this is something that should be fixed.
Question from Ali.
Yeah, thanks. Important work. However, the CPR that you use is version 5, which is, we know that this is not a good version. We use version 4, which is much better. So if you look at version 4, probably is much better than what you see in version 5. So we like a couple of years ago, when we looked at version 5, we found the same issue and we dumped it. We never used version 5 rainfall. We only used snowfall of version 5 CPR. And then we use version 4 of rainfall. And that version 4 rainfall has already been tested by a couple of people, a couple of publications already.
No.
I mean, I am on 2 of them. What do you mean, no? So I have...
The detection skill has been tested.
No, the estimation is also tested. The rainfall version 4, not 5. So, yeah, I mean, I'll also use
the thing is, I'm pretty certain that if you look at the 2012 paper that introduces the CPR algorithm, they talk about the bimodal distribution that they get of precipitation.
The version 5 of CPR rainfall is bad.
No, but but the bimodal distribution, this is pretty much the pattern. You see it in the first paper.
But that's version 5.
Huh? That's version 5. But the original paper has the bimodal feature in the precipitation distribution.
I mean, that retrieval completely changed from version 4 to version 5. That's what I'm trying to say. So
okay. Yeah. I would like to see the validation papers.
It's a different algorithm. Yeah.
Also, did I see you did the MRMS snow comparison?
The MRMS, this is both mixed together.
Okay, because you know that CloudSet is dynamic and MRMS
Sorry?
is CloudSet has a dynamic to best relationship while MRMS is static. So many differences might come from there. You saw the flat thing compared to more dynamic in CloudSet and the other chunks that you showed. I don't know if that was rain or snow, but anyways, the concept is that the amount of MRMS spits out is not necessarily right for snow.
No, yeah, certainly. But still, you would even if it was set off from the diagonal, I mean, that would be completely fine. But this is like, right, we have this bimodal behavior. Like, this is like, I mean, for a scatter plot, this is, in my opinion, as worse as it gets.
I'm sure there's validation done with that. I'll look up for you.
Thank you. And the last question is?
I'm curious about uncertainty using MRMS when you do the comparison with satellites. So there's a spatiotemporal uncertainty, and then there's also MRMS is not perfect as well. I mean, there's biases that MRMS definitely has. So can you comment on like how much uncertainty there is just doing the matching and ensuring that you have consistent results?
I mean, there's certainly uncertainty, but I feel like for DPR we get pretty decent matchups.
Mm-hmm.
And I mean, yes, CPR has a higher resolution.
Yeah.
But I mean, I feel like this is like a very specific example where I don't think there's much room for, like, this looks very homogeneous in MRMS. And I mean, CloudSat is quite all over the place. So, and even if you look at the reflectivities, right? I mean, they don't look like there's so much structure there. Like, certainly there's always uncertainty, but the thing is, like, as I said, I couldn't find any validation, and I just looked into that, and it looks pretty terrible.
Yeah. Okay. Thanks.
All right. Thank you very much. Okay, so we go to the next speaker. The next speaker is Masafumi Hirose from Japan, and to present work on the precipitation variability. Hello, everyone.
Thank you, Chairman. My name is Masafumi Hirose. I'd like to talk about some results on collective characteristics of precipitation systems and the associated error utilizing abundant specimen radar data. In Japan, our Earth, 6 out of 9 Earth observation satellites have exceeded their initial lifespan, and it raises questions about their ongoing value. So we have to answer what is the effect of additional operation. So with nearly 30 years of data record from consecutive to specimen radar mission, our understanding about the precipitation uncertainty and its complexity is gradually deepening. So in this study, in this presentation, I'd like to talk some about the limitation of the current data set and the precipitation climatology. That still requires more further data accumulation. I'd like to discuss about sampling adequacy and temporal spatial variations and the retrieval error using stream PR and GPM DPR data. I also developed a storm database classified by its spatial scales based on equivalent diameter of precipitation areas. The large systems greater than 100 kilometers in diameter observed a few hundreds per 0.1 degree grid for 28 years. So simply, roughly speaking, about one event for 1 month. So, and it the fraction of rainfall fraction by large precipitation systems is over 50% globally, and nearly 90% in the middle latitude. So due to such rarity of the high impact systems, the number of large systems must be important. Such continuous observation should be indispensable to accurately map their seasonal and diurnal cycles. And this map shows the interquartile range of the precipitation anomaly with a reference of long-term statistics for 28 years and 11 years based on GPM, DPR, and PR and KUPR. And this box indicates a range from first quartile to third quartile. And we found that about half of grid show no rainfall, no samples, and if we use 1 year data. So as you know, the shorter the time period, the scatter become diverse. And even for we use 15 years data, for statistics for 3 monthly and 3 hourly mean data, this range become between -20 to 20%. So it means about 50% of grid have a sampling error greater than 20%. So we can understand from this analysis, we can say that more continuous observation is indispensable. And I'd like to skip the detail, but this kind of composite analysis is advanced. We can extract specified events such as tropical cyclones. And recently, I added a 3D digital map of tropical cyclone observed by DPR, KUPR. So please check this digital website in my website. You can check this URL at my poster over there. And the users are generally from United States and Japan, but over the past year, the China tops the list and followed by Singapore. So all over the world, many users are checking this website. So please enjoy the precipitation climatology from this website. And this is a composite analysis about the tropical cyclones by GPM, DPR, KUPR. The number of samples are about 1/3 compared to TRMP-PR, but the more precipitation can be observed at the upper levels by DPR, KUPR because of the higher sensitivity. And at the lower level, the rainfall rate is affected by the blind zone, so we collected the low-level rainfall profile for around here. So we can detect the sharp difference between around the eye of typhoon. And from this March, latest algorithm is released, and this low-level precipitation profile collection is implemented in the latest algorithms. So it is expected for about 5% increase around the typhoon rainfall. As for the temporal variation, we can also extract seasonal variations of the diurnal cycle. For example, it's still difficult to see, but in Japan, this is in the rainy season. And in rainy season, southern part of Japan, called the Kyushu area, we experience morning rainfall around here. And it is resulting from widespread systems in JJA and MAM only around Kyushu areas. So as the data increases, this picture becomes clearer year by year. The same applies for Europe. This Iberian Peninsula is located out of the TRMP-PR domain, so it is still the sampling issue is difficult. It's significant, but we can say in winter season, the afternoon rainfall is less significant over these areas. So now we are trying to making the better spatial average, not to obscure the natural resolution. I will skip the data about this, but the cluster analysis also has been done, and we can detect monthly and diurnal cycle from the GPM and TRMP-PR dataset. But we want to, if we ignore the high resolution information, we can detect this kind of information, but we need more, and we can detect to detect the morning rainfall in the winter season in Europe, still we need more data set. And the sampling error can be ignored when we average all over the world. But this figure seems to be difficult, but there are red circle here, red marker here. It shows the global average, averaged over 36-degree latitude, and it fluctuates around -4 to 6%. In the medium value show underestimation because of the high impact system is rarely observed. But in average, it fluctuates around 0 compared to the baseline. But I think this fluctuation is closely related with retrieval errors. And I estimated 3 kinds of retrieval errors. That is low-level precipitation profile, and shallow precipitation deficiency, and weak precipitation deficiency. I don't talk deeply about this, but for this weak precipitation deficiency, I assumed constant contribution from the precipitation below the sensitivity for liquid and solid precipitation for before and after boost and PR and KUPR. and it affects a significant increase in the higher altitude. This LPP correction is implemented in the latest version, but these SPD and WPD are calculated statistically. Eventually, the precipitation by trim PR is increased about 12%, and KUPR increased 19%. So we can say underestimation of over 10% in total precipitation is resolved by these corrections. And it also reduces significantly the statistical artifacts between PR and DPR and between before and after the orbit boost. For example, the difference between PR and DPR was 5%, but after the correction, it became to about 1%. So this kind of correction must be done to evaluate to estimate the truth value. And the comparison with microwave radar data, that is GPCP and GSMAP data, we have several differences, and the response to ENSO and the seasonal variation is also has much different. So we have to pay attention to the sensor-derived difference. So in conclusion, still we need more continued observation, and careful screening is still indispensable to make the robust precipitation climatology. That's all. Thank you.
Thank you very much. We have time for one quick question. If anybody? I'm faster than you.
Yeah, the problem that you mentioned, that you have this flickering, one pixel, was not consistent. It didn't have a special structure when you were looking at the time to maximum precipitation. And you mentioned that the more record we have, the more this disappears and looks more smooth. This is exactly the problem I mentioned in my talk. So we should talk, because this is what a spectral approach, where you can learn the spectrum of the natural variability, the spectrum of the noise, and you can apply a low-pass filter, which is specific to the problem that you care about, that will basically separate the noise, or whatever it is, internal variability, from the signal of interest. So this is a perfect example where what we have developed would apply. So let's stop.
Thank you very much.
Thank you very much. We can now move to the next speaker, who will be Jessica Sutton, and she will talk about landslides and precipitation.
Hi, everyone. It's so nice to be here. Thank you, Vasco, for organizing this, and everybody that's on the committee. So today I'm going to talk to you guys a little bit of landslides and using high-resolution precipitation forecast. And so this is a joint effort. This is not just me, clearly. I do the precipitation analysis and the Lhasa output analysis, which I'm going to show. But all of the forecast models have been run by Jin Woong, and the Lhasa output has been produced by Thomas Stanley. So, all right. So our study motivation, back in 2024, NASA was asked by the coastal storm team to provide information about the upcoming Hurricane Helene. Now, we did that, and we provided a 24-hour, or the most recent 24-hour forecast using the GEOS FP precipitation product, which is what Lhasa, this global model, which I'll talk about later, uses. And so with that, we were able to take that precipitation, 24-hour precipitation product, which you can see on the left, and then it's input into Lhasa, and it produces landslide probability hazard. So the more warm colors, the red colors, indicate higher probability of landslides in that region. However, as you can tell, it highlights a lot of places, and how well did that do? So following this first thing, because we knew when Hurricane Helene hit how bad and destructive it was, we were basically asked by NASA headquarters, could we have done better? And so the second part of this was, all right, well, let's look at whether or not a higher resolution product would have done better, because they are available. And so this paper has just recently been published in Weather and Forecasting. If you guys are interested, I'm happy to send it to you. And I'm just going to show you a little bit of it. But we basically compared the GeoSFP, which is at a 1/4 degree resolution, which is what the global landslide model is based off of. And we compared it to HER, which is a NOAA product at 3 kilometers, and NAM, which is also a NOAA product at 12 kilometers, and then also an experimental product by GEOS, which was run by one of our colleagues, and it produced a 3-kilometer product. Now what you can see on here is the dots represent the landslides. These are preliminary landslides following Hurricane Helene that the USGS were able to map. Since then, way more have been mapped, but all the study has been done using these like 2,000 landslides. And as you can probably tell by the red and the yellow, the HER product performed the best. Now again, this is just published, so you can go and look at it, but this is also a 24-hour forecast. So the way you can read this is a rock curve graph. Basically, you want that graph to have this line that goes up and like that, right? So we want true positives to be true positives. We don't want any false positives. We won't want true negatives to be true negatives, etc. It outperformed. We also looked at putting them together as an ensemble, and it did pretty well, but seriously, HERB did the best. So with that, we now came up with this, well, okay, maybe we could have done better with a longer forecast, right? So this initial forecast was 24 hours. We did higher resolution, 24 hours. Definitely better. Could we have done better with a longer forecast? And so today, I'm going to talk about some of our preliminary results. It's not finished. I'm still analyzing. But basically looking at higher resolution forecast products using 1 kilometer forecast 3 days in advance. So basically the part of it is to identify which physics suite, we use 4 different physics suites, so I'll get to that, provided the most accurate precipitation, but then also the most accurate landslide hazard. And then determine whether or not this 3 days in advance actually is worthwhile to run, because these are harder to run. They're much higher resolution products. So this first part is just precipitation analysis. And again, I'm not showing everything, but I'll show you some of it. All right, so for this, we use the WRF system, which maybe you guys are familiar with. It's at 1 kilometer. And we use 4 different physics that goes into that. Each one of those is different in the way they handle microphysics. Some of them are bulk, some of them are using different bin schemes, and most of the time I think people are familiar a lot with Thompson. It's also what's used in HER. But we compared those 4, and then we also validated against NOAA gauges, which are an hour resolution, USGS gauges, which are typically 15-minute, but they range based on gauge availability. And then we also looked at stage 4 quantitative precipitation estimates, which are at 4 kilometers. And for the sake of the quantitative precipitation estimates, we had to change that 1 kilometer forecast up to 4 in order to actually compare them. All right, so these are some of the statistics and some of the interesting things. So this is based off of hourly precipitation. So how well did the hourly hindcast compare to the rain gauge observations? This is a map of the entire study area that we looked at. The actual landslides are within that North Carolina regions, but for the sake of the storm, we actually see a lot of precipitation happening down in South Carolina too, so we looked at this whole area. What you can see is you can see control on the left, Morrison, and Morrison with Grail Freites, and then Thompson. And these are all outputs based off of that hourly precipitation, and they're compared to the gauges that are located in those regions. Now the color and the size represents the R squared. I have other ones for root mean square error, bias, but I'm lack of time. And what you can see here is there are some areas that actually did much better, right? So some of those gauges were better correlated to what the forecast was providing. So really the hourly Thompson kind of won out, saying that that microphysics scheme was better for that. However, now we want to look at, okay, well, how will it actually do? So this is hourly, we could see that, but that's over that whole range of time, right? So from September 24th through the 28th. The actual landfall and hitting North Carolina was the 27th. But how well did it do over space and over time? So on the top of this, there's a lot of stuff going on, so I'll let it go. But at the top, you have maps of hourly precipitation from your control with a little triangle that's supposed to represent one of the gauges. Control Morrison, Grill, Frades, and then Thompson. And what you'll see as that runs is that they're highlighted by the 90th percentile precipitation. So you can see kind of as it moves, you can see exactly kind of where those precipitation is occurring and where the heavier precipitation is occurring based off that 90th percentile. On the left bottom, this way I kind of was able to put the pieces together. You can kind of see if you look through it where those overlap. Are they doing well in one area or not? And then on this bottom is a time series at just one location. This is in Asheville at the Asheville Regional Airport. And what you'll see here is something really important that sometimes we fail to pay attention to. Landslides, obviously, when we're talking about precipitation-induced landslides, when the land becomes saturated, that's when we start to have slope failure. Well, look at what happened right there at that Wednesday, Thursday time. This is a precursory event that was massive, right? The actual hurricane did not hit until September 27th. And on September 27th, when we actually see that, all of these models are doing pretty darn well on an hourly scale over that location. However, they are all missing the precursory event, right? Has to do with the physics that are going into these models to say what that precipitation is doing. And if you look at that, you can actually see Thompson, it just kind of goes that way some during that time. So it's really kind of interesting. We're still go through all the results. But another interesting thing is, so again, I compared the stage 4 QPE. This is a gridded product. It has gauges and it has radar combined in it. It's very comparable to MRMS. Lots of times in this region, stage 4 is known to be better, but honestly, I can't say this or this because I have not evaluated against it. But what we see here is these are some maps. So we have control in the first column, Morrison, Grove-Frades, and then Thompson. And these are the difference maps between your stage 4 QPE, our ground reference, and then the hindcast. And so you can see the most difference is actually occurring September 26th and September 27th. Some areas are saying it rained a lot more, some areas are saying it rains a lot less, but we see that those kind of points pop out. And what's very interesting is that the Thompson, and I'll highlight this in just a moment, has that band of dry right over that area. And if you look at this, this is actually the Blue Ridge Escarpment. Not many people in the area probably or in here really know about it, but it's a big issue when it comes to looking at precipitation. This is an artifact we also see in HER, which also uses the Thompson physics scheme. So something to be mindful of, that in this region it's actually showing some interesting stuff going on. So we're still looking into it, but super fascinating stuff. Okay, now I have to move on fast because I have a little time, and this is the interesting stuff. So now we want to say, okay, well, how well it did when we threw it into the LASA model. So to do this, we took daily precipitation, now not from the hourly, but the daily. We were ingested into the LASA model, and then we were able to generate predictions of forecast for it, or really hindcast, because this happened already. Now, the LASA model is a global model. It takes all kinds of dynamic variables like antecedent rainfall, soil moisture, and then it also takes things like static variables, like for instance, you have your peak ground acceleration, your lithologic grading, and your slope gradient. And it's all thrown in here, and we're able to try to generate landslide hazard maps, which are very helpful. Up until these projects, we've been using GeoSFP, a 1/4 degree resolution. Now we're using the higher. So what this does, we take this example precipitation hindcast, we throw it into LASA, it gives you an output. Then to evaluate that output, we basically turn it into a probability of a 0 to 1 using a threshold of 0.5. And then we also take our landslides, because that's really where we want to be able to compare it to. And we also grid them to at a 1 kilometer as well. And then we compare presence and absence. Now, these are some of the metrics. You guys are probably very familiar with these: true positives, true negatives, false positives, false negatives. This is the probability that we did that, so less than 0.5 versus over 0.5, and then the binary prediction. And these are some of the performance metrics that we looked at, which, again, I can go back to if people have questions about those. All right, so let's look at it. So, overarching question, did the 1 kilometer of 3-day precipitation hindcast provide more accurate landslide prediction? It did. And this is when it's compared to that 1-day forecast that is originally put into that global landslide model. So we're comparing the 1-day forecast from GeoSFP at a 25 kilometer, which is, again, not high resolution, but it's a global product. And we're comparing it to the 3-day forecast. Now what you'll notice, I didn't highlight it, but you'll notice this big red spot on all the graphs. You see that even with the other ones. That big red spot indicates that there's a high probability of landslides. It means it rained a lot, there's good slope conditions, it should be landslides, right? But there's not any. Now, we're waiting until the USGS finishes their landslide mapping, but what it looks like so far is there are landslides there. We just need to confirm it, and that's something that we're going to see. But if not, we fail in that region completely. So if we look at some of the statistics or some of those performance metrics, right? Same rock curve, not as good as some of the 3 kilometer, like the HERB product, but it does much better, and overall, the control actually does a better landslide prediction than what we saw with the Thompson in the precipitation analysis, which is also really interesting to kind of get into that. So I'm running out of time, but these are some of my summary slides, and I'd love to have questions if I have time. Thank you.
Thank you very much, and we have time for 2 short questions.
Sorry, I tried to go fast.
Because I saw 3 hands.
Hi, Jessica. Great talk and great work. Yeah, I guess 2 things that jump out at me. First, obviously, the combining rapid observations with forecasts would be super powerful, and this is a great example of that. But I guess also maybe I wonder, I realize that like in our work for the Famine Early Warning System Network, we've been told to predict the next 6 out of 4 droughts, right? So it's, in terms of like hits and misses, it's tolerable to have, false predictions of hazards that don't pan out if you help people get out of harm's way. So I just wonder if you thought about that when your validation statistics will beat you with a stick, but maybe from a human, safeguarding lives perspective, it's not so bad.
Absolutely, and that's something that's, I think, very important to be mindful of, but I also want to, like, when we're doing this, we want to also be honest and truthful and look at where these things are missing. And if you look at some of the other ones in the paper that we have, like, we're seeing the same type of information, and if you actually zoom out, right, it's showing landslides in other regions, and that we could do better, right? We don't want to give those false things. So, yeah, it's a great point. I appreciate that.
Yeah, I was just wondering about you mentioned about the gauges in the North Carolina area.
Yes.
So were you able to, I'm not sure it was available, but were you able to access the Duke gauges, Duke University gauges?
I haven't tried. That's a good idea. No,
So
I have
there is
not.
a paper just came out 2026 in the JTEC. So they are talking about 32 gauges, I-merge verification. Now, I'm not sure exactly, because this is September 24th. The study is end 2021. I'm not sure the gauges were still there, but most likely the case. There's a 32 gauges over the mountain areas.
That would be lovely.
North Carolina. That might be the golden, it could be your golden source right there.
Yeah, no, that's wonderful. Could you send that to me, Alex?
Sure, I will.
Also, the other thing is there's Coco Ross.
Gauges are available.
Oh, okay. That's wonderful.
He's the co-author of
Oh, okay. Well, great. I would love to. I'll add it to, because we're still writing up the paper. Yeah, absolutely. Thank you.
Oh, yeah. I think so.
All done?
It's
Okay.
better to move and so we'll continue
Absolutely.
the discussion
Thank you.
after on. So the next presenter is recorded by James Smith on the possibility of the next cut improvement.
"40 years ago, Vitek Krajewski and I worked at the U.S. National Weather Service on precipitation algorithms for the NexRad weather radar system. 40 years later, we're providing guidance to the National Weather Service on how to maintain high-quality precipitation estimates from a national network of weather radars. In the 1980s, the roadmap for QPE was Mike Hudley's 1984 design document with the unassuming title, NexRad Technical Requirements for Precipitation Estimation. It's an underappreciated masterpiece of hydrometeorology that's played a critical role in the contributions of the NexRad system to mitigating the impacts of weather hazards in the U.S. The hallmark of Mike's contributions is attention to detail. This holds for network design, algorithm structure, system maintenance, and uncertainty characterization. The current architecture for NextRad includes more than 140 polarimetric radars in the contiguous U.S., providing the capability for high-resolution precipitation estimates over much of the U.S. Network design should address requirements for both flood forecasting and flash flood forecasting, especially for settings with potential loss of life. High-density population centers, shown here in gray, are important settings for high-quality precipitation estimates. Range-dependent sampling of the atmosphere plays an important role in radar QPE. The figure here shows radar coverage at 1 kilometer above ground level. We're developing a comprehensive set of tools for addressing network design, algorithm structure, and uncertainty characterization, and we'll use these tools as the basis for recommendations to broadly enhance radar QPE for hydrologic applications over the entire U.S. In this talk, I want to focus on one specific problem, which is QPE for storms producing catastrophic flash floods. One of our recommendations is to specifically target enhancements to radar QPE for these storms. We're basing our recommendation on observational and theoretical analyses of storms producing catastrophic flash floods. In the previous session, I briefly described analyses for the Appalachian region, which ranks a close second to Texas in U.S. flash flood fatalities. Texas has the most flash flood fatalities in the U.S., and Texas Hill Country is its hotspot of flash floods. We've carried out analyses of 13 extreme storms in Texas Hill Country using observations from 4 radars, all during the polarimetric era. Our analyses use a reference KDP-based algorithm. The parameters were derived from disdrometer observations in Oklahoma, and they played a big role in development and implementation of polarimetric algorithms, especially for storms with hail. The hydrometeor classification during the periods of peak rainfall for each of the 13 storms is indeed hail with rain. I'll use the July 2025 Texas Hill Country storm to illustrate results. The dashed square here shows the setting for analyses of the July 2025 storm. U.S. Geological Survey flood peak measurements suggest that the South Fork Guadalupe experienced a world record flood peak, eclipsing the May 1935 Saco Creek flood peak, which occurred less than 100 kilometers to the south. The 3-hour maximum rainfall of 275 millimeters for the July 2025 storm is extreme, but it's less than half the world record rainfall in D'Hanis, Texas from the May 1935 storm. I think 275 millimeters is an underestimate, and the principal rationale was articulated by Pauline Austin in the 1980s. Pauline participated in at least 2 IPCs. At the 1988 IPC in Boston, she highlighted the role of vertical motion for radar rainfall estimation. Pauline directed the MIT Weather Radar Project for nearly 30 years and was a colleague of Mike Hudlow at the National Weather Service. In fact, Mike's 1980s architecture for the NextRad system draws heavily on the blueprints developed by Pauline. Pauline's focus on vertical motion has largely been lost over the past 4 decades, and it needs to be revisited, especially for storms producing catastrophic flash floods. For the July 2025 storm, rain gauge observations point to underestimation of the most extreme rainfall, with the caveat that there are no surface observations in the core of peak rainfall. There is systematic underestimation of rainfall with a mean field bias of around 1.4, and there is conditional bias with larger underestimation of the most extreme rainfall observations. Analyses of the 12 additional Texas Hill Country storms generally exhibit similar features. There are 3 storms in the collection with 2-hour and 3-hour rainfall accumulations larger than the July 2025 storm. Empirical evidence points toward underestimation the cores of peak rainfall, but not towards a path for enhancing radar QPE. And so the question really centers around the role of downdrafts. The equations here relate rainfall rate to raindrop size distribution represented by the raindrop spectrum in at X and the vertical velocity W. Rainfall rate is the sum of the rainfall rate with vertical velocity equal to 0 and the product of downdraft velocity W and liquid water content. Our reference KDP parameters are derived from surface disdrometer observations and thereby grounded in the assumption that vertical velocity is 0. The rainfall rate representation holds regardless of the drop size distribution, but the distribution has an important role to play through the liquid water content. We've carried out analyses with a gamma drop size distribution using parameters developed for heavy rain. From these analyses, amplification factors of 1.5 to 2 are shown to be possible. Upper-level polarimetric observations for the July 2025 storm point to strong updrafts and strong downdrafts. ZDR columns mark regions of strong updrafts with large values of ZDR above the 0 degrees C level. KDP columns mark downdraft regions with large values of KDP extending above the 0 degrees C level. Polarimetric observations also point to large values of liquid water content immediately below the 0 degrees C level. And these inferences are based on analyses from the severe weather literature dealing with downbursts, hail, and tornadoes, not on analyses of extreme rainfall. We need to turn this machinery towards QPE for storms like the July 2025 Texas Hill Country storm. Pauline Alston and Mike Hudlow provided the template for developing high-quality rainfall estimates from radar. We're following their path in developing recommendations for systematic radar QPE over the U.S., and we also build on Pauline Alston's insights to recommend a special focus on QPE for storms producing catastrophic flash floods. Thank you.
Okay, no question. So we can move directly to the next speaker, who is Brian Swaden, talking about trends in precipitation extremes. Is the mic working?
Okay. And it's motivated by the fact simply that we have these very long records of rainfall now. We have almost 40 years of passive microwave data and 20 years of spaceborne radar. And for the 40-year record, the climate's warmed by almost a degree over that period. So we want to, can we detect trends in mean and extreme rain events? And how do these trends, if we can detect them, how do they compare to current theory and observations? And there's a couple papers that Eric has written about these. I'm going to show results from these today. And a lot of previous studies have tried to look for trends in, say, global rain events or global rainfall rate. And I've listed a couple of them here. And you can see the numbers differ, and there's reasons that they differ. They look at different time periods, or they're looking at different products. But also, even within a given product, there's changes from one version to the next. And I've just put up a plot here. This is from a paper by Alex Mattis and colleagues of his. He's a postdoc at Goddard. And they're looking at the atmospheric energy budget, and they're trying to constrain that, and so they're using GPCP precipitation. And it just shows, this is latent heat, so it's a constant times the anomalies in precipitation. And it just shows that there's a lot of variability from one version to the next in GPCP. And I show this not to be critical of GPCP, but just more generally, blended products are great, and they have lots of very important uses. But using them to look at long-term trends and variability is probably not the best option available to use. And so what we wanted to do is to go back to the original data records. And so starting with the SSMI record, this is from Frank Wentz's retrievals. And what we've done is to select satellites which have the least amount of drift in their crossing time, and then intercalibrate those records. And you can see we've used 4 different satellites here from F8 out to F17 that cover almost all of this 40-year record. And over their overlapping periods, they're remarkably consistent with each other. So it was really encouraging to see how stable this raw data record from SSMI appears to be. These trends give us a global trend of about 3.5% per degree warming for the global ocean-only precipitation rate, which is roughly in line with what we expect from theory and models, and water vapor increasing at the Clausius-Clapeyron rate of around 7%. So this all was consistent with what our expectations were. We also looked at the instantaneous rainfall intensities and looked at changes in the what we referred to as a 99th percentile. This is just for tropics here. And what you notice here, again, there's this very broad consistency between different overlapping satellite records, but that the most extreme rain events are increasing much faster. Instead of 3.5% for the global mean, now the 99th percentile is increasing at close to the rate at which water vapor increases, at around 7% per degree. Now, we expect that the variance of precipitation should increase as the climate warms, and that's often explained somewhat heuristically is that when it rains, the rain will be more intense because there's more water vapor, but that rain events will be occurring less frequently in time. But that's not what the SSMI record shows. In fact, over the 40-year period of SSMI, there's been no trend in the frequency of rain events over ocean. So the frequency of occurrence of rain hasn't changed over this period. But what has changed, one, is the frequency of the most intense rain events, but also the frequency of the lightest rain events. And so how this increased variance is being manifest, at least in the SSMI record, is by a reduction in moderate rain events, but an increase in the frequency of rain events on the other side of the distribution. And I'm sorry I didn't explain, you probably figured it out, but these are, this is the change in the PDF as a function of deciles, and then we've just expanded uppermost decile. So yeah, what this figure shows is that there's a reduction in moderate events, an increase in the frequency of the most intense and least intense events. And then we wanted to see, just to make sure this wasn't just an artifact of just Frank Wentz's retrieval algorithm or different sensors, so we compared it over a shorter time period, 2001 to 2023, with the TMI and with GMI and with different different retrieval algorithms, and they're all, remarkably consistent in showing this reduction in moderate events with an increase in most intense and least intense. And then we've also went back and produced an intercalibrated record of the TRIM GPM. I won't go into details of how we intercalibrated that. But we find that same shape, at least, of the shift in distribution in the TRIM and GPM records. It's elevated relative to the passive microwave records, but this shape in terms of the change in the distribution of precipitation events as the climate warms seems to be a pretty robust feature that really lacks any, simple explanation. I'm not aware of any theoretical explanation or model-based explanation for why this increased variance happens in this manner. If you look spatially at how this trend in the extreme precipitation occurs, so this is the 99th percentile, and this is over ocean only. Everything so far shown is just over ocean. What you see here is that this increase in the most intense events is occurring at all latitudes, but it's most pronounced in the tropics. And this has also been noted in rain gauge measurements over land, over obviously a different period. And Paul Gorman has a nice paper kind of highlighting that. And again, why there's this amplified sensitivity in the tropics compared to mid-latitudes, no real explanation for in the literature. Lastly, our interest in the TRIM and GPM was to get over land, which is where rainfall really matters, at least if you're not a fish. And so we developed this intercalibrated record of TRIM and GPM. The top shows the tropical mean change in rain rate over land, and there's no significant trend over land. We were very impressed. We didn't use the GPROF to intercalibrate the TRIM and GPM records here. So this red curve that shows the GPROF retrievals over land is completely independent of our attempt to intercalibrate TRIM and GPM. But it looks very encouraging in terms of the stability of those records. So we are very impressed with that. The bottom graph shows the trend in the 99th percentile over land. And despite the fact that the mean rain rate isn't increasing over land, the most extreme rainfall rates are increasing according to this record at a rate even larger than Clausius background, so at 10% per degree over this period. And lastly, we just kind of wanted to do a comparison with what models suggest for this period. And so we've taken the same time period, and these are coupled model simulations from CMIP6. They both show an increase in these extreme rain events. And obviously we haven't defined the 99th percentile to be the same value for models as observations. They're all self-consistent. But what we do find is that in the models, these trends are roughly half of what we see in our estimates from the observational record. So over ocean, they're only 3.5% as opposed to 7%, and over land, they're only 5% as opposed to 10%. So overall, our take-home points, we do believe that these individual satellite records from the passive as well as TRIM GPM are able to detect anthropogenic trends in rainfall, both mean and extreme. I didn't comment on this, but there's also a distinction, if you're familiar with the IPCC literature, between the true hydrologic sensitivity, which is the response of precipitation just to changes in surface temperature, and the apparent hydrologic sensitivity, which is the response of precipitation to surface temperature plus CO2. So CO2 tends to dampen the precipitation increase. You can actually distinguish those two sensitivities in the observational record. So to get at the apparent sensitivity is just a trend that I showed. The true sensitivity is you detrend the data, and then you just look at interannual variability. And when you do that, you get a much higher sensitivity. This is the true sensitivity. And so I think it's notable that you can actually discern those two things in the data record. Also, in terms of the change in distribution, we see this reduction in moderate, but increase at either extremes. And the heaviest rainfall rates over land increase faster than Clausius Clapeyron. All of those things I put an asterisk by because I don't think we have good theories to explain those, but they seem to be robust in the observation data. And with that, I'm happy to take any questions.
Okay, thank you very much for your presentation. So Ali has a question. I'm Ali Behrangi. I'm currently GPCP PI, so I comment on the first slide that you showed. So, yeah, I agree. I mean, looking at SSMI itself is very important, and that's what we use as a calibrator for GPCP. However, if you just stick with SSMI, then the sampling has an issue. For every region, every grid, you want to get some data. You can't just use SSMI and fill out the entire picture. So that's why we use combination of SSMI, SSMIS, and geostationary. That's the only way that you can get enough sampling for your analysis. But I mean, for analysis that you did is fine because you just look at the entire ocean average and stuff like that using one sensor, which is fine. But just wanted to clarify that the reason why we use combination of sensors, not all the sensors, we just use SSMI, SSMIS, and geostationary just because of the consistency. And that's something that we need to do because otherwise we have no enough sample everywhere, every grid. The other point is when you compare different versions of GPCP, that's pretty much reflecting changes in GPROC. So in version 2, we use different GPROC, version 3, different GPROC. So if you use SSMI, SSMIS from different versions, probably you see changes in the variability as well.
Okay, yeah, I'm not sure I quite got the last point, but I agree, you know, the GPCP has a lot of different stakeholders, and we're just looking at one aspect here.
So we have 2 more questions. Christian.
Yeah, thanks for that really interesting and important talk. I just, you know, without being too simplistic, but when you say there's no physical explanation for the behavior of the streams going more than Celsius chaperone, it just seems to me like, especially in the tropics over the ocean, you know, you're going to have basically the vertical mass flux, and the Celsius chaperone piece just looks like the kind of booster component going up, right, with saturation, vapor pressure, but you're going to get a feedback where you get more vertical velocity because of all the movement shooting.
Yeah, there's debate on that. I mean, there's 2 general explanations given for this. It's been seen in cloud resolving models. One is it's either a dynamical feedback. The other is it's a microphysical feedback. Eric's first paper, we actually looked at trends in convective mass flux, or at least a proxy for it, and we don't see trends in the most extreme convective mass fluxes over this period even though the climate warms. Not that that's definitive by any means, but it's, but I agree. There are explanations out there. I just don't think there's evidence to support anything or just a firm foundation, a theoretical foundation to support what the change should be.
So the increased variability, more light, more heavy, less intermediate. If someone asked me what that was, I'd say, I don't know, let's ask Brian Soden. I'm not going to let you get away with just saying there's no. So what do you think?
No, I honestly, I don't know. I always would give kind of the standard line, well, when it rains, it's going to be more intense, but it's going to rain less frequently, but that's not what the observations show. I did have a conversation with Paul Gorman, who pointed me to one of his papers where, with Carolyn Mueller, where they play with the auto-conversion microphysics and a cloud resolving model, and they got a change in the PDF that looks something like that. Okay, so there's one model out there that can produce something like that. Take that for what it's worth, but I think it's largely unexplained.
Okay, thank you very much.
One last question. So, Brian, maybe I'm not sure, but that might be a reason partly explaining it. So we know the convergence zone is intensifying. I don't know if you have excluded like deep tropics and do the analysis again and include it and do the analysis again if that changes any of the conclusion, because it might be related to something like intensification of the deep convergence zone.
We do see that it tends to be a tropical phenomena in one of the figures, so it's much more, that trend is much more obvious in the tropics than in the exotropics.
All right, thank you very much. To respect the time, so we have to move forward, and the final presentation of this session is related to the downscaling of IRA5 using VOR by Carlos Ferrier.
Okay, thank you. I promise I will be short. I know I'm the last presentation. So I'm going to present an ongoing work started by my colleague João Ferreira that was already there talking about radars. And me and João, we decided to analyze more deeply the downscaling of ERA 5 using the Weather Research Forecast version 4.2. Those results might seem a bit incomplete because they are an ongoing work, but I will show what we get so far. In addition, it's important to say that this work was made in the scope of a project, a big European project named NCP, the National Collaborative Programs. They are an initiative by the European Center of Medium Range Weather Forecast, ECMWF, and with Copernicus Climate Change to improve national collaborative programs in each country of Europe. So Portugal is one of belongs to this program. Okay, why did we try to regionalize Euro 5 for Portugal? Because it was important, at least for our country, to produce less coarse products, to have more suited data sets to our region. We only, like in the past, we only used EDW interpolation methods in Portugal using the weather stations, and we needed a higher resolution product. That's why we decided to use WRF to downscale Euro 5 to fill those gaps without observations, those places in Portugal without observations, and to have a more confident climate information in regions, as I said, without observations. We decided to downscale essential climate variables from Euro 5, such as temperature, precipitation, and wind, but I will talk more deeply in precipitation because this is a precipitation conference. And the analysis we did, firstly, was more into precipitation than the other variables. That still lacks some validation. So the downscaling process worked like this. We retrieved Euro 5 data from 1981 to present, a resolution of 0.25. You all know, 3 hourly time steps. And then we used a weather research forecast model to downscale the Euro 5 global model to this D1 domain for mainland Portugal, for Madeira, and for Azores Islands. And then in the second step, we downscaled the first domain to the other domains, the 2, 3, and 4. The 2 for mainland Portugal, the 2 as well for Madeira Islands, and the 2, 3, and 4 for Azores West, Central, and Eastern groups. The two-step downscaling methodology, it was important to use because if we force the Euro 5 right into 3 kilometers, it would provoke some numerical instabilities, and it would not be possible to do. That's why we did it into separated steps. The parameterizations followed a paper by Miranda from 2021. Okay. The results of the downscaled Euro 5 using WRF are shown here in 4 different spatial aggregations. We can see the full grid in the A plot, in the A panel. This is an example of the climatology, the rainfall climatology 1991-2020 rainfall climatology for December in Portugal. And this is integrated in a platform which is already available for the public, so it's publicly available. It's the dataclima.ipma.pt, and those results are integrated in a national climate service. And because as I said in the beginning, we are in this project, and the NCP project. One of the main tasks of this project was to produce data, like a platform where people can click in the municipality or in the district and can download and see rainfall temperature, rainfall indexes for Portugal. So, moving on, this is an example of for example, this is for May 2026, the Euro 5 downscaled WRF for Portugal, aggregated by municipalities. And when we click in a municipality, for example, in a territorial unit, we can have information about precipitation, the rainfall normals, the 1991-2020, the 1981-2010. This is more like a public service. Assessing the rainfall errors, we can see that even though the WRF biases might seem worse than Euro 5, when we look at the root mean squared error and the mean absolute error, we can have in Euro 5 much more like dispersed errors than in WRF. So our conclusion can be that Euro 5 errors are worse or slightly worse than the WRF model itself. We can also see that the biases, as expected in summer, they reduce, as well as the errors, and in transitional seasons like autumn, spring, and even in winter, those errors, they spike, they are much bigger. Okay, this is one of the derived precipitation indexes that we show, the standardized precipitation evapotranspiration index that we show in this platform. People can also see the data and download the data. Get this information via the Data Klima platform, as well as maximum temperature, also available here in platform. This is an example for the climatology for July 1991-2020. And when we access the errors, and here I didn't compare with Euro 5, but that's an ongoing work, so we still want to compare with Euro 5 in other data sets. But the main conclusion is that, at least for the maximum and average temperature, the WRF model tends to underestimate the temperatures. Minimum temperatures as well, with much higher variability in the errors. Okay, yeah. This is for team maximum temperature and minimum temperature. The first panels are the biases, and the second and the third, the root mean squared error and the mean absolute error. Those are more consistent, and they don't have those like spikes and very high variability as we saw in precipitation. When we look at wind speed, we see a different result. We see that the WRF model actually overestimates wind speed when we compare it with observations. I forgot to mention that we are comparing with 53 observations from the institute, from the National Institute, from IPMA. And yeah, the results for wind speed is that the WRF tends to overestimate the wind speed against the observations. Okay, so final remarks on this work. The first one is that downscaling of Euro 5 using WRF actually improved the rainfall results, at least the errors, they were improved over Portugal mainland. The assessment of the errors shows that the WRF model actually underestimates rainfall and near surface temperatures, maximum, average, and minimum, and overestimates wind speed. Those regionalized products, the downscaling methods, they are of greatest importance for our country and for climate monitoring services, because they can fill the gap of not having observations. Regions with lack of observations actually they rely on this type of methodologies. The final remark, take-home message is that those results, this product is available on DataClima platform. Again, dataclima.ipma.pt. In the future, we would like to apply some the downscaling process that we used is a physical, dynamical downscaling methodology. But in the future, we would like to start to test some downscaling processes using machine learning and artificial intelligence. I think the results are going to be good as well. So yeah, thank you very much for your attention.
Any questions? Yes, on top.
So what do you think causes the biases that you see in the wind speed and the temperature? Because they're very constant biases, right?
In wind speed, we are not quite sure. We actually compared the results with other studies, and actually came into the same conclusion: is that the WRF tends to overestimate wind speed, at least in other countries, like in Europe. The minimum temperatures, the temperatures, it will be, our theory is that it can be related with the weather stations, because the weather stations are mainly installed in valleys. At least in Portugal, they are, we have, first of all, most of the weather stations, 60 to 70% of the weather stations are in the northern region of Portugal. So we have the results tend to be more representative of the central north part of the country than the south, that has less weather stations. And most of the weather stations are installed in valleys, so it can be one of the reasons for these differences between observations and the WRF.
Okay.
Yeah.
Cool presentation. I think it's really interesting. So when you did your comparisons with your gauges or your wind stations, did you do like a pixel to individual gauge, or did you merge them at all, or when you actually compared them? Does that make sense?
Yeah. It was as you said. Those comparisons we used the nearest neighbor for Euro 5 and for WRF grids, and we did the mean bias. So the results are the mean bias So the box plot that you see, they have the 53 weather stations results for the January, February, and that. Yeah. So it was the nearest neighbor that we used. Yeah.
Thank you, Carlos, for the presentation. This is very useful data. My first question was, is this data available on a gridded data set daily, or is it a monthly product?
Oh yeah, this platform, it still is a monthly, so it is available on a monthly time step, so it's not daily, neither hourly. The gridded data set, actually, that's interesting, because we don't make available the entire grid like in a NetCDF. But if you click in a pixel, you can download the data. So I mean, if it can be changed in the future, so I definitely will talk internally to make available at least NetCDF. It could be useful, even monthly. And yeah, in my opinion, I think we as well should start regarding the data, should at least make available daily data. I think you are right when you, as well, you questioned João. So yeah, I think I will internally ask for and try to force to make available at least daily data. But yeah, currently we don't make available a NetCDF or yeah.
Yeah. My second question is related with extreme representation. Do you have any idea if your downscaling represents well the extreme events?
Well, I don't know. Maybe João can I don't know if you, João, if you can answer
You can
this
talk
better.
later as well.
But the only thing I know is that the WRF, when we input the digital terrain, the digital model terrain, the WRF tends to smooth the orography, the topography, so it can clearly influence the extreme precipitation events, at least in the northern part of the region, where we have more mountains, so it's more mountainous. But maybe João can have a better answer on that. João, the microphone is behind you. Okay.
Sorry. So Carlos showed that we have negative bias in precipitation, right? Can you show it?
Yeah. Oh, yeah.
But for extremes, WRF gives a very high suspicious values. For example, for Açores, we have an island in the Açores called Pico, which is the highest mountain in Portugal. WRF gives a maximum of 9,000 millimeters, which is
it's
very, very high.
Unrealistic. Yeah. My final comment is on the forcing data. So you used ERA 5. The experience I had in the last months is that there is already a very good product in the European Center, which is called Serra.
Serra, yeah.
Yeah. And most of these issues with the wind and precipitation are already solved.
Okay.
The only problem is that it's at a lower resolution, so it's about 10 kilometers.
Yeah.
But specifically for the wind in the coast, it's a much, much better product.
Okay. Yeah. Actually, when I was talking about that, we still have to make more error assessments on temperature and on wind. I mean, we have to as well in precipitation to add Serra. It's one of the. It's in the pipeline to do. And in temperature and wind as well, using Serra, ERA 5 and ERA 5 land maybe as well, to compare, like have 4 or 5 models to compare with these results. And yeah, wait for ERA 6, maybe we can have better results, and then do the same process with ERA 6. But yeah, that's our ideas to the future, so the target will be those models, yeah. Thank you.
Thank you very much. We can now, I guess, close this session, and we have the final session for the final discussion led by Sarah, right?
I just wanted to start with an observation. I've really enjoyed the sessions today. And so the theme of this was bridging observations and models. And I was thinking about if I heard that phrase 5 years ago, I would think something completely different from when I hear that now. Because all of these talks about machine learning and training, I mean, the models are being built by the observations. And it brings up a lot of interesting questions about the training data and truth. What is truth? And I think we saw with some of the Q&A today that people can actually get a little bit prickly when you might suggest that what they take as their truth is not the same thing you see as the truth. So I'm really excited about these conversations that we're going to continue to have. So this discussion, I'm hoping we can get a nice, robust discussion going and then bring it on to dinner with us tonight. Precipitation 2040, the terminology comes from a NASA long-term planning exercise called NASA 2040, and years ago I started thinking about, oh, you know, what about in precipitation as a field if we started thinking that far ahead, with the idea that if we had some directions, we could start to slowly turn our big ship that way. So I think it started at a PMM meeting, and then maybe we had the discussion at the last IPC. But so that's where that came from. I'm just going to show a few slides, and then I'm really hoping that you all will take over and we'll just have a nice discussion. I have some prompts on the slides here, and if there are lulls, we'll just move on to the next prompts. But as sort of an introduction to start, I mean, I think it's an understatement to say that we are currently in a very dynamic period in our science and the way things are working. A lot of precipitation science has been focused on GPM and the mission, the constellation. And the core satellite itself is going to begin drifting down in 2031 and re-enter in 2034, according to the current solar cycle forecast. So we need to start thinking about where we go from here. And then the character of the constellation that, you know, we've been using that core satellite to calibrate to is also changing. We have an influx of smaller, shorter-lived radiometers. We now are seeing commercial contributions to that constellation and a shift towards higher frequencies. We have radiometer observations going back now, you know, into the 70s, and we can very happily make global maps. But I was really happy to see Brian's talk. This is exactly the point that I like making, that we can't use this to look at trends, right? We might be able to make these maps going back, but there's a change throughout these years in the information content that is contributing to those maps. And so these are all plots that Chris Kidd made years ago, just sort of demonstrating. On the left there is a timeline of the radiometer constellation. The blue lines correspond to imagers, and the green lines correspond to sounders. And you can see, you know, we have Simmer going all the way back late in time by itself out there. And as we move forward, and then on the right-hand side, actually moving into the future, we have a nice big constellation. We do see more of a shift towards the green, towards the sounding satellites. And we start to see, this is a little bit old, but the introduction of these small sets like Tropics, now Tomorrow.io, et cetera, et cetera. So a little more heterogeneous as time goes on. And these things make a difference. The information content is different from these different satellites. So I'm not going to spend a lot of time on this, but these are some plots that I made using the GMI radiometer. I did precipitation retrievals using different subsets of channels. So the black lines in the zonal mean plots there correspond to using all of the GMI channels. The dark blue is the very lowest channels. The lighter blue is similar to a trim set, and then it moves up in frequency. And so you can see that when you don't have the full set of channels, over the ocean, you're typically retrieving less precipitation. Over land, it's a little more complicated. But these are not like some sort of easy to subtract bias. If we look at those differences on a map, it's complicated. You know, there are differences in convective cores and the stratiform around it. You know, this isn't something where we can just fix it by subtracting a number. So I want to start discussing, and you know, my introduction was heavily biased towards satellite observations because that's the world I live in, but I'm hoping that we can also talk today about models and radars and et cetera, et cetera. But the first big broad question is, what should the precipitation observing system of 2040 look like, integrating all of these different things? We've heard a lot about various gaps over the last 2 days. Is there a single most important one, or should we be spending our time broadly over all of these things? Which current limitation most constrains the progress? Oh, and just a note, a lot of these questions were emailed out to you as a survey. We were hoping people would answer, and then we could use your answers to guide this discussion, but apparently 2 people answered the survey, so we're starting from scratch. What should the next generation precipitation algorithms prioritize? And this, I think, gets at the idea that I was talking about, you know, truth. these next generation algorithms are going to be machine learning based, so do we all need to decide together what's truth, or can we have different versions of the truth and different algorithms? Which scales should be prioritized? You know, the previous session suggested that there is a whole lot of value towards, you know, higher scale applications needs. And how can and should applications guide future observing systems? So, you know, we saw today that these precipitation products are being used to do things like answer questions about disease forecasts and landslides, and this is important stuff. So should that be guiding the way that we are developing our future retrieval? So this is your first prompt. Jessica, you want to start us up? I guess I need a microphone.
Yeah, I'll take a go at it. So I think it's really interesting. The first question is the single most important observing gap. I don't know if there's just a single one, but I think it's really important, at least from my work, of the importance of still gauges and ground information. Because I feel like as we're moving forward with more machine learning and more AI, I don't want that to disappear, because for us, right, what's on the ground is important. And we don't want to like kind of ignore that. And I feel like we still need to be pushing for more gauges in more places that we don't have them. And to be able to actually have that information, I don't want to like jump off and just forget about that. And and like thinking about the way in which we're doing it, right? Could we optimize it? Can we do it better? So anyway, that's my 2 cents for the first one.
More gauges. All right, we've got lots of hands going up now.
Okay, I will jump on, build on what you said. So historically, when ground-based radar started, we saw a decline in the engaged networks because there was a tendency to believe that radars would replace gauges. So I would build on what you said, and by analogy, more AI shouldn't mean less physically based models. We should use AI, we should use observations in order to refine the physical knowledge.
The mic there. You know, I didn't see in any of the presentations yesterday or today talking about the problem of horizontal advection, because to me this is the biggest, or one of the biggest uncertainties when you use gauges along with remote sensing, because what the radars sense is not at the ground. You want the information at the ground. And you know, in terms of like how do you incorporate that, the easy way to do it is with Lagrangian trajectories, either back trajectories or forward trajectories. But if you do that, you end up with an irregular space grid. And so as far as I know, there's no technique that uses an Eulerian-based correction method for this. So if you want to make progress in terms of, you know, what's the most current limitation, I think solving the advection problem is probably going to be the best bang for your buck. So if anyone has any thoughts on how to incorporate advection into these corrections in these AI models, that would be probably helpful.
Yeah, I would really love to see a physical precipitation retrieval algorithm that works globally, because I mean, I don't think that exists. Yeah, but I mean, it's like, I mean, there is none, right? I mean, there's maybe mirrors, but even that is not, like, the precipitation is a parameterization in the end. Like, it just doesn't exist. Like, I think it's wishful thinking. Huh? Retrieve precipitation from satellites accurately. I mean, but like I mean, the point everybody always says we need to keep physical algorithms around and not replace them by AI. There are no physical algorithms, right? I mean, what are there? Do you have one?
It's called physics.
No, I mean, but it's not even fundamental physics. It's not, right? It's not. There is no. It's not derived from quantum, or what is it? Yeah, it's not fundamental science. Like and even then, right? It's based on probably single column assumption, the radiative transfer, which is all wrong. Like every physical, you have so many approximations. Like have you developed a physical precipitation algorithm? How many fudge factors have you adapted for that?
Yeah. But I would move us on and say that I think that one of the biggest gaps is really data continuity, right? So on one hand we have GPM going away, these small satellites coming in, very discontinuous. I don't know how many people have really looked at the number of stations going into the GPCC data set, that it's really fallen precipitously since 2010. And yet, nothing against the GPCC, they do heroic work, but the number of stations are totally plummeting in a lot of the global south. And at the same time, you need to do things like route declarations, you need to have like African risk capacity, declaring a disaster when Malawi gets slammed by Cyclone Freddy, right? And so there's this big discontinuity in direct continuous data. So I think that's a major concern.
I will not talk about precipitation retrieval, but one of the gaps, I was expecting a bit more application-oriented talk also during this day. I don't know for tomorrow. But still, I have the problem that, to me, we are developing something that, I'm saying something strong, that basically nobody is using. So a very little number of people is using, at least with respect to the data that we are developing. Also today, we see some application for some single events, always over US. That's fine. But I think that these kind of things is, I don't know, probably I'm not aware of what is going on, but precipitation is the main driver of the hydrological cycle, and still anybody is using gauge, and we know the limitation of that.
Here is something that may or may not make sense. For whatever reason, people like to keep a gauge at home when you give them one. So Kokoras go beyond 50,000 in the US. In 15 years, if you make cheap enough tipping buckets, people will gather it together at home and provide data for free. And that may solve great problem. Well, with new tools, it shouldn't be that hard to screen and do quality control, because it will be so many of it. Yeah.
Go ahead, Chris.
I guess, in 2040, I'll be 88 years old, so.
What do you care?
And I won't remember my name, so I'll say it now. But I think, we saw it in the talks today, right? That if I want to do early warning diseases, I need lots of satellites, high resolution, no time delay. If I want to understand what Brian showed, I don't need any of the CubeSats. I need some big radars, and I don't care about time delay or anything else, right? So I think the real question you have to ask yourself at some point is who the hell is going to want to pay for this, right? Because it's not me. And if it's not me, you don't really care what I say. You care about the person who's going to write the check. Right? So I think if you start thinking about what are the problems of 2040, and who do we need to convince that this is essential for their well-being, you start narrowing in on what we need to do for that. Right? But I always think it's a little funny when we decide what we want to do when somebody else is writing the check.
Yeah. And that goes to your point also, and it's this idea of an applications-driven approach is sort of the direction that we need
to go. So one of the big problems of 2040, something's still in my memory, but those have to be the problem.
Yeah. Go ahead, Ali.
Okay. On the the discussion of data-driven machine learning, pure machine learning-based precipitation estimation and physical-based. I just want to I mean, in hydrology, we have the same similar problem. We're not dealing with necessarily precipitation retrieval. We're doing stream flow retrieval. And we see LSTM methods purely based on machine learning are providing most of the time the best results, beating all the physical models. However, there are cases that we have data scarcity. And when we have that situation, the physical model can be very helpful in bringing up the gaps that we can see in the purely data-driven method. So I assume the same thing probably happens in the precipitation fields. When we have lack of data or bad observations, then we have to go back to physics to compensate for some of the things that we cannot learn. Or, I mean, like, we don't have certain channels that you explained. Maybe that's the time that we need to incorporate more physical stuff into this, method, whatever. So they could be complementary, but in most of the time, we see that purely data-driven method works, but not always.
Yeah, so I've switched now to the next slide because, of course, machine learning is woven through everything that we're talking about here. But I think an important thing that needs to be part of this discussion is that when we're training these models and we're training them on the truth, often, if your truth is a satellite retrieval, it has some model information in it. If it's coming from high-frequency sounders, it's an indirect relationship where we're modeling how we think ice scattering is related to precipitation at the surface. So all of these things are sort of incestuous, and it's not as simple as training a machine learning retrieval on the truth and getting the right answer. So I'd love to hear more discussion on what everybody thinks about. Here's a new prompt that's just specific to machine learning. We need lots of data. We need really good data. Is what we have sufficient? How important is explainability?
Well, I mean, in terms of the last point, how important is explainability? I mean, one thing you could do is you could just hook up your AI model to WARF and just have it play around with uncertain parameters. And that way, instead of training to get the output that you want, you train based on the parameters. So maybe that's the way forward. That way, you can have a hybrid model. You have the best of both worlds, where you can get the effectiveness of AI, but then you can also get a little bit of the explainability because you'll have the parameters.
So to the point whether current capabilities are sufficient. So I think with gprof, we're pretty much at the limit where we can get with just the passive microwave retrieval, and where we need to improve is the reference data, so combined. I mean, like, most of the pain in developing gprof was working around the issues that come actually out of the reference data. And if you think about how we can improve combined retrievals, then we are far away from being able to do that, right? Like radiative transfer, microwave scattering radiative transfer, in my opinion, has not made any progress in the last 20 years. We still have 1D radiative transfer, which just, if you, like, it doesn't work. Like, you assume that the radar and the passive microwaves do the same. It's not true. And nobody thinks about it. And also, there is no willingness to fund it. I think Will McCarthy said it. He wants the things, NASA wants to fund things 80% of the way. The problem is we're going from 8, like, if we want to do climate, we need to go to 100. But there isn't really, people don't want to fund this. It's kind of what a lot of people call boring engineering, right? We need fast radiative transfer so that we can actually model. This is, it would actually be a physical retrieval, so apparently people would love it, but it's like, it's also boring in engineering, right? So I think we don't have the capabilities, they're not sufficient, but I also don't really see how we're getting there. It's not obvious to me.
Yeah, Jessica.
I think Simone did a really good point on there. I think we need to do better at saying why it's important, right? That's something that's happened recently. if our science is not important, if we can't communicate it, then we're not going to get funding. And with the current funding the way it is, at least in the United States, that's a big problem. And so we're being pushed to say, well, how is it actually important? And so maybe something we need to do as scientists is think about how to communicate that in a way that people care, right? Like we suck at that, I'm sorry, but we do. And to make it to where it makes sense of why people would want to fund it, right? If we can't convince our own organizations to fund it, there's a problem because it is important. That is a problem that we need to fix. So maybe we need to start with thinking about how we sell it. I don't know, just a thought.
Yeah, and I would argue we're not even great at selling important things to ourselves within our community. Like talking about radiative transfer, we are now able to simulate particle scattering from like extremely complex ice crystals. However, we have absolutely zero idea how to implement that information into a retrieval. Like there's a disconnect.
So I have a concern with respect to AI age. Not because AI is a bad thing. I always use AI, it's a very good thing. But say one group, precipitation group, come up with their own AI method to capture precipitation. Then ET community comes with their own AI method to come get ET. The other community comes with their own machine learning-based method to come up with that variable. But how the whole variable is going to be consistent? That's something that I always think, man, is like individual components might be great, but they may not talk to each other. And I mean, the good thing about models like Era 5 things that are self-consistent to some extent, they're all helping each other. I mean, eventually the results or the variables are communicating. But I don't know if we do individual, I mean, if we do best for individual, eventually they all help each other or meaningful in terms of physics. That's one thing that I'm a little bit concerned, so maybe we can discuss that, like across earth science, how we should deal with individual components that currently we can retrieve very well with AI.
Any other comments on that one? Can we move on to the next prompt? Commercial constellations. What opportunities and challenges does this bring? I'm so excited to see that we have some commercial representation at IPC this year. So this brings the question of, what does the division of responsibilities between the public and private sectors look like? What should be open and public? And where can the private sector add real value without weakening things like access, transparency, and public applications? What are people's thoughts on that one?
Yeah, I feel like the obvious thing is that we do climate, because if you launch a satellite now, it won't help you at all with climate. And it also feels like this is where, I'm not sure, but probably least of the money is, at least right now. Maybe. So that would be kind of an obvious thing for me.
Yeah, of course, climate and satellite retrievals is a tricky situation because of information content and consistency over time. But that's true. That's not a moneymaker for the commercial sector. Sure.
Right.
Absolutely. That's true.
Just saying
that's true.
Yeah. Climate now.
Another comment? Everybody's getting hungry for dinner? Let's see. Go ahead.
Oh, I guess on the commercial versus public sector debate, I think it's an interesting one and a scary one, at least for me, because at least for the commercial, I mean, the incentives that you have in the commercial sector are not the same ones as you have in the public sector. So maybe it's a stupid example, but I know, imagine you have a satellite that is not necessarily, does not produce a lot of revenue or whatever, but it's really good for a particular application that has a lot of good outcome value for the public sector. So it's, in my opinion, I don't really like that they're going like so much into or that the commercial sector is taking so much space, because I wonder like what will actually happen in the future. Will this just be driven by the economical aspect of things and not like climate change, etc.? So yeah, I just wanted to share my opinion.
Valid point. Andrea?
Okay. I'll walk and talk this over to Andrea at the same time.
Oh, I think she's got it.
Oh, she's got it. Okay. Yeah, I guess I would just say that, I think that there are ways that private sector and short time scale and advances in satellites and climate scale and data continuity, can interact.
For sure.
So one example is El Nino, right? So if we have long, robust data sets, we can tell where you're going to see El Nino extremes, like we're going to be worried about flooding in Kenya. And at the same time, the people that I'm working with, partnering with Tomorrow.io, who's working with the Med Agency to do ag advisories. And so, we do powerful work both on the climate time scale and the weather and there's opportunities.
I think, don't yell at me, but I'm going to oversimplify, or, I don't know, you get one. But the public good side, I think it's naturally going to fall a lot on the public, because you're going to see a lot of organizations that rely on free, open access data because they're limited time and limited resources. So they'll take anything that they can get without reducing increasing their workload, or even, making sure that their time resources, especially, leveraging like third-party platforms. So if they can easily write an API to access information like GPM, and we provide that information, that is extremely helpful. So I think, not saying, private sectors, especially if they have the nonprofit component, I do think we need to recognize that, especially globally, we're not just talking in the US, but globally, but there's many organizations that use the data and leverage it, and that's going to, if we just cut off or simply not really think about that time, it's going to disrupt a lot of systems.
Well, if we look at the optical side of Earth observation, they've been having the commercial sector very active for many years.
For sure.
And we look at companies like Planet, and we see the share of commercial revenue dropping from 5 years ago to now. So I also wonder over the long run whether the private companies, and we have people who can talk about this a lot better than I do, but I wonder if in 5-6 years we're going to see like a huge share of revenue coming from public contracts with the government, maybe a lot of dual-use defense contracts as we're seeing in the optical side, and not so much a replacement, because we see, for instance, Sentinel-2 is still up and flying, of course, coarser resolutions than the commercial satellites, but maybe that's going to be the future. We'll keep some satellites up for standard and calibration, and private companies will fill the other gaps. I don't know.
I think that between now and 2040, that shift, I think we're probably going to see that.
Yeah, so I guess from our perspective, we would love to launch sort of a Simba ATMS equivalent class, backbone sensor and have it fly for a long time. Obviously, that's very expensive. But ideally, with the NOAA data buys, if they sort of shift the money that's going into the backbone sensors to commercial, it'll still be the same capability, but it'll just be funded, slightly differently. Sort of the perspective there. And the question then becomes data ownership, right? There's a huge value in having the data freely accessible, obviously, for the purposes of scientific inquiry and, even operational, right? That's sort of where the line is harder to define, because, on the one hand, we definitely want that data to be available when it can, save lives and help with disasters. But on the other hand, you need to still recoup costs if the government's not footing the whole bill. So, there's a fine line there between uses for disaster and uses for maybe insurance, where, maybe one is not so critical. You can sort of give the data away in one way, whereas you're still making money in another. It's going to be an interesting time.
Definitely agree with that. All right. Extreme. This is such a huge topic at every meeting, extremes, extremes, extremes. What needs work here from the precipitation side? In observations in particular. Obviously models have their own issues, but we know that the satellite retrievals are not great at this. How can we steer our slow-moving ship in that direction between now and 2040? And then, just as an example, droughts are an extreme. Should we be working, we still are pretty siloed. Do we need to be working more closely with other communities to attack some of these extremes?
Yeah, I would say we have, I'm not sure we actually want to handle extremes because we have mathematical techniques to do it. We're just not using them. It's like, I'm always saying like, yeah, give me an application and we can do extremes. It's just, I feel like, as long as this discussion is kind of unguided, if you only try to match like the distribution of your training data in ML, which is what a lot of papers essentially do, even that can be done. But then the question is like, what for? Right? We always we know it's an inverse problem. The satellite precipitation retrieval, there will always be uncertainty, and that's where the extremes lie in these uncertainties. So we need a probabilistic approach. Whether that is what Effie was proposing, we have these techniques, right? We just need to basically use them. So I think, yeah, I guess to put it a bit more positively would be, yeah, we need to bring the applications and the retrievals together.
I think we've spent a lot of the last 10 years, just trying to get the global averages, and I feel like we're there. So now it's time to sort of upgrade.
The comment here is related to the link with the other variables. I don't know if you know about the Schmidt signs that they opened some call, because in the first slot, basically high resolution modeling, everybody is using reanalysis. And I probably submitted 3 proposals. I don't remember exactly, because I was approached from people saying, come on, if only reanalysis, we need also to use remote sensing. And the point in this call is actually the consistency between precipitation and the VAP. And also, for instance, we submitted another study more focused on some monster. I think that this is something that is really missing, the use of this kind of global observation also in this kind of study. Also in this kind of let's say, scientific study. That basically, if you want the data, if you go to ERA 5 or, I don't know, MERA 2 or something, that is easier to use because they are there, the data every hour. And then also, yeah, we talk about SMAP level 4 is every hour, better. But it's not observation. So the use of this observation and how to use them and how to handle the problems is something that would be really useful to do. At least to have something different from modeling.
Me again. I actually disagree with your comments about extremes. We don't know extremes. Paper after paper, we don't know extremes. We either misplace them, we can't put them directly over parts. As far as precipitation goes, the timing is not correct. We need to think of like sub-daily. When we're thinking of intensity, like we don't have the extremes. So I completely disagree. Maybe theoretically we could get there, but I think there's more than that. I don't think we do a good job at extremes, especially with things even like snow, right? But in any case, I have to disagree.
I don't know that, I don't want to speak for Simone, but I think he was more saying that it's not that we have them in the retrievals now. He's saying that we know how to do it, we're just not doing it. So, what would you think? All right, so I think it's almost time to head for dinner. I want to hit one more here. This is another thing that's for sure happening, and that we're moving from these big, expensive flagship type missions to constellations and disaggregating everything. That obviously changes the information content, and the continuity because of that. So what do we do about this? How do we deal with this and keep consistent products that can be used consistently?
It's just open source data sets, having trained data sets people can use and apply their models on. You can just compare the results. I think it's that simple.
That makes an interesting question for, at NASA anyway, commercial data is meant to be a part of these disaggregated constellations. It's not clear to me that developers will all have access beyond the people working with the agencies. So that's an interesting question. Any other comments? It's 5 till. What do you think, Vasco? Should we close her out? All right, great discussion. Thank you, everyone, for speaking up, and let's keep it going over dinner.
Okay, so dinner's next. It starts at 8 p.m. The location, you can find the location on the conference website. It's called Quinta das Lágrimas, for those who understand my Portuguese. There are 2 shuttles for those who booked the shuttle. Those who didn't but can have a seat available can also use it. The first ones will leave at 7 p.m., so right now. And the next one will leave at 7:30 p.m. I do have 2 or 3 seats available in my car as well, so I can also take some people to the venue, but I will be leaving probably in about 30 minutes. Thank you. Those who get there early, feel free to start having some drinks, and we'll meet you there.